Chasing Reality, Strife over Realism. X contents. Nowadays billions of us spend long hours watching screens of various kinds. But of course we all know that the most interesting and important facts and ideas are behind screens. This is why we look for objective fact behind appearance, for cause or chance below event, for mechanism behind behavior, and for system and pattern underneath particulars. All these tasks require rigorous imagination, in particular, disciplined fiction rather than myth-making. Although we are immersed in reality, our knowledge of it is not immediate. The ancient atomists and the founders of modern science and philosophy, in particular Galileo and Descartes, knew that the senses deliver superficial appearances rather than deep realities. They went after real things with primary or mind-independent properties, and some of them made use of mathematical fictions, such as functions and equations, to account for facts. Not that the secondary properties or qualia, such as color, taste, and smell, are unimportant for organisms, quite the contrary. But qualia reside in nervous systems, not in the physical world around them. The universe is colorless, soundless, insipid, and inodorous. Besides, the scientific investigation of qualia, in particular their explanation in terms of primary properties, had to wait for the emergence of cognitive neuroscience in the 20th century. For instance, it has only recently been learned that optical and auditory illusions are dysfunctions of the corresponding brain subsystems. And yet some of the most influential early modern philosophers, namely, Berkeley, Hume, and Kant, as well as their neo-Kantian, positivist, neopositivist, phenomenological, hermeneuticist, conventionalist, and constructivist relativist heirs, have been teaching exactly the opposite. Thus, the phenomenalists claim that only appearances count, and the hermeneuticists or textualists, or general semioticians, that only symbols matter. Indeed, the former repeat Ptolemy's contention that the goal of science is to save the phenomena. The textualists claim that the word is the abode of being, Heidegger, whence there is nothing outside the text, Derrida, and that facts, or at least the social facts, are texts or like texts, Charles Taylor. And neither the phenomenalists nor the textualists know where to place the mathematical objects, for which they have no use anyway. Given these serious lacunae in contemporary philosophy, it is clear that the nature of facts, appearances, and fictions deserves further investigation. This book is about hard facts, superficial appearances, and fictions both tame like the number and wild like Cocken. The concepts of fact, appearance, and fiction constitute a family, since neither of them makes full sense in isolation from the other members of the triad. Indeed, appearances are facts as perceived by sentient beings, and fictions are either large distortions of facts or inventions unrelated to facts. Facts, in turn, occur whether or not someone perceives them or fantasizes about them. This is a realist postulate, which everyone presupposes but few philosophers adopt explicitly and consistently. I will argue that this postulate underlies, albeit tacitly in most cases, the exploration and deliberate alteration of the real world. I will also argue that, paradoxically, no such exploration succeeds without fictions, particularly those of mathematics. The fact-appearance-fiction triad occurs in all walks of life. Indeed, when trying to understand or control a piece of the world, one must often distinguish and interrelate three layers, those of fact, appearance, and fiction. For instance, some politicians and media invent fictions about the public life, and these fictions contribute to shaping our perceptions of society. Meanwhile, the political and economic currents continue to flow underneath fictions and appearances, largely unaffected and undetected, and therefore beyond our control. The unwary citizen may thus unwittingly become a casualty of what have been called weapons of mass deception. By contrast, the alert and responsible citizens are constructive skeptics. They start by peeling off superficial layers of reality, so as to uncover the hidden social mechanisms and so be able to act upon them. They are philosophical realists. Unsurprisingly, therefore, the fact-appearance fiction triad is at the center of some of the oldest and toughest philosophical problems. For instance, how can we know that there are things outside our minds? How are we to proceed from observable fact to conjectured cause? How did Newton solve the so-called problem of induction, of jumping from data to hypothesis, a problem usually attributed to Hume? Does appearance differ from reality, and if so, how? Are raw feels, or qualia, such as sense and tastes, irreducible to processes describable in terms of primary properties, such as those of odor molecules? 12 Preface. And olfactory receptors? Can possibility and disposition be real? What, if any, is the ontological status of mathematical objects? How do they differ from mythical and artistic characters? Are causation, possibility, and chance real despite being unobservable? Is probability a measure of the strength of belief, or else a measure of real possibility? And are there objective laws, or only data packages? In addition to the above ontological and epistemological problems, we shall tackle the following methodological ones. How may we find out the way things actually work behind appearances? What is the use of speculating about alternative worlds? Why wonder about the truth value of contrary to fact statements? How can we best handle inverse problems, such as going from desired output to both requisite input and mechanism? Is there more to explaining than subsuming particulars under generalities? Can scientific theories be directly confronted with facts? What is the status of indicators such as vital signs and pointer readings? And why is it still respectable for philosophers to question the independent reality of the external world at the same time that scientists are discovering ever deeper layers of it, and practical men are altering it for better or for worse? We shall also ask whether it makes any sense to extend realism to embrace values and moral principles. In other words, we shall ask whether there are objective values, moral facts, and moral truths. Besides, we shall ask how far realism can be advanced without making certain assumptions about the nature of things. In general, is epistemology independent of ontology? In particular, can scientific realism thrive independently of materialism? And can their synthesis, which I call hylorealism, account for mathematics and other imperceptible cultural objects? Finally, in the course of our investigation we shall meet a few historical problems. In particular, we shall ask whether it is true that, as most historians of philosophy have assured us, Hume and Kant were the philosophers of the Newtonian Revolution. Next, have the modern-day subjectivists added anything to Berkeley's teaching? And have the social constructivists succeeded in constructing anything resembling real life? Another such question is whether the logical positivists' professed love of science has been reciprocated, and did they solve any of the philosophical problems raised by contemporary science and technology? For that matter, did any other contemporary philosophical schools, in particular dialectical materialism, phenomenology, and linguistic philosophy, improve on the ways to chase reality? If not, why not relearn the lesson that the ancient Greek and Indian atomists taught 2.5 millennia ago, that the familiar is best explained by the unfamiliar, data by constructs, and facts by ficta, rather than the other way round? In short, why not chase reality instead of either taking it for granted or attempting to elude it? This book is part of a lifelong effort to update philosophy with the help of science, and to unmask unsound philosophy posing as science. What started me on this road, as I was finishing high school, were some of the best-selling popular science books in the 1930s, those of the famous astrophysicists Sir Arthur Eddington and Sir James Jeans. Eddington, the first to confirm Einstein's theory of gravitation, was a subjective idealist. He claimed that we only find what is already in our minds. And Jeans was an objective idealist. He taught that the universe is a mathematical text written by God. I wished to refute them, but was unable to for lack of the requisite knowledge. This is why I decided to study physics. However, at the beginning of my research work in quantum physics, in the early 1940s, I swallowed the standard or Copenhagen interpretation, which is operationist, hence semi-subjectivist. My realist epiphany came only a decade later. During a break of a meeting of the Argentine Physical Society, I suddenly realized that, when describing a free electron, or calculating the energy levels of an atom, one uses exclusively variables describing properties of a thing that is not being observed by anyone, that is, a thing in itself. That experience suggested to me that much of what passes for the philosophical output of science is actually stale philosophy that plays only a decorative role in scientific research. I thank Joseph Agassi, Carlos F. Bunge, Eric R. Bunge, Sylvia A. Bunge, Marta C. Bunge, Carmen Dragonetti, Bernard Dubrovsky, Michael Carey, Richard L. Hall, Martin Monner, Michael Matthews, the late Robert K. Merton, Greg Michelson, Martin Morgenstern, Stors McCall, Andreas Pickel, Hector Vucedic, Sergio B. Volkan, and Per-Olof Wikström for interesting questions, insightful remarks, sharp criticisms, or pertinent information. I am particularly indebted to Martin Monner, who read the whole of an earlier version and lodged many complaints, many of which I listened to. I am also grateful to John St. James for his patient copy editing, and to Leonard Husband and Francis Mundy for their diligent editing. The central theme of this book, namely, the search for reality, may be introduced through 3 short stories. The first is this. The sun sunk beyond the horizon, and all animal life seemed to come to a standstill. The little girl asked, "Did the sun really sink, and did all the animals die?" Teacher: "No, it just looked that way. What really happened was that the earth spun eastward until we were no longer facing the sun. It also happened that, because of the ensuing darkness, the diurnal animals went to sleep. In sum, sundown, just like sunrise, are only in the eyes of the beholder. The sun takes no notice of the earth's spin." Incidentally, did you know that the Aztecs believed that they had to kill some people to ensure that the gods would make the sun rise the next day? And do you think they would have abandoned this custom had they learned the truth? Wait. Before answering, let me warn you that some famous people still believe that all we can know is the way things look, never the ways things really are. The second story concerns a little boy who, one summer night, tried to catch a firefly between flashes. One may conjecture that, not having heard of Berkeley, Kant, Bohr, or the logical positivists, the child assumed that the insect kept moving between flashes. And, being not only a spontaneous realist but also curious, the child chased the insect with a flashlight, to try and spot it between flashes. Eventually he caught the bug and took it to school. The teacher told him that the intermittent light emission is involved in the firefly's mating ritual. And his uncle the chemist tried to explain to him the chemical reaction involving an enzyme that emits light. But of course not even the brightest 5th grader knows enough organic chemistry to understand that reaction. The third and last story is a realistic one, and it concerns the ambiguities and deceptions of social life. When the Nazis seized power, Max Planck, the grandfather of quantum physics, kept his job as the top German science administrator. Once, during a state ceremony, he was seen to timidly raise his right arm in the Nazi salute, Heilbronn 1986. True, Planck did not join the Nazi party, and he never denounced Jewish science. Moreover, he protected what little good science had been left, and defended both rationality and realism. Yet again, Planck rebuked Einstein for resigning his membership in the Prussian Academy of Sciences, and during the war he lectured around the country and in the occupied territories. So, he legitimated the regime by his mere presence in visible places. In sum, Planck, along with millions of fellow Germans, looked nearly black outside, but seems to have been nearly white inside. What color was he then actually, in fact, really? Or is this an ill-conceived question, since color, far from being a primary property, is in the eye of the beholder? At all events, we all know that appearance, simulation and dissimulation, as well as misperception and self-deception, are part of social reality. The preceding stories involve not only the ontological concepts of appearance and reality, but also an ill-disguised preference for scientific realism over phenomenalism. The first two stories also involve the methodological concepts of observation, assumption, reality check, and explanation by way of unveiling mechanisms. All of this is quite normal for smart children, craftsmen, scientists, and technologists. It takes a philosopher with his head in the clouds to hold that observation is unnecessary, Plato, Leibniz, Hegel, that there is nothing behind phenomena, Berkeley, Hume, Kant, Renouvier, that no hypotheses should ever be framed, Bacon, Comte, Mach, that guesses need not be checked, Bergson, Husserl, Goodman, or that explaining is just subsuming particulars under generalities, Mill, Popper, Hempel. It may be objected that I am poised to beat a dead horse, since most philosophers are at least as smart as the little boy who chased fireflies. However, such optimism is unwarranted, since anti-realism is still alive and well in academia. The following random sample of highly regarded contemporary views should show why. 1. In a much-quoted book, Bas van Frassen, 1980, tells us that the aim of science is to save the phenomena appearances rather than to account for an independently existing reality, something he places in metaphysical baggage to be jettisoned. Likewise David Lewis, 1986, an influential philosopher famous for assuming a plurality of real worlds, adopted Hume's view that there are neither objective connections nor laws proper, that the universe is a vast mosaic of disjointed phenomena. 2. Nelson Goodman's, 1978, fantasies about world-making, and in particular star-making, have been commented on respectfully and profusely, if at times critically, as if they were important contributions to knowledge and as if Berkeley had written in vain. 3. Most textbooks on quantum mechanics still pay lip service to the Bohr-Heisenberg or Copenhagen interpretation, according to which that theory refers only to facts under experimental control, in particular phenomena. As the physicist d'Espagnat, 1981, 22, said approvingly, one of the consequences of this view is that it destroyed what Copernicus had accomplished. It has put man back at the center of his own representation of the universe, from which Copernicus had expelled him. 4. Most biologists, psychologists, and social scientists teach that every scientific project starts from some theory-free observation, that data alone drive research and exude hypotheses, and that theoretical speculation is dangerous. 5. The Nobel laureate Gerard Debreu, 1991, claimed that the moment he axiomatized the theory of general economic equilibrium, this theory became part of mathematics, and is therefore impregnable to empirical data. The practical moral is obvious: economists must be trusted just as much as Euclid, regardless of economic reality. 6. The Bayesian statisticians and philosophers believe that all probability assignments must be subjective, so that none of them can be said to be either true or false. In fact, they hold that a probability value is a measure of the strength of someone's belief in something, rather than either a pure number or the measure of real possibility, such as the probability an atom will jump between given states within the next minute, whether or not it is being observed. 7. Most mathematicians believe Plato's thesis that the mathematical objects, such as numbers, sets, functions, and the statements about them, exist on their own and are therefore discovered rather than invented. 8. The social constructivist relativists deny the difference between thing and idea, fact and fiction, law and convention, research and conversation, empirical test and horse trading with colleagues. Likewise, the hermeneuticists claim that everything social is a text or like a text to be interpreted rather than a fact to be observed, described, explained, or altered. Obviously, neither school has any use for the dual concepts of truth and error, without which scientific research would be pointless. 9. Influenced by ideas of Ludwig Wittgenstein, the Vienna Circle rejected both the thesis of the reality of the external world and the thesis of its irreality as pseudo-statements, Carnap 1950b, 32-3. Yet, Wittgenstein is as influential as ever. 10. The radical relativists, fictionists, and conventionalists deny the existence of objective and therefore cross-cultural truths, such as those of mathematics, chemistry, and genetics. The very idea of an objective test is alien to them, which allows them to state whatever they please. The preceding sample should convince anyone that ontology and epistemology are going through a crisis. See Bunge 2001. What can one do in a crisis but either flee or fight? Upon despairing of solving certain crucial philosophical problems, the famous Harvard philosopher Hilary Putnam, 1990, 118, wrote, Time has come for a moratorium on ontology and a moratorium on epistemology. Dewey, Wittgenstein, and Heidegger concurred, Rorty 1979, 6. I prefer to keep on doing ontology and epistemology, because I believe that a philosophy without them is like a body with neither trunk nor head. Philosophy can and must be criticized and reconstructed unceasingly. Criticism is never enough, for we need constructive ideas in addition to weeding out falsities if we care for truth. Here are some of the theses to be expanded upon and defended in this book. 1. Scientific realism, the thesis that the universe exists on its own, can be explored, and is best explored scientifically, is not just one epistemology among many, it is the one presupposed and confirmed by scientific and technological research. By contrast, phenomenalism, that is, the view that the world is a sum of appearances, Kant 1787, B 724, or at least that only appearances can be known, is shallow and false. In fact, light emission, chemical reactions, infections, biological evolution, intentions, political tricks, and almost everything else, occur even though they are imperceptible. It is therefore no accident that Galileo and Descartes, two of the founders of modern science, emphasized the difference between primary and secondary properties, and proposed that science should focus on the former. Ironically, the phenomenalists, notably Hume, Kant, and the positivists and logical positivists, in their eagerness to refute supernaturalism and speculative metaphysics, would have killed science as well had they been taken seriously. 2. Although appearances are only skin deep, they are part of reality rather than its opposite, for they occur in the subject's brain, which is part of the total world. Inner experiences, qualia, such as feeling cold, seeing blue, hearing a creak, or smelling mint, are not basic but derived, they are processes in the central nervous system, not in the external world. Yet they are not to be discarded, because they are real and moreover indispensable for animal life. 3. An intelligible, scientific, and useful phenomenology, like the one sketched one generation before Kant by the polymath Johann Heinrich Lambert, 1764, would explain the secondary, sensory, properties in terms of primary properties. As a matter of fact, this is one of the tasks that cognitive neuroscience is currently performing. It has begun to explain appearances in a scientific way and as brain processes. 4. To explain a fact is to exhibit the law-abiding mechanism, that caused it, as when blushing is explained as the last link in the chain stimulus perception conception activation of an emotion organ such as the amygdala stimulation of the motor strip in the brain cortex relaxation of facial muscles dilation of the capillaries that irrigate the cheeks. Because it overlooks mechanism, the so-called covering law model of scientific explanation, though not incorrect, is only partial, it just accounts for the logical aspect of explanation. 5. Causation and chance, though not manifest, are objective modes of becoming. And, though neither is reducible to the other, they are related to one another, as when an increase in gas pressure is explained as an increase in the frequency of the random molecular impacts on the walls of the gas container. 6. The sciences and technologies use the realist, often misnamed propensity, interpretation of probability, namely, as a measure of real possibility. By contrast, Bayesianism, which interprets probability as credence, is conceptually fuzzy and has no empirical support in psychology. And the realist interpretation of probability necessitates a broadening of determinism, to include probabilistic laws. 7. The inverse problems, such as inferring, guessing, axioms from theorems, causes from effects, and mechanisms from functions, have been sadly neglected in the philosophical literature, with the sole exception of the so-called Hume's problem, data hypothesis. Yet, they are far more challenging and rewarding than the corresponding direct problems. The most promising strategy for tackling inverse problems is to try and transform them into direct problems, as when Newton postulated his laws of motion to deduce the orbits of bodies. 8. Induction is neither everything nor nothing. It occurs in low-level, empirical, generalizations as well as in the confrontation of theoretical predictions with relevant data. This confrontation involves some statistical processing. But there is no such thing as probabilistic inductive logic, or probabilistic epistemology, because propositions, not being random items, cannot be assigned probabilities except arbitrarily, and also because hypothesizing is not a rule-directed activity but an art. 9. Scientific theories are seldom if ever contrasted directly with the relevant empirical data. One must first enrich them with indicators, such as fever as an indicator of infection, and GDP as an indicator of economic activity. Indicators are independently checked hypotheses that relate hypothetical variables to observables. To be reliable, the underlying mechanism must be unveiled. This is why ammeters and brain imaging devices are reliable, whereas crystal balls and dream almanacs are not. Yet indicators are seldom examined in the philosophical literature. 10. Although fiction is not fact, paradoxically we need some fictions, particularly mathematical ideas and highly idealized models, to describe, explain, and predict facts. This is not because the universe is mathematical, but because our brains invent or use refined and law-abiding fictions, not only for intellectual pleasure but also to construct conceptual models of reality. Hence, moderate mathematical fictionism, the view that, although mathematical objects have no independent existence, we may feign that they do. This restricted version of fictionism, unrelated to instrumentalism, is inconsistent with naive realism but compatible with scientific realism. The preceding theses may be compressed into Figure I.1. So much for the apéritif. Figure I.1m. A. Ontological perspective, phenomena, appearances, constitute but a small part of reality. Theorists are a part of reality, but the theories they construct are not in the outer world if conceived of in themselves, that is, apart from the processes of thinking and applying them. B. Epistemological perspective, reality can be understood and altered efficiently only through theories prompted and checked by phenomena. We deal with facts all the time, yet there is no consensus on the meaning of the very word fact, particularly since in ordinary language it is often confused with either datum or truth. This confusion is likely to stem from Sanskrit, whose word satya means both existent and true. So, there is room for puzzling. Are laws and rules facts? Are there general facts? Are social constructions, such as legal codes, facts? Is it a fact that 2 + 2 = 4? How do propositions relate to facts in the external world? And what did Wittgenstein, 1922, 1.13, mean when he wrote that he facts in logical space, are the world? Such puzzles about the meaning of the term fact are not just lexicographic quibbles, because the right way of dealing with an item X depends crucially on the nature of X. If X is in the outer world, we may have to act upon X, whereas if X is a construct, we may have to subject X to conceptual analysis. In this chapter we shall only deal with a few of the many problems centered on the concept of a fact, namely, some of those that relate to the central theme of the book. More on ontology and semantics in the author's treatise, 1974a, 1974b, 1977a, 1979a. More precisely, we shall examine briefly the concepts of thing, property, state, change of state, law and appearance, as well as the materialist and realist doctrines and their contraries. In dealing with facts we must start by examining the concept of a thing,
because a fact is anything involving a thing. This is why, as the great sociologist Durkheim, 1988-78, put it, every scientific object is a thing, save perhaps the mathematical objects. In a scientific worldview, then, the world is constituted by things. This was also the view of the ancient Greek and Indian atomists, the medieval nominalists, and the Enlightenment materialists. 1. 10. The statement that the world is the collection of things is hardly controversial. However, no word is more vague than thing. It is therefore advisable to try and elucidate it. Let us start with the broadest of all nouns, the neutral term object. It is generally admitted that objects can be either material, concrete, like birds and schools, or immaterial, abstract, like concepts and theories. Concrete objects are also called things or existents, and abstract objects ideal or constructs. Correspondingly, the properties of concrete objects, such as viscosity and productivity, may be said to be substantive, whereas those of ideal objects, such as consistency and transitivity, may be said to be formal. However, the thing/construct and substantive/formal distinctions may be taken to be methodological rather than ontological. This is because, in a non-Platonic philosophy, constructs are human creations, hence dependent on the concrete things called thinkers. Besides, whereas some constructs, such as those of deity, cloven night, and parallel universe, are wild fictions, others, such as the concepts of set and function, are tame fictions, and moreover indispensable to understand and handle concrete things. For instance, the natural kinds, such as the chemical and biological species, may be regarded as sets, and many properties of concrete things, such as speed and population, can be analyzed as functions. Thus, we face the paradox that we need fictions, of the tame kind, to account for real things, just as we may use wild fictions to create the illusion of escaping from reality. In short, fiction is the path to and from reality. More on fiction in Chapter 8. So far we have used the word thing as if it designated a clear and distinct idea, but it is not, since it is often confused with object. We must therefore attempt to define it with some precision. The traditional view is of course that of Descartes: a concrete thing, unlike an abstract one, is a residential extensa. But, while spatial extension applies to solid bodies, it does not to electrons, fields, biopopulations, families, corporations, and many other things. Neither of them has a precise position, volume, and shape. Besides, in a relational theory of physical space, the latter is the structure of the totality of things. As for the vulgar characterization of material in terms of shape, mass, and solidity, it is even less adequate, because solids are exceptional in the universe. I submit that Plato got it right in this case. According to him, whereas ideas are immutable, when considered in themselves, material entities are corruptible, changeable. But of course he was mistaken in restricting changeability to the sublunary world. Change is universal. In other words, I submit that mutability is the one property shared by all concrete things, whether natural or artificial, physical or chemical, biological or social, perceptible or imperceptible. In other words, I assume postulate 1.1 for all x is material equals x is changeable. 11. Note that materiality is not predicated exclusively of things or entities, properties too qualify. For instance, position in spacetime, density, and productivity may be said to be material properties because they are properties of concrete objects. Likewise, relations, whether binding such as attraction or non-binding such as above, can be said to be material if they hold among material objects. However, properties and relations can be material only derivatively, that is, by virtue of the materiality of the things involved. There are neither properties nor relations in themselves, except by abstraction. The same holds for events and processes. The changes of these kinds may be said to be material if they occur in material things. Thus, heat propagation, metabolism, and ideation qualify as material since they are processes in material things. By contrast, logical consistency, commutativity, and differentiability can only be predicated of mathematical objects. Likewise, omnipotence, omnipresence, and omniscience apply exclusively to certain gods. However, whereas an entity is either material or ideal, some properties are possessed by entities of both kinds. Thus, finiteness and countability apply to abstract sets as well as to collections of pebbles, and continuity is a property of both certain functions and the trajectories of bodies. In other words, the set of material properties overlaps partially with that of formal properties. Equivalently, whereas the domains of certain predicates are homogeneous, those of other predicates consist in unions of sets of material and ideal objects. Incidentally, Joseph Dietzgen, 1906, 300 ff., the tanner and self-taught philosopher highly praised by Marx, held that thought is material. Lenin, 1947, 251, criticized this statement, arguing that, if it were true, then there would be no difference between materialism and idealism. This argument may have originated in Lenin's conflation of materiality with reality, since he defined material as whatever exists independently of any subject. He could not accept that thinking, which is private, is also material. Lenin's criticism of Dietzgen seems to have been the root of the dualist philosophy of mind official throughout the Soviet Empire. This amazing deviation from the materialist tradition was added to the further dualistic division of every society into its material infrastructure and its ideal superstructure previously postulated by Marx and Engels, example Engels 1954. Such double dualism might have been avoided if Marxists had bothered to think clearly instead of imitating Hegel's convoluted prose. They might then have realized that it is possible to distinguish thought processes and cultural processes from others without dematerializing them. However, let us go back to the peculiarity shared by all material entities. Like all universals, changeability or materiality can be conceived of in an extensional way. That is, we can define matter as the set of all material objects present, past, and future. Definition 1.1 Matter equals XX is material equals XX is changeable, where denotes the collection of objects of all kinds. Being a collection, matter, the concept, is immaterial. So are hydrogen, the collection of all hydrogen molecules, and humankind, the set of all humans. More on species in Chapter 9. Since the technical word for changeability is energy, formula 1 can be rewritten as postulate 1.2 for all x, x is material equals x has energy. Depending on the scale, which is conventional, an energy value may be positive, negative, or null. Besides, there are many kinds of energy, mechanical and thermal, kinetic and potential, electric and magnetic, nuclear and atomic, gravitational, chemical, elastic, and so on. This variety is such that it overflows every single chapter of physics. Indeed, physics does not define the general concept of energy. This is why Richard Feynman claimed that physics does not know what energy is. Which suggests that the general concept of energy, like the general concepts of thing, fact, and law, is ontological, Bunge 2000a. To repeat, energy is not just a property among many. Energy is the universal property, the universal par excellence. Moreover, energy is a universal in re, it inheres in things instead of being either ante-rem, prior to them, or post-rem, after them. My view is then neither idealist, in particular Platonist, nor nominalist, vulgar materialist. In the Middle Ages it would have been characterized as immanentist realism. More in Chapter 9. Parenthetically, energy, the property of all things, must not be confused with the various concepts, predicates, used in science and technology to represent it on the conceptual plane. We shall come back to the property-predicate distinction in Section 4. Because energy is a universal, it is just as insufficient as being, existent, or thing to characterize any particular thing. To this end, further properties are needed. In fact, every time we describe a particular thing we list some of its properties, as when characterizing a certain fruit as round, juicy, and of color orange when illuminated by white light. Moreover, properties do not conjoin haphazardly. Thus, in the preceding example, roundness and juiciness are concomitant with solidity, liquid and gaseous fruits are impossible. Likewise, democracy works best with equity and liberty, and not at all with extreme inequality and tyranny. In sum, properties cluster. More precisely, every property conjoins with some other properties. In other words, properties come in bundles or systems. However, the properties in a property cluster are not all on a par, whereas some of them are essential, others are accidental, whereas some are basic. Others are derived, or dependent upon basic properties, and whereas some properties are primary, or inherent in things, others are secondary, or dependent upon some sentient being. For example, having cylinders and a transmission are essential to a standard car, whereas its color and price are both accidental and secondary, because they can be altered without the thing ceasing to be a car. In other words, the accidental properties of a thing can, unlike its essential properties, be added or subtracted one by one. Again, the essential properties of a thing constitute a system, they come in bundles. Equivalently, every one of them is related to at least one other property of this kind. Hence, any change in one of them is bound to alter some of the others. Another philosophically interesting distinction is that between invariant, or absolute, and non-invariant, or relative, properties. The former are the same in, relative to, all reference frames, such as laboratories and star constellations. Therefore these properties are also the same for all observers moving relative to one another. Paradigmatic examples are real existence, the electric charge and entropy of a physical thing, and the composition and structure of a system. Other properties, such as mass and frequency, as well as position and velocity, depend on the reference system. For example, the mass of a body increases with its velocity, and the frequency of light decreases as its source moves away from the reference frame, Doppler effect. Frame dependence is objective, it occurs whether or not the reference frame in question is inhabited by a sentient being. Moreover, although some quantitative properties are frame dependent, their corresponding qualities are not. Thus, being localized, in motion, or massive, and having an age are absolute. Only having certain coordinates, moving with a given speed, possessing a certain mass, and being so many years old, are relative, but the relation in question is to a physical reference frame, not to an observer. In short, relativity does not involve subjectivity. Does having different velocities relative to different frames of reference count as so many facts or as a single fact? If we decide on the former, we will have to put up with an unnecessary multiplication of facts. It seems more reasonable to relativize fact to reference frame and say, for instance, that my walking around the block is a single fact with as many projections as reference frames, by analogy with the shades projected by a body on different surfaces by different light beams. On the other hand, the secondary properties, such as taste, smell, color, and heat, are subject dependent. The world in itself is neither colored nor hot, and it neither tastes nor smells. Another obvious example is social order, which is perceived differently by different people, even if some of its features, such as the distribution of wealth and the degree of citizen participation, are poor. 14. Factly objective. Likewise, values are subject dependent, even though some of them have objective roots. For example, beauty is in the eye of the beholder, but nutritive power and peace are not. As with properties, so with their changes. Whereas some changes, such as displacement and mixing, are quantitative, others, like the chemical combination and the formation of new organizations, are qualitative. Equivalently, these changes involve the emergence, gain,
or the submergence, loss, of certain properties. Regrettably, most dictionaries misinform us that emergence means impossibility of explaining qualitative novelty in terms of the constituents of the whole in question and their bonds. In fact, this is only the irrationalist, in particular holist and intuitionist, version of the emergence doctrine. Such epistemic pessimism is certainly not countenanced by the physicist who investigates phase transitions, such as from liquid to solid, and from magnetic to non-magnetic, the chemist who studies the formation or dissociation of molecules, the neuroscientist who wishes to understand the genesis and death of neurons, or the historian intent on explaining the emergence or dissolution of social systems and the norms inherent in them. All such cases point to the promise of emergentism as the corrective and complement, not necessarily the enemy, of reductionism, Bunge 2003a. Now, the laws of nature and the social norms are invariant relations among properties and their changes. Here, invariant means both constant in time and independent of any particular choice of reference frame. Strictly speaking, only the basic laws are the same relative to all reference frames of some kind, see Bunge 1967b. Hence, to say that the essential properties of anything come in bundles, or constitute systems, amounts to saying that every one of them is lawfully related to other properties. And, since laws conjoin properties, they are, complex, properties themselves. It is therefore to be expected that they will be formalized by more or less complex propositions, such as the postulates of electrodynamics, which relate such properties of the electromagnetic field as its electric and magnetic intensities, and the intensity of the electric charges and currents that accompany the said field. Because properties cluster, it has sometimes been suggested that things are nothing but bundles of properties. This view, reminiscent of Plato's theory of ideas, or forms, is mistaken for two reasons. The first is that, as Aristotle argued against his teacher, there are no properties without substrata. Every property is a feature, trait, or aspect of some object or other. This is why we measure or calculate the metabolic rate of organisms, the population densities of cities, and so on. And this is why energetism, the doctrine that all is energy, and nothing material, is false. 15. The same holds for informationism, or the thesis that the world is the maximal computer, that every concrete thing is made from bits, Wheeler 1996. Indeed, all the information processing systems, such as computers, are material. By contrast, bits, the amount of information content, are properties of signals or symbols, not entities. This is why computer hardware is designed with the help of physics, not information theory. Hence Wheeler's cute maxim, it from bit, is every bit as wrong as both traditional, individualist, subjectivism, it from me, and social constructivism, it from us. More in Deutsch 2004. A second reason that the bundle theory of things is false is that it suggests writing formulas such as PP, Q, where P and Q stand for two, substantive, properties, such as price and quantity. This formula is not well formed because the set P, Q has only mathematical properties, such as that of having two elements. Sets can have no substantive properties, such as that of being able to move. The usual way of characterizing a particular thing is to list its salient properties, such as sex, age, and occupation in the case of persons. Actually, what we list when individuating or identifying an individual is property instances or tropes, such as 30 years of age. This procedure is at variance with Quine's celebrated formula no entity without identity. This formula is suitable for sets and for the mathematical objects constructed with sets. By virtue of the axiom of extensionality, two sets are identical if and only if they have the same members. But Quine's formula is irrelevant to the study and handling of material objects, for no two such things can be exactly identical, although the elementary particles may be exchangeable. This result should not be surprising because logic, even when enriched with set theory, is insufficient to build ontology, since it does not describe the world. In sum,
a reasonable ontology must start with the concepts of thing and its properties. And if it is to be compatible with modern science and technology, that ontology will conceive of concrete things as changeable. Consequently, it will be able to give a reasonable account of facts, such as a thing being in a given state or going over to a different state. 2. Fact. In ordinary language the word fact denotes pretty well anything. Even some famous philosophers have used it carelessly. For instance, the idealist Husserl proposed the slogan Zurück zu den Sachen, that is, back to facts. But, since Husserl, 1931, bracketed out the external world, and regarded realism as absurd, presumably what he meant by facts were phenomena such as 16. Sights and smells, rather than either physical objects such as atoms, or social ones such as families. In any event, given the ambiguity of the word fact, it will be convenient to try and elucidate its meaning. Suppose this cat is in fact, actually, really, on that mat. That the cat is on that mat is a fact that involves at least three concrete, or material, things: the cat, its mat, and the floor underneath. If the environment does not change appreciably during the time of interest, or if its changes are of no significant consequence to cat, mat, or floor, we need not refer to it explicitly. A moment later the cat gets up and walks away. The first fact, that the cat is on the mat, pivots on the state of the cat, whereas the second fact revolves around the animal's motion, which is a particular change of state. We call such changes events if swift, processes if protracted. In sum, we ordinarily distinguish facts of two kinds: static fact equals thing, s, in a given state. Kinetic fact equals change, s, of state of thing, s. Note that in both cases the facts in question consist in either states or changes of state of concrete things. No such things, no facts. Thus, the analysis of any fact should start by identifying the thing, s, involved, such as reagents in the case of a chemical reaction, and brains in that of a mental process. What holds for empirical analyses also holds for conceptual, in particular semantic, analyses. This analysis starts by identifying the referents of the constructs in question. That is, we begin by stating what is being talked about. For example, the referents of the statement buildings are taller than people are buildings and people. And the statement describes a fact, or rather a whole collection of facts, even though the relation taller than is non-binding. In general, the statement that thing B stands in our relation to thing C, or RBC for short, describes a fact if the statement is true. Neither the relation nor the corresponding relata are independently real. What is real is the fact that RBC. To paraphrase Hegel, in cases like this, das Wirkliche ist das Ganz, the whole is real. This is not to be taken as a profession of holistic faith but as a warning against the temptation of reifying relations and unrelated individuals. These are only analytical devices. However, the fact-thing distinction is only an analytical device since, as stated above, in reality there are neither states nor changes of state in themselves. Nor are there things that fail to be in some state or other, or that undergo no changes. The fact that many a thing, such as a plucked guitar string or an electron, may be in a superposition of elementary states, such as harmonics and eigenstates respectively, constitutes no counterexample. Whether simple or complex, all states are states of concrete things. Likewise, the distinction between static and kinetic facts is rather coarse. 17. Because nothing stays forever in the same state. For instance, the cat mentioned above undergoes thousands of chemical and physiological processes while sleeping on its mat, and the latter changes too as it interacts with the cat, the floor, and the air, as we find out when cleaning it. Another distinction that should not be confused with a dichotomy is that between natural and social facts, or between brute and institutional according to Searle, 1995, 27. True, there are purely natural facts, such as earthquakes, that happen independently of the state of society, and whether or not we perceive them. Likewise, there are purely social facts, such as economic downturns and crusades. All such facts are macrosocial. Moreover, they are brute in the sense that they are beyond the control of the individuals involved. But at the level of the individual there are only, a. natural facts, such as breathing and eating, and b. biosocial facts, such as walking on a public street and buying a newspaper. We can distinguish the biological from the social aspects of an individual action, but we must not detach them, because they come together, for the simple reason that everything social is the work of animals. Finally, the event/process distinction, though clear in ordinary knowledge, is not obvious in science. Here one attempts to analyze events into processes. In principle, even quantum jumps can be regarded as swift processes. In sum, a fact is the being of a concrete thing in a certain state, or changing from one state into another. There are neither states nor events in themselves for the simple reason that, by definition, every state, or state of affairs, is a state of something or other, and every event is a change in the state of a concrete individual. Therefore, Armstrong, 1997, notwithstanding, the concept of a state of affairs is not an independent category. We have known this since Aristotle criticized Plato for writing about movement in itself rather than about moving bodies. All of the preceding may suffice for everyday life and ordinary knowledge ontology, but it is too imprecise for science, technology, and scientific metaphysics. In these domains we need more precise concepts of state, event, and process. Now, the most exact and general analysis of these concepts is the one inherent in the state, or phase, space approach, familiar to natural scientists and engineers, example Bunge 1977a. It is the most general because, being stuff independent, it can be used in any discipline dealing with facts, from physics to ecology to sociology to ontology. However, the reader uninterested in formal matters may skip the balance of the present section, whereas the reader interested in learning more about it may wish to consult the appendix. To introduce the state-space approach, consider the simplest possible case, that of a thing with only two salient properties, such as position and moment. 18. TUM, blood pressure and heartbeat, population and GDP, or quantity and price. Call them P1 and P2, and represent these by mathematical functions f1 and f2 respectively, called state functions. For definiteness, these may be regarded as depending only on the time variable t. Next, form the ordered pair f, t, equals. This point may be pictured as the tip of a vector in a two-dimensional Cartesian space, namely, the Cartesian product of the codomains of f1 and f2. As time goes by, f, t, moves in this space, generating a trajectory that summarizes the history of the thing represented. This motion is constrained by the law, s, that relate f1 to f2. For example, if the thing is a linear oscillator, such as the tip of a pendulum, the abstract point in the state space represents a possible state. The state space is S equals f, t, t, where designates the real line. The corresponding lawful state space is the proper subset SL of S of all the points that satisfy the constraint energy equals constant. For each value of the energy, SL is an ellipse. That is, SL equals E, QP, equals constant. See Figure 1.1a. Figure 1.1b represents the possible states of an ecosystem constituted by two populations of organisms, one of which preys on the other. Caution, since the state space is abstract, so is every trajectory in it, it represents a process but not a trajectory in physical space. The generalization of the above to things with n properties, where n2 is immediate, SL equals F1, T, F2, T, Fn, T. In physics there are as many state spaces as reference frames. For instance, since things in a freely falling lift are weightless, weight cannot be taken to be a state variable relative to such a reference frame. The state spaces in quantum theory are those spanned by the A, B, and 2. Figure 1.1 m, A, the state, or phase, space for a classical linear oscillator with position q and momentum p. Each ellipse represents a possible motion with constant energy. B, the possible states of a system composed of a prey in numbers n1 and a predator in numbers n2. n1. Q. P. 19. State functions, which are not built property by property but in one piece. Each of these abstract, Hilbert, spaces is infinite dimensional. However, the basic idea is the same. A state space is the set of all the really possible, that is, lawful, states of a material entity, particle, field, ecosystem, business, national economy, or what have you. The description of really possible facts, states, events, and processes, in terms of state spaces renders both modal logic and possible worlds ontology redundant. The reason is that neither of these involves the central notion of a law. See details in Bunge 1977a, 2003a. The following table summarizes the preceding analysis. Ontological item conceptual counterpart. Thing model thing. Property attribute, NARY predicate, state space state point in state space event ordered couple of points in state space process trajectory in lawful state space law, rule, or norm restriction on state space. Note the logical order. We start with things because they are the bearers of properties, we then go to states and their changes, and end up in patterns of being and becoming, laws. This is the order of analysis, but what we find in reality are things with all their properties, and changing in lawful ways. And we model them in terms of attributes, predicates, such as functions, or state variables, that define a state space. Note also that we have avoided the common confusion between fact and datum, a confusion encouraged by ordinary language. An empirical datum is not a fact but a proposition reporting on some fact, for instance, that your age is such and such. Another difference between facts and data is this. Whereas facts obey laws of nature or social norms, data, being propositions, abide by logic. There are negative, disjunctive, and general propositions, but not negative, disjunctive, or general facts. For example, that the hound of the Baskervilles did not bark that fateful night is not a negative fact but a proposition. Whatever fails to occur is not a fact. Likewise, a hole in a chunk of cheese is not a piece of negative cheese. And that all adult dogs bark is an empirical generalization, not a general fact. All facts are singular and positive. Because data are propositions, they can involve theoretical concepts, that is, they can be theory-laden. This is the case with all the data occurring in scientific reports, such as the data concerning specific weights, DNA sequences, and income inequalities. A ready indicator of theory dependence is 20. The occurrence of abstract nouns. But of course the facts reported are not theory-laden. Moreover, even the most sophisticated scientific data result not only from procedures designed with the help of theories, but also from theory-free observations, such as those of a yellow glow, an instrument pointer, and a trace on a photographic plate. The preceding clarification is intended to refute the rather popular thesis that there is no distinction between observational and theoretical terms because all observations would be colored by theories. Actually, only some scientific observations are theory-laden, and even these must be completed with theory-free observations, such as that of the position of a pointer reading. Even Einstein, 1958, 62, the arch-theorist and anti-positivist, emphasized the need to connect the theoretical concepts with the primary concepts, that is, those that are directly and intuitively connected with typical complexes of sense experience. 3. The world, the totality of facts or the maximal thing. Astronomers equate the universe with the system of all things. By contrast, at the start of his Tractatus, Wittgenstein, 1922, famously wrote, "The world is the totality of facts, not of things." 1.1. Regrettably, he did not bother to clarify the key terms fact and totality, as a consequence of which he soon fell into circularity. Thus, he tells us that an atomic simple fact is a combination of objects, entities, things. 2.01, only to add, it is essential to a thing that it can be a constituent part of an atomic fact. 2.011. So, a fact is a combination of things, but in turn a thing is a part of a fact. And nowhere does Wittgenstein offer illustrations to facilitate understanding and show that his cogitations are useful to analyze scientific problems. Though still widely discussed in the philosophical literature, and recently updated by Armstrong, 1997, Wittgenstein's many-ontology is wrong for the following reasons. 1. It is not clear how the ambiguous word totality, Gesamtheit, is to be read in the expression totality of facts, whether as whole, system, or as collection, set. The former interpretation does not sound right, because facts do not assemble, only things do. And if the second interpretation, set, is adopted, it turns out that the universe is a conceptual item, not a concrete thing. This may be fine in an idealist ontology but is wrong elsewhere, if only because physical cosmology treats the world, universe, as a concrete and therefore changing thing, not as an idea. The same holds of course for any materialist ontology. Two things can interact, whereas facts may not. For instance, the fact that your 21 computer lies on its table does not interact with you. But you, your computer, and its table, things all of them, interact in various ways. Another example, the fact that your watch shows that it is noon does not interact with anything. But your perceiving it is an event that may stimulate you to go out for lunch. All these are processes going on in you, your watch, your office, your street, your eatery, and their surroundings, things, not facts, all of them. 3. All of the law statements and social norms refer to, things, such as dogs and nations, not facts, such as barking and trading. For example, cosmology is about stars and other celestial objects. But, of course, everything is in some state, a fact, and it may jump to another state, another fact. No things, no facts. If Newton's laws of motion did not refer to bodies, we could not use them to describe a fact such that the Earth is currently at such and such a distance from the Sun, or the process that a certain meteorite is moving dangerously close towards our planet. For the world is a system of things because every one of its component things interacts with some other things. If the world were a heap of facts, or states of affairs, it would not constitute a system, because it would not be held together by interactions. However, it is not a question of opting between two ontologies, one of things and another of facts. We only need a single ontology of things involved in facts, or facting things, or, what is the same, an ontology of facts involving things, or thinged facts. However, for the sake of logic we must start with things. We need the concept of a thing before we can form the idea of a state of a thing. This is why mereology, which is about things, is basic to ontology. Mereology is the theory of the part, whole relation and of the physical addition operation, as in the population of territory A plus territory B equals the sum of the partial populations. 5. The view that the world is a heap of facts might have been accepted by Berkeley, Hume, and Kant, provided fact were restricted to phenomenon or appearance. But, because appearances do not assemble through objective and lawful connections, such a heap would not constitute a world or system. However, appearances deserve a separate section. In sum, the world is not the totality of facts but that of things. And all things are changeable, and everything is related to some other things. 4. Enter the knower. So far the sentient being, or knowing and acting subject, has not appeared. The moment we decide to include interests and points of view in our consider 22 ations, we will have to add another 3 categories to those of thing and fact. These are the concepts of phenomenon, appearance, construct, such as concepts and propositions, and intention. The subject has got to be included in a comprehensive ontology, not least in an objectivist and materialist one. This is because, whereas some facts are perceptible, others are not. Thus, car collisions, unlike atomic collisions, can be experienced. And if perceptible, a fact may appear differently to different observers, because perception depends not only on external stimuli but also on the subject's knowledge, attention, and expectations. That is, one and the same external fact may elicit different appearances or phenomena, or none. Much the same holds, mutatis mutandis, for our conceptual models of facts and for our plans of action. This is not to endorse relativism, because it comes with an important rider: appearances can be deceiving, conceptual models inaccurate, and plans unfeasible or unfair. Hence, all subjective, subject-centered, accounts and decisions must be regarded as, at best, preliminary sketches to be perfected or rejected. At all events, our world pictures may have components of all three kinds: perceptual, conceptual, and praxeological, action-theoretical. This is because there are three gates to the outer world: perception, conception, and action. However, ordinarily only one or two of them need be opened. Combinations of all three, as in building a house according to a blueprint, are the exception. We may contemplate a landscape without forming either a conceptual model of it or a plan to act upon it. And we may build a theoretical model of an imperceptible thing, such as an invisible extrasolar planet, on which we cannot act. In other words, perceptible things elicit appearances. Interesting things, whether perceptible or imperceptible, are understood through conceptual models, and useful things call for plans of action. Note the subject-related concepts in the foregoing: perceptible, interesting, and valuable. They bridge the subject to the object, the knower to the known, the actor to the thing he wishes to act upon, in short, the inner world to the outer one. To continue in this metaphorical vein, we add that action, in particular work, science, technology, art, and politics, builds those bridges. Thus, a single thing may elicit several appearances, various conceptual models of it, or several plans of action for it, depending on the subject's abilities and interests. That is, we distinguish, with Kant, the thing in itself from the various concomitant things for us, but we do not follow Kant in claiming that the former is unknowable, let alone non-existent. See Figure 1.2. This is not all. The naive observer may be joined or displaced by the scientist, technologist, or philosopher intent on analyzing or evaluating the things for us that accompany some things in themselves. See Figure 1.3. 23. Illusions constitute a particularly interesting case in point, and one that has drawn the interest of psychologists, neuroscientists, and artists. See, example Gregory and Gombrich, eds 1973. They are facts, but they occur in the brain rather than in the external world. Consider, for instance, the out-of-body experiences that spiritualists have invoked as evidence for the separability of mind from body. These illusions can be induced at will by electrical stimulation of the brain's right angular gyrus. The subject reports that she sees herself from above, or with her legs becoming shorter, or moving quickly. See, example blank ETAL 2002. The trips of drug addicts are similar, they are just brain tricks. A more sophisticated case of the distinction in question is that between property and predicate. In principle, every property of a thing may be conceptualized in alternative ways. For instance, an electromagnetic field in a vacuum may be represented either by an intensity tensor with 6 components, or by a vector potential with 4 components. Neither representation is more correct. W1 W2 Wm A, B, C, D, E, F U U1 U2 on F W1 W2 WP M1 M2 MG UU fiction. Figure 1.2 M, A,
various appearances wi of a thing u, b, several things uj appear the same to the untrained observer. C, several phenomena but no discernible underlying thing, as in illusions. D, alternative models mk of one and the same thing u, e, unknown thing, neither appearances nor models thereof, such as Spencer's unknowable. F, fiction, a construct with neither real nor phenomenal counterparts, such as the Cheshire Cat or the real line in mathematics. Ideas about things for us analyses or evaluations of W or M. Things for us appearances W models M. Thing in itself real and knowable thing. Figure 1.3 M. The things for us, appearances and models, can be analyzed or evaluated, for truth, utility, beauty, etc. 24. Or realistic than the other, but each has its advantage, the first is closer to measurement, and the second is easier to calculate with. Which is the correct representation or formalization of a predicate representing a property of a concrete thing? I submit that predicates should be construed as functions, operators, or elements of an algebra, depending on the theory. Thus, in classical physics energies are construed as functions, and as operators in quantum physics, and spins are formalized as elements of an algebra, or as matrices. Take, for instance, age. It is a property of stars, rocks, cells, rock stars, social systems, and more. After measuring, computing, estimating, or guessing the age of a thing, we write the age of is so many time units, or a, u, equals t for short. This shows that a is a function of the form a, times uq plus, where stands for the set of aging things, u for the set of time units, and q plus for the set of positive fractions. The point of the preceding exercise is to emphasize that, whereas properties are possessed by things, predicates are rightly or wrongly attributed to them. It is not that attributes are necessarily subjective, on the contrary, in science and technology they are expected to be objective, but some of them may turn out to be mistaken. For example, we may mistake a test score for an intelligence measurement, or a stock market index for a measure of economic health. 5. Subject/object separability. Knowledge of matters of fact has traditionally been regarded as a particular case of the subject-object relation, namely, the relation between explorer and explored. In other words, empirical cognition involves a sentient being capable of detecting signals from an object of knowledge. For example, one can see a book provided the book reflects some light that ends up in one's retina. Thus, the acquisition of knowledge depends on the possibilities of a. Distinguishing the knower or subject from the knowable or object, and b. Using or establishing an interaction between subject and object and, preferably, altering that interaction at will, as in an experiment. The first condition, distinguishability, depends on separability for, if the two terms of the interaction are not separable, then it is not possible to ascertain what the contribution of either is. Indeed, if the constituents of the subject/object system were joined too tightly, the subject might think either that he is creator, idealism, or helpless creature, empiricism. In the first case he would not bother to check his ideas, whereas in the second he would not dare having any ideas beyond those suggested by his sensory experience. The problem of separability, at first sight trivial, is actually quite complex. 25. Newton's theory of universal gravitation showed that the universe is the maximal system, that every component of it interacts with every other constituent. The emergence of the Faraday-Maxwell electromagnetic field theory in the mid-19th century reinforced this view. This for two reasons, because it introduced a further kind of cement among things, and because a field acts as a unit, a disturbance at any point in it propagates throughout the entire field. However, it was also known, or rather assumed, that all bonds weaken with distance. This makes it possible to study nearly isolated systems, such as the solar system, light beams in a vacuum, and atoms at very low temperatures. In short, although the universe is a system, it can be analyzed into nearly self-contained parts.
and even when such parcelling is impossible, as in the case of an ecosystem, it is usually possible to single out a few salient factors, such as humidity and temperature, and regard the others as roughly constant background. The existence of tightly knit, entangled, concrete systems poses the problem of the reality of their constituents, particularly when the strength of their bonds does not decrease with their mutual distances. Before the experimental refutation of the Bell inequalities in the early 1980s, it was presupposed that if the components of a system are distant from one another, then they are separable into mutually independent systems. Since then we know that this is not so, that once a system, always a system. Such entanglement is often said to refute the postulate of local reality. What actually happens is that the constituents of a real system are real but not independently so. What occurs in, at, or to one of them affects the state of the other, even if they are in a remote place. This holds at all scales, not only for atoms and photons. Thus, babies are real even though they are inseparable from their caregivers. In short, non-locality does not imply irreality, it only implies that reality does not satisfy classical physics, see Bunge 1979a. The emergence of quantum mechanics seemed to have changed all this, in showing that the constituents of a microphysical system are entangled, hence inseparable, unless strongly disturbed by the environment. Luckily for us, however, such entanglement does not hold for sentient beings, both because the things in question are macrophysical, and because they interact strongly with their environment. Thus, the popular claim that the knowing subject and the microphysical objects he studies constitute a sealed unit is false. Consequently, quantum physics does not threaten objectivity. It is still true that the world is made up of protons, photons, and the like, whether we act upon them or not. All the same, we are faced with this dilemma: no subject-object interaction. 26. No knowledge, but the interaction must not be so strong as to lead to confusing the two terms of the interaction. More precisely, this interaction must be such that the subject receives a clear signal, such that the signal-object action is far weaker than the object-subject reaction. The fulfillment of this condition depends critically upon the experimenter's competence and ingenuity. His equipment may involve shielding plates, vacuum installations, micromanipulators, and other contrivances designed to avoid disturbing the object without blocking the latter's signals. 6. Materialism. Philosophical materialists and idealists have been fighting each other for more than 2 millennia. Whereas idealists like Plato assert the independent existence of ideas, materialists and Aristotelians deny it. Moreover, idealists either deny the independent existence of things outside the mind, the case of Berkeley, or, like Plato and Hegel, they admit that there are concrete things, but all of them deriving from ideas or ruled by them. This strife has been so bitter that philosophical materialism has been ignored or vilified as crass or even immoral, even in university teaching. Consequently, this ontology has been generally ignored, misunderstood, or demonized. In particular, materialism is still widely identified with the physicalism of the Greek atomists, the amoralism of some of their Indian contemporaries, the distrust of ideas inherent in medieval nominalism, Nietzsche's vulgar and brutal materialism, or the genetic reductionism of the socio-biologists. In sum, it is seldom recognized that there is a vast family of materialist doctrines. But of course all of them share the principles that the world is constituted exclusively by concrete or material entities, and that thoughts are brain processes. However, the materialism/idealism strife is partly a matter of definition, because there is no consensus on the meanings of the terms material and ideal or their respective synonyms, concrete and conceptual. For example, some materialists, such as Steven Weinberg, 1992, 3, claim that matter has lost its central role in physics, because they stick to the traditional definition of material as something characterized by mass, or inertia, as if photons, which are massless, were immaterial. Others, notably the upholders of the computationist, or information processing, philosophy of mind and ontology, claim that stuff does not matter, that all there is are bits and algorithms to process them. See, example Barrow, Davies, and Harper 2004. As will be recalled from section 1, I submit that whatever is capable of changing in a lawful manner, from electron and gravitational field to person and society, is material. And, since being changeable is the same as possessing. 27. Energy, the predicate is material, turns out to be coextensive, though not co-intensive, with has energy. By contrast, unchangeable items, such as sets, numbers, and functions, are ideal, because they possess no energy. Thus, since electromagnetic fields have energy and obey physical laws, they are material even though they are massless and subtle rather than solid. Contrariwise, a theory of such fields, that is, an electrodynamics, is immaterial because it has no energy, even though it can be altered by physicists. The theory, like any other construct, is a conceptual, or ideal, object. The materialist thesis is not just that there are material objects, but that the world contains only material things. More precisely, a materialist ontology includes the following two basic assumptions. Postulate 1.2 Every object is either material or conceptual, and none is both. Postulate 1.3 All the constituents of the world, or universe, are material. A corollary to the first postulate is that, contrary to the hylomorphism attributed to Thomas Aquinas, there are no compounds of matter and forms, ideas. Given our broad concept of matter, the second postulate is not physicalist. It does not exclude such superphysical material things as organisms and social systems, all of which are characterized by emergent properties. In other words, this theory eschews radical reductionism. This is why it may be named emergentist materialism. See, example Bunge 1977a, 2003a. This version of materialism does not eliminate the mental, it just denies the autonomous existence of ideas. Nor does it outlaw all fictions. It only locates the mind in the brain, and tries to show why sometimes we need fictions, particularly mathematical ideas, to understand facts. More on fictions in Chapter 8. Moreover, emergentist materialism blends easily with realism to constitute what may be called hylorealism. However, before praising realism we must characterize reality. 7. Reality. We have not defined material as whatever exists independently of any minds, for this is what real means. More precisely, we propose the following, definition 1.1. Real things are those that exist independently of any subject. Of course, the objective idealists such as Plato, Leibniz, Hegel, Bolzano, and Dilthey have claimed that ideas exist objectively, not only in the privacy of human minds. But they have not bothered to substantiate this hypothesis. Moreover, it is empirically untestable, because the only way we can check whether an object exists really is by watching its physical actions, but, of course, ideal objects cannot exert such actions. 28. In turn, reality may be defined either as the set of all real things, in which case reality is unreal, or as the maximal real thing, the one constituted by all things. In the first case it turns out that reality, being a set, is unreal. Since this is not the normal usage of the term, we shall opt for equating reality with the physical, or mereological, sum of all things, that is, the universe. The term exist that occurs in the above definition is ambiguous, for existence may be either concrete, material, or abstract, ideal. Modern logicians, from Russell to Quine and beyond, have claimed that this imprecision is remedied by using the so-called existential quantifier. For example, there are prime numbers would be symbolized x, x is a prime number, dot. This device certainly works in mathematics, which deals exclusively with ideal, or abstract, or conceptual, objects. But it fails wherever ideal and material objects are referred to side by side,
as is so often the case in ordinary knowledge, science, and religion. For instance, an atheist has no problem with the statement that some angels are guardian angels, so long as the real existence of such supernatural beings is not stated separately. He prefers to add the explicit denial of their real existence. That is, he chooses to state something like this: some angels are guardian angels, but in reality there are no angels. This statement contains the quantifier some, formalized by, along with the predicate exists. That is, the atheist would affirm that XX and ERX, where R stands for the set of all real things. The existence predicate has been defined elsewhere, Bunge 1977a, 155-6. The existence predicate may be defined as follows. Let be a universe of discourse, and S a proper subset of. Further, consider the characteristic function S of S, that is, the function S such that S, x, equals 1 if x is in S, and 0 otherwise. We now define the existence predicate ES as follows: ESX equals, S, x, equals 1. If S equals R, we have real existence, whereas if S equals C, we have conceptual, or ideal, existence. Scientists use several criteria of real existence, such as observability and reactivity, kicking back. In pure mathematics, utterly different existence criteria are used, such as definability, constructivity, and absence of contradiction. Since things come with their properties and the changes thereof, these two are real. So, the expressions property X is real and process Y is real must be understood as affirming the reality of the underlying thing, S. Materialists identify reality with materiality. That is, the main assumption of materialist realism is postulate 1.4 all and only material things, complete with their properties and changes, are real. In other words, the concepts of real existence, materiality, and possessing energy are postulated to be coextensive, even though they have different 29 senses or connotations, as shown by their definitions. Postulates 1.1 and 1.3 jointly entail Theorem 1.1 all changeable items are material and conversely. To put it in somewhat paradoxical terms, to be material, real, is to become. This identification of reality with materiality is not a philosophical extravagance but normal in factual science. For example, in criticizing Mach's subjectivism, Ludwig Boltzmann, 1979, 112, equated realism with the centerpiece of materialism, namely, the so-called identity theory of mind. Mental processes are identical to certain material processes in the brain, realism. Today's cognitive neuroscientists are likely to concur. However, one may, like Plato and Leibniz, embrace at once realism and immaterialism. That is, one may hold that concrete things are only shadows, copies, or corruptions of self-existing ideas. That this thesis is at best untestable, and at worst false, is beside the point. My point is that realism is logically independent of materialism, but vulnerable unless united with it. However, the matter of realism deserves a separate section. 8. Realism. Realism is the thesis that there are real things. However, like any other comprehensive philosophical system, realism has 7 components: ontological, epistemological, semantic, methodological, axiological, value theoretical, moral, and praxeological, action theoretical. Besides, every one of these constituents comes in various shades: naive, critical, and scientific. Hence, one may distinguish altogether 21 possible kinds of realism. One way of distinguishing these various doctrines is to state and analyze the principles of scientific realism, the more restrictive and therefore most complex form of realism. This doctrine may be summarized into the 7 principles conjoined by the following postulate. 1.4 Realism is the philosophical system constituted by the following 7 theses. 1. Ontological realism: the external world exists independently of the knowing subject. 2. Epistemological realism. A. The world can be known. B. All knowledge of facts is incomplete and fallible, and much of it is indirect. 3. Semantic realism. A. Some propositions refer to, are about, facts. 30. B. Some such, factual, propositions are approximately true. C. In principle all approximations are perfectible. 4. Methodological realism. The best strategy for exploring the world is the scientific method, scientism. 5. Axiological realism. There are objective values, such as health, knowledge, security, peace, environmental protection, and fairness. 6. Moral realism. There are, a. moral facts, such as generous deeds and selfish ones, and, b. true moral principles, such as rights, to be fair and respected, must be balanced by duties, and solidarity and democracy favor coexistence. 7. Practical realism. There are objective pairs, such as, and. Let us next focus on ontological, epistemological, and semantic realism. The remaining components of the system will be further examined in Chapter 10. Naive realism holds theses 1, 2a, and 3a. Critical realism consists of the first three complete theses. Thesis 4, also called scientism, is peculiar to scientific realism. Planck, 1933, 82, emphasized clause 2b, which he stated as follows: the real outer world is not directly knowable. This was his response to the positivist thesis that sense impressions supply direct knowledge and are the only source of knowledge. A familiar counterexample to the positivist thesis is this: the light given off by a light source, such as the sun, does not point directly to the composition and structure of the source, it only poses the problem of conjecturing these features, for instance, that our star is constituted mostly by hydrogen, that the hydrogen atom has a single electron, that the latter can be in any of infinitely many states, and that every transition between states is accompanied by the emission or the absorption of a photon whose frequency is proportional to the difference between the energies characteristic of those states. Contrary to a widespread opinion, scientific realism does not claim that our knowledge of the outer world is accurate, it suffices that such knowledge be partially true, and that some of the falsities in our knowledge can eventually be spotted and corrected, much as we correct our path when navigating in new territory. Thus, the fallibilism of thesis, 2b, is balanced by the meliorism of thesis, 3a. Reality checks, empirical tests, will show again and again that even the most accurate theories are at best more or less close approximations that can be improved upon. Rescher, 1987, calls this thesis approximationism. I regard it as a constituent of scientific realism, example Bunge 1967a. The frequent occurrence of error, perhaps even better than the occasional finding of truth, proves the existence of the real world, Bunge 1954. Indeed. 31. While a subjectivist could argue that scientists construct the world as they perceive or conceive it, he would be unable to account for discrepancies from the truth, particularly since falsities and approximate truths occur more frequently than completely accurate truths. In particular, intuitionists, such as Bergson and Husserl, cannot account for error because they claim to have instant access to full truths. Finally, anti-realism is of course the opposite of realism. Like the latter, it consists of 7 branches, every one of which comes in various shades. The most popular version of anti-realism is subjectivism of the phenomenalist kind, from Kant to logical positivism. It will be examined in the next chapter. 9. So far we have stressed some ontological notions, in particular that of ontological objectivity or independent existence. Let us now turn to epistemological objectivity and its kin. A factual proposition is said to be objective if it refers to real existence in an impersonal manner, and describes them to the best of its author's knowledge, see Rescher 1997. Ideally, objective propositions are true. In practice most propositions, particularly the quantitative ones,
are at best approximately true. Impartiality, though related to objectivity, is different from it. An impartial judgment is one that takes no sides in a conflict. No conflict of interests, neither partiality nor its contrary. Yet, partiality is compatible with objectivity. For instance, universal Medicare may be favored not only on moral grounds but also because a healthy population is in the interests of everyone. Just think of infectious diseases and of the many resources wasted because of sickness. Max Weber, 1988-1904, famously demanded that the social and political sciences be objective. He wanted to purge these disciplines from value judgments, all of which he, mistakenly, regarded as unavoidably subjective. Weber wished, in particular, to prevent the ideological contamination of the social studies. This goal is laudable, for scientific research is, by definition, a search for objective truths, whereas ideologies are biased and often mendacious. But are value neutrality and impartiality possible? The postmoderns deny it. They hold that, since knowledge is power, and since research is ordinarily funded by the powers that be, power lurks behind every research project, at least in the field of social studies. In particular, Habermas, 1970, and other members of the Frankfurt, or critical theory, school, along with a number of student activists in the 1960s, incurred two false identifications. These were science equals technology and science, or technology, equals ideology of late capitalism. These writers did not 32. Understand that, whereas basic science is the disinterested search for truth, technologists design artifacts, and ideology is the intellectual component of a social movement. However, let us return to Weber. I submit that Weber conflated three different concepts, those of objectivity, impartiality, and disinterest. Worse, he failed to be objective whenever he put into practice the neo-Kantian dogma that the aim of social science is to understand or interpret the inner or subjective life rather than to describe the so-called material conditions of existence, such as means of livelihood, work safety, and freedom to join unions fighting for a measure of social justice. No doubt, an objective student of society will pay attention to attitudes and subjective evaluations. But emphasis on the subjective area, with disregard for the objective conditions of existence, is not only a methodological lapse but also a piece of ideological partisanship. It was no coincidence that Weber's first empirical work, of 1892, was his participation in a survey of the conditions of rural workers conducted by the Verein für Sozialpolitik. Its core was a group of university professors who were worried about the growing antagonism of German workers, organized in socialist unions, toward the German state. Lazarsfeld and Oberschall, 1965, 185. Another fact that alarmed Weber was that, by importing Polish laborers, the East Prussian landowners endangered the German character and the national security of the east frontier of the German Reich, Ibid, 186. Thus, on this occasion Weber put his science in the service of his liberal and nationalist ideology. Why is Weber generally regarded as more scientific than Marx and Engels, Marx's co-worker, who described objectively the material conditions of the English working class on the strength of first-hand research as well as reports by industrial inspectors appointed by Her Majesty's government, is yet to be explained objectively. In any event, Weber's objectivity thesis was hardly original. In fact, it was what Thucydides and Aristotle had practiced in antiquity, Ibn Khaldun in the Middle Ages, Niccolò Machiavelli in the Renaissance, and Leopold Ranke in the early 19th century. Adam Smith, David Ricardo, Alexis de Tocqueville, Karl Marx, and Émile Durkheim had been no less committed to the search for truth in social matters, even though each of them had also his own axe to grind, as did Weber. In sum, objectivity, though often hard to attain, particularly in social matters, is both possible and desirable. Moreover, it is mandatory in matters of cognition. However, objectivity must not be confused with value neutrality,
because the pursuit of certain values, such as well-being, peace, and security, is objectively preferable to the pursuit of others, such as the pleasure derived. 33. From getting drunk or attending a public execution. Objectivity is also desirable in the fields of technology, public policy, and the struggle for power, since in these cases a false picture of reality is bound to result in practical failure. In short, objectivity is desirable and attainable everywhere except in art. In other words, realism is the philosophy of knowledge inherent in successful science, technology, and praxis. 10. We have attempted to elucidate the notions of thing and fact because they are far from clear in the philosophical literature. And, contrary to a certain tradition, we have neither confused realism with materialism nor kept them apart. After distinguishing them, we have joined them in a doctrine that may be dubbed hylorealism. One reason for wedding realism to materialism is that the idea of irrealist materialism is an oxymoron, since the statement that the universe is material amounts to the claim that the non-conceptual is known to be material rather than, say, ghostly. Another reason is that materialism without realism is both pointless and toothless. Indeed, what would be the point of exploring a purely imaginary or totally unknowable material universe? And how firm would realism be without the assumption that all real things, however ephemeral or artificial, abide by laws that are either physical or rooted, however remotely, in physical laws? In general, epistemology and ontology, though distinguishable, are inseparable. For instance, radical, or dogmatic, rationalism calls for an idealist ontology, because only abstract ideas can be known, invented or learned, without the aid of experience. And radical, or dogmatic, empiricism requires a phenomenalist ontology, because experience deals in qualia, not in primary properties, which are the ones characterizing things in themselves. Whoever admits the existence of things in themselves rejects both dogmatic rationalism and dogmatic empiricism, and adopts instead ratio empiricism, or empiriorationalism, a synthesis according to which human cognition makes use of both reason and experience. This is so for two reasons. One is that the overwhelming majority of facts are imperceptible, hence accessible only through conception. The other reason is that the normal human brain is active and inventive as well as reflexive. In particular, it looks for ideas or deeds behind words, reasons behind assertions, and mechanisms behind appearances. However, the concept of an appearance or phenomenon is so slippery, and yet so central to many influential philosophies, that it requires an entire chapter, the next one. 34. 2. The distinction between subject and object, or explorer and territory, is commonsensical. This distinction is enshrined in naive realism, the tacit epistemology of nearly everyone. Moreover, that distinction would seem to be essential to animal life. Just think of the chances a gazelle would stand if did not instinctively acknowledge the real existence of lions in its outer world. Yet, a famous Harvard philosopher, Putnam 1990, 122, once announced that the idea of discourse-independent objects has crumbled under philosophical critique, in particular that of Wittgenstein, Carnap, and Quine. So, don't worry, gazelle, the lion is only in your mind. Go see a shrink. To his credit, shortly thereafter Putnam 1994 abandoned anti-realism. The earliest irrealist philosophy is found in the Upanishads, ca. 800 BC. According to these theologico-philosophical texts, the world is illusory, only Brahman, the Godhead, would be real. 3 centuries later, the Buddha taught that there is an unknowable reality hiding behind appearances, but no God. At about the same time, the view was attributed to Protagoras, alas, falsely, that there are no subject-independent things, hence no objective truths. Illusionism has remained popular in India to this day, but did not prosper in the West. In fact, the overwhelming majority of ancient Greek, medieval, and early modern thinkers in the West have been objectivists, realists. Subjectivism became important only at the beginning of the 18th century, partly as both an expression of the rising individualism and a reaction against modern science. Recall Berkeley and his followers, up to the social constructivists. Only Hamlet, an idle prince, could afford to entertain the possibility that life is a dream. Shakespeare and his European contemporaries were busy constructing modernity. The ancient questions, whether all things are as they appear to be, and whether we can know anything beyond appearances, have resurfaced in Ter. 35. Mitently in modern philosophy and in science, witness the epistemological discussions of Galileo, Descartes, and Locke, Berkeley, Hume, and Kant, Comte, Mill, and Mach, and their 20th century followers, from Russell, Bridgman, Carnap, and Reichenbach to Nelson Goodman, Thomas Kuhn, Paul Feyerabend, and David Lewis. The same questions, with similar answers, reappeared from the mid-1920s in the controversies over the interpretation of quantum mechanics. They even occur in Michael Frayn's famous play Copenhagen. All of these ideas are involved in one of the oldest philosophical disputations, that between phenomenalism and realism. What reasons have been adduced in favor of either view, and why does it matter which horn of the phenomenalism/realism dilemma one chooses? These are some of the topics to be discussed in this chapter. 1. Phenomenon and noumenon. In ordinary language, the terms phenomenon and fact are synonymous. Not so in philosophy, where the Greek word phenomenon, appearance, stands for an observable fact or event, an object or aspect known through the senses rather than by thought or non-sensuous intuition, Webster's New Collegiate Dictionary. Thus, colors, sounds, tastes, smells, and textures are sensory or phenomenal properties, whereas wavelengths, atomic weights, chemical compositions, planetary orbits, other people's thoughts, and political crises are non-sensory or non-phenomenal. Phenomenal properties or raw feelings, such as the smell of mint and the feel of the beloved's skin, are features of sensory experience. They are also called qualia. All sentient organisms experience some qualia, whereas no machines, not even robots, have them. Nor do zombies, if they exist. Non-sentient things have and detect only physical, or chemical, biological, or social, properties. We learn these distinctions early in life, and forget them on occasion if exposed to an irrealist philosophy. Indeed, presumably we start life as spontaneous phenomenalists. The world around a newborn human is likely to look and feel like a rather chaotic mass of appearances, tactile sensations, visual images, sounds, tastes, and smells. In other words, presumably babies describe the world and themselves in terms of secondary properties such as soft, wet, warm, slimy, smelly, tight, bright, loud, and frightening. As we crawl away from the playpen and learn, we add primary properties to our repertory: long, round, heavy, swift, and so on. That is, eventually we become realists, first of the naive kind and later on, upon further reflection. 36. Critical realists. Much later, with luck and further learning, and barring encounters with subjectivist philosophies, we may end up as scientific realists. Kant famously called non-phenomenal things noumena, or things in themselves, by contrast to the things for us, phenomena, or things as perceived. However, as we shall see, he could not make up his mind on whether phenomena can exist without any underlying noumena. Many contemporary philosophers still debate the status of qualia. Physicalists, vulgar materialists, deny their existence, whereas radical empiricists claim that qualia are the source and origin of everything else. Meanwhile, biologists and cognitive neuroscientists take it for granted that phenomena are made out of noumena, and attempt to find out how qualia emerge from processes in the organism/environment interface. To the extent that they succeed in this endeavor, they confirm emergentist materialism, example Sellers 1922, Bunge 1979a, Blitz 1992. This is the variant of materialism that embraces Spinoza's central thesis, one substance, many properties. This doctrine combines substance monism with property pluralism. Hence it admits the limitation of radical reductionism, Bunge 2003a. By the same token, emergentist materialists reject physicalism or eliminative materialism, which denies qualitative novelty and therefore impoverishes both human experience and its science, namely, psychology. Freshmen face the same problem when taunted by the old chestnut: did the tree falling in a remote forest make a noise if there was no one around to hear it? If smart, they will answer that there was sound, in fact a shock wave, without loudness, a noumenon without a phenomenon. The standard or Copenhagen interpretation of quantum mechanics makes the opposite claim. It states that electrons and the like lack properties of their own, but acquire whatever properties the experimenter decides to endow them with. We shall argue that this extraordinary claim derives from confusing reality with reality tests, the source of operationalism. This problem, like most ontological queries, has ancient roots. For example, the Buddha was a phenomenalist. The earliest Western phenomenalist seems to have been Protagoras of Abdera, and the earliest treatise on the subject Sextus Empiricus's Hypotyposes. The former is famous for having stated the principle man is the measure of all things. And Sextus is well known for having relied consistently on sense data, and for having argued in detail, alas, often sophistically, against all the scholars known to him. Many later eminent philosophers, like Hume and Kant, as well as some scientists while in a philosophical mood, like Mach and Bohr, have claimed that only appearances count. A similar thesis is this: the secondary properties or qualia, such as brightness, loudness, warmth, softness, wetness, sweetness, roughness, and colored, are basic either ontologically or epistemologically. However, the distinction between the two kinds of properties deserves a new section. 37. Two primary and secondary properties. Realists hold that properties come in two kinds: primary or subject independent, and secondary or subject dependent. For instance, light wavelength is primary, whereas color is secondary because it emerges in the brain. By contrast, according to phenomenalism, all of the primary or objective properties, such as velocity, energy, entropy, chemical bond, dissociation energy, metabolic rate, population density, GDP, and the social order, would be derivative or even imaginary, because they are not apprehended by the sense organs. See Table 2.1. An equivalent way of drawing the same distinction is to speak of phenomenalist and realist, or physicalist, propositions or sentences, example Kyla 1979. The phenomenalist claims that the phenomenalist propositions are primary, and the realist ones secondary, in the sense that they are somehow derivable from the former. Of course, such derivation cannot be direct. The phenomenalist and physicalist propositions are separated by a chasm as long as the predicates occurring in them remain self-contained. However, this chasm can be bridged by assumptions or definitions containing concepts of the two kinds. A clear example of such bridge is Kant's, and Mill's, Mach's, Carnap's, and Husserl's definition of a thing as a possibility of experiences or sensations. Table 2.1 Sample of primary, or objective, and secondary, or subjective, properties. Whereas some of the former are in the outer world, all of the latter are in the brain. Primary properties, secondary properties. Position, place. Time, perceived succession. Size, bulk. Velocity, swiftness. Wavelength, color. Sound intensity, loudness. Sound frequency, pitch. Temperature, thermal sensation. Viscosity, permeability. Engram, recall. Activation of the amygdala, fear. Deprivation, dissatisfaction. Atomic mass. Spin. Electric charge. Entropy. Valence. Dissociation energy. 38. One trouble with this alleged reduction is of course that psychology is the only science that studies sensations. Moreover,
it attempts to explain them as brain processes, which are in turn described in terms of primary properties. Another problem is that physics is demonstrably irreducible to psychology. Just try to explain electromagnetism and nuclear physics, say, in terms of perception, memory, emotion, and the like. 3 phenomenalisms, ontological and epistemological. The philosophical doctrine that admits only phenomena, that is, appearances to someone, is called phenomenalism. Phenomenalists have no use for noumena, such as the things or events that elicit our sensations, or the items that, though deemed to exist, no one could possibly perceive. Think, for example, of the collision of the Earth's plates that caused the latest earthquake, of the electrons that circulate in your computer, of the neuron firings involved in your watching your computer's screen, or of the surges of greed and fear behind the latest stock market fluctuations. All this and much more is beyond the phenomenalist's ken, as is the universe as a whole. However, 2 kinds of phenomenalism must be distinguished, ontological and epistemological. The ontological phenomenalist claims that there are only phenomena, whereas the epistemological phenomenalist holds that only phenomena can be known. In other words, ontological phenomenalism, existent equals apparent epistemological phenomenalism, knowable equals apparent ontological phenomenalism, such as that of Berkeley, Renouvier, Avenarius, Mach, Ostwald, Carnap, and Boer, places man at the center of the universe. It is anthropocentric. By contrast, epistemological phenomenalism, such as Plato's, Ptolemy's, Hume's, Duhame's, and Spencer's, is less radical. Indeed, it makes no claims about reality, except to declare it unknowable. It just restricts knowledge to perception. Recall Plato's allegory of the cave. We can see only the shadows projected by real things, which dwell in the realm of ideas. Kant, as will be seen below, wavered between the 2 kinds of phenomenalism, asserting the former on one page, and the latter on the next. Kant's main successor, Hegel, left phenomena to science, and kept noumena for himself. Indeed, he told scientists to restrict themselves to phenomena and inductive generalizations. Among these he counted Kepler's laws, which he misunderstood. Moreover, he claimed that they entail Newton's laws of motion, Hegel 1969, Sector 270. He, Professor Hegel, would take care of the things in themselves, revealing, for instance, that air in itself is fire, 1969, Sector 283, and that the magnet represents in a simple naive fashion the nature of the 39 concept, and in its developed form that of deduction, Ibid, Sector 312. Hegel's sanity is in doubt. What is certain is that he, along with Fichte and Schelling, adopted the worst components of Kant's a priorism, and were the first moderns to successfully pass off convoluted nonsense as deep philosophy. Clearly, ontological phenomenalism entails epistemological phenomenalism. Indeed, if there are only phenomena, then only phenomena can be known. And phenomenalism of either kind opposes realism, the view that the external world exists by itself and is knowable to some extent. See Figure 2.1. Subject secondary properties. Ontological phenomenalism. Object secondary properties. Subject secondary properties. Epistemological phenomenalism. Object secondary properties. Subject primary and secondary props. Ontal. And epistem. Realism. Object primary properties. Figure 2.1. The 2 phenomenalisms, ontological and epistemological, and double realism. Ontological phenomenalism, the knower constructs the object, which is entirely sensuous. Epistemological phenomenalism, the object, which is phenomenal, induces phenomena. Neither type of phenomenalism has any use for primary properties. Realism, phenomena emerge at the subject-object interface, as when we perceive a grass knoll as green, or a candy as sweet. Both the object and the subject have primary properties, but of course the knower senses also secondary properties in addition to some primary ones. 40. 4 Qualia in materialism. Scientific realists and emergentist materialists do not deny the existence of qualia. And they know that these are quite different from physical objects and their primary properties. For example, whereas the wavelengths of the light that causes color sensations are ordered on a linear continuum, the corresponding colors may be arranged around a circle, see figure 2.2. Realists and emergentist materialists just hold that qualia emerge in some nervous system, usually as a result of external stimuli. Consequently, they propose that qualia be studied by psychology, in particular psychophysics and cognitive neuroscience, rather than by a priorist philosophy. As Clark, 1993, 8, says, the scholars who support this research project do not argue that current explanations are complete, or even true, but merely that the approach has no conceptual flaws, and can answer the various a priori objections. In short, it could succeed. That finding would suffice to defeat the skeptic, or at least to postpone the onset of melancholia. People like us, used to thinking of such unobservable entities as atoms, force fields, DNA molecules, neurons, dinosaurs, nations, and the universe as a whole, may find it difficult to understand how such eminent thinkers as Hume, Kant, Mill, Mach, at one time Russell, Bohr, Heisenberg, and Born, to mention only a few, could have espoused phenomenalism. This is particularly baffling in the case of skeptics like Hume, and atomic physicists like Bohr and his circle. Perhaps such incongruity can be understood by placing the doctrine in question in historical perspective. After all, phenomenalism had sometimes been used to cast doubt on the supernatural and to curb the wild imagination of metaphysicians. Let us therefore go back a few centuries. 5 From the scientific revolution to Locke. The story of the 17th century scientific revolution has been told many times. Here I will recall only 3 philosophical features of that great move. Figure 2.2, A. The line of light wavelengths. B. The circle of colors. A, B. 0. Red, yellow, blue, green. 41. Meant that are pertinent to our subject. These are the ontologies that those revolutionaries contended with, the distinction between primary and secondary qualities, and the concept of a law of nature, or objective and necessary connection, without which the world appears, in William James's phrase, as a blooming, buzzing confusion. I submit that, at the time of Galileo, Descartes, Harvey, Boyle, and the other pioneers of modern science, there were 4 major contending worldviews. A. The magical view, which imagines the world teeming with supernatural beings. B. The common sense or ordinary knowledge ontology, centered on the data provided by the senses. C. Aristotelianism, which tries to account for everything in terms of perception, occult qualities, and causes of 4 kinds: formal, material, final, and efficient. And D. The emerging mechanistic worldview, according to which there are only bodies and their microscopic components, along with causes of a single kind, efficient. The heroes of the scientific revolution hardly bothered to criticize the magical worldview, they addressed the educated public. The ontologies that the heroes of the scientific revolution sought to undermine were the common sense one and the scholastic version of Aristotle's physics. The scientists did this in 2 ways, by criticizing these views and by replacing them with clear and testable, if not always true, hypotheses concerning material entities in motion, such as Copernicus's model of the solar system, Galileo's law of falling bodies, Kepler's laws of planetary motion, Boyle's law of gases, Huygens's theory of light, and Harvey's theory of the cardiovascular system. But the scientific revolution was far more than a collection of scientific discoveries. It also involved a new worldview, mechanism, and a new epistemology, scientific realism. The root of both is the distinction between primary and secondary properties. The former are the geometrico-mechanical qualities inherent in things, and thus objective. By contrast,
the secondary properties are subjective, they are the sensations and feelings caused by the external objects on sentient beings like us. However, this distinction was understood to be provisional, since in the end the secondary qualities were assumed to be reducible to the primary ones, as when perception was explained in terms of atoms penetrating into the sense organs, Dijksterhuis 1986, 431-3. Galileo proposed the key distinction between primary and secondary properties in Il Saggiatore, 1953 1623, 312. Here he stated that tastes, smells, colors, and the like reside only in the sensitive body, so that, if the animal is removed, all those qualities are removed and annihilated. For instance, if someone touches slightly our foot sole, we will feel tickled, a condition that is all ours, and not the hand's. Following Galileo, though without quoting him, Descartes clarifies the primary-secondary distinction at several places. For example, he starts LE 42. Monde, 1664-1633, 7-10, with a discussion of the difference between our sensations and the things that produce them, precisely the difference that phenomenalists deny. There he attempts, alas, vainly, to account for the burning of a log in terms of the very fast and very violent movements of its tiny parts. He contrasts this mechanical explanation with the empty verbiage of the schoolmen in terms of the form of fire, the quality of heat, and the action that allegedly burns the wood, as if fire were not enough. Descartes adds that the sensations that fire causes in us, such as those of warmth and pain, are not properties of the fire although they are caused by it. He thus warns against confusing secondary with primary qualities. Let us now cross the channel and advance the calendar by 6 decades, to look briefly at John Locke. He too adopted Galileo's distinction, he was an ontological realist, and moreover occasionally tempted by materialism, as when he famously wondered whether matter might think. He thought it obvious that the external bodies exist by themselves. Moreover, Locke, 1690, BK2, Sector 8, 9, asserted that the primary qualities are utterly inseparable from the body, in what estate soever it be. By contrast, the secondary qualities, such as colors, sounds, tastes, etc., are nothing in the objects themselves. However, he also held, Ibid, BK4, Sector 3, 28, that we can have no distinct knowledge of the motions of bodies beyond our experience, because we do not understand how they cause sensations in us, other than by the intercession of an infinitely wise agent. So, we are utterly incapable of universal and certain knowledge of the bodies around us. Little did Locke suspect that his skepticism concerning the power of science was behind the times, since the scientific revolution was already well advanced. In particular, he was unaware that Newton's magnum opus, 1687, which contained precisely some of the laws of motion that Locke had decreed unknowable, appeared the same year that he finished his essay. Both men interacted, though only briefly and about matters of government. Luckily, not even Locke's great intellectual authority could prevent the triumphal march of Newtonianism. However, his skepticism regarding the power of science eclipsed the important work of his near contemporary Thomas Willis, the early modern neuroanatomist who regarded the brain as the organ of emotion, perception, and memory, Zimmer 2004. This is one more example of the harm that arrogant philosophers can cause. Would Locke have adopted a less skeptical stance concerning the power of the intellect to get to know the mechanical affections of bodies had he known of Newton's work and its sensational success? I doubt it for the following reasons. First, Locke did not have the mathematics required to read, understand, and appreciate Newton's formulas. Second, whoever accepts 43. Newtonian mechanics must give up Locke's empiricism, for the former involves concepts that, like those of mass, acceleration, and gravitational interaction, are absent from the empirical data serving to check the theory. Ironically, Leibniz, 1703,
refuted Locke's empiricism but rejected Newton's mechanics. Be that as it may, Locke's skepticism about science, together with his belief that only God could effect connections among things, unwittingly opened the door to Berkeley's subjectivist philosophy, of which more anon. 6. The Counter-Revolution, Phase 1, Berkeley. Not everyone accepted the mechanical worldview that replaced Aristotle's organicism. After all, the view that the world is a clock seemed drab and gray in excluding everything that makes life worth living, from colors, tastes, textures, and scents to feelings, passions, ideas, and values. Hence most artists, theologians, and humanists were bound to react vehemently against mechanism. It is generally believed that the first anti-mechanist and anti-realist reaction was Romanticism, from Rousseau, Vico, and Burke to Goethe, Schelling, Fichte, Hegel, Schopenhauer, and Coleridge. Actually, the first reaction came much earlier and from an unexpected quarter. It was the radical phenomenalism of Berkeley, Hume, and Kant. In this regard, these philosophers were the first Romantics. But of course they were pre-postmoderns, as Merton would say, in that they upheld rationality even while defending their most outlandish doctrines. Berkeley's animadversion to mechanism is generally acknowledged because of his explicit and clever attacks upon Newton's physics and mathematics. But because Hume ignored Newtonianism, and Kant paid lip service to it, and because both philosophers were agnostic, we tend to forget that both were just as subjectivist as Berkeley. Worse, we are often told that Hume and Kant were the philosophers of the new science, while actually they undermined it while understanding nothing about it. Let us see why. Like Locke, George Berkeley held that to know is to perceive. But, unlike Locke, he famously contended that to exist is to perceive or to be perceived, to which he later on added to act. Therefore he deemed matter, with its alleged primary qualities, to be a figment of the imagination. In fact, Berkeley, 1901, 260-1, claimed that all the choir of heaven and furniture of the earth, in a word all those bodies which compose the mighty frame of the world, have not any subsistence without a mind, that their being is to be perceived or known, that consequently so long as they are not actually perceived by me, or do not exist in my mind, or that of any other created spirit, they must either have no existence at all, or else subsist in the mind of some eternal spirit. 44. Without this assumption, that God can be counted on to keep the world going while the subject is absent or asleep, Berkeley's philosophy would not have been intellectually respectable. That is, a secular version of Berkeley's philosophy would have been even more outrageous. This is the case of Husserl's phenomenology, according to which the world of things is only a presumptive reality, whereas I myself, that is, Professor Husserl, am an absolute reality, Husserl 1931, 145. Whereas to Berkeley the world is a collection of human and divine percepts, to Husserl it is an infinite idea, a complete synthesis of possible experiences, Husserl 1960, 62. And, whereas Berkeley's prose is crystal clear and logically consistent, Husserl's is neither. For example, Husserl states that the proof of transcendental, non-empiricist, idealism is phenomenology itself, 1960, 86. And, although he claims that the real world is subject-dependent, Husserl also demands that one must go back to the things themselves. However, what he means by thing is a complex of sensations. Furthermore, Husserl holds that, to grasp the essence of a thing, one must start by pretending that it does not exist, one must perform the epikef or bracketing out operation. Thus, Husserl closes his Cartesian meditations with a quote from Saint Augustine, "Do not wish to go out, go back into yourself." That is, look inward, not around yourself. However, let us go back to the master subjectivist, whom so many copied without giving him credit. Berkeley's phenomenalism is ontological as well as epistemological. And he contends that his view is commonsensical because, unlike the views of the schoolmen and the new scientists alike, he invokes only sense data. Foreshadowing Hume and Kant, Berkeley also claims that there are neither objective, subject-free, connections nor laws. There is nothing necessary or essential about bodies, but it depends entirely on the will of the governing spirit. 1901, 316. Berkeley's subjectivism is unique in its cogency, clarity, and literary elegance. This is why it passes for being irrefutable as well as obviously false. However, Berkeley's philosophy is hard to refute only if its premise, that knowing is limited to perceiving, is admitted, and consequently the power of scientific theory is doubted. Indeed, the success of Newtonian mechanics provides the desired refutation, for, if astronomers can use this theory to predict that Venus will appear to us first as the morning star, and towards the end of the same day somewhere else as the evening star, then we must admit that they know something about matter that goes far beyond the primitive knowledge of secondary qualities delivered by the senses. That is, conception can overcome the limits of perception. This is why theories, not data, crown modern science. 45. However, an even stronger argument against the identity of ideas and reality comes not from the successes of science but from its failures. Bunge 1954. Indeed, subjective idealism is falsified every time a theory fails to account for the behavior of something. Only scientific realism makes room for factual error, that is, discrepancy between idea and fact. Such discrepancy cannot be explained by subjectivism, intuitionism, or empiricism. And yet the discovery of error is a major stimulus for engaging in scientific research. A completely true theory induces complacency and thus stagnation. This is why Rita Levi-Montalcini, the great neuroscientist, titled her autobiography In Praise of Imperfection. What might have led Berkeley to his outlandish theory? Certainly not empiricism per se, because an empiricist may allow for the autonomous existence of the external world, as was the case with Sextus, Bacon, Locke, and Hume. The source of Berkeley's theory may be the confusion of existence with existence criteria or tests, a conflation of ontology with methodology. Thus, how do I know that there is a rose bush in that garden? Because I can touch, see, and smell that plant. It would seem then that, indeed, to be is to be perceived, until the botanist examines the plant under the microscope and subjects it to tests showing that it possesses many more primary than secondary properties, such as the abilities to absorb light, synthesize sugar, and grow by cell division. Berkeley's conflation of existence with existence tests is the source of three influential 20th century philosophies: operationism, the verification theory of meaning, and constructivism. Operationism, Bridgman 1927, a version of logical positivism, can be summed up in two formulas: a, the ontological principle to be is to be measured, and b, the semantic principle that the scientific concepts are defined by, or get their meaning from, laboratory operations. This was the philosophy of science dominant in the first half of the 20th century. Amazingly, it was also the philosophy behind the so-called Copenhagen interpretation of quantum mechanics, according to which atoms and the like do not exist as long as no one observes them. See, example Bohr 1958, Heisenberg 1958, and Bunge 1959b. The falsity of principle, A, becomes clear upon reflecting on the following counterexamples. There are many different ways of measuring times, yet there is a single, classical, concept of time. As for principle, B, not all concepts are definable in a given theory, some of them, the definers, are basic or primitive. Besides, defining is a conceptual operation, not an empirical one. For example, a speedometer measures the value of speed, which in classical physics is defined as distance over time. Incidentally, the very design of such an instrument involves fragments of physical theory, among them the said definition. 46. The verification theory of meaning, see, example Air 1959, states that the meaning of a non-logical sentence consists in the operations whereby it is verified. Accordingly, test would precede meaning, which of course is false, since we must understand the meaning of a statement before we can even imagine how to put it to the test. Just think of endeavoring to test, say, the basic law of electrostatics, namely, equals 4, before finding out what these symbols mean, and before figuring out observable indicators, or operational definitions, of the potential gradient and the electric charge density. The correct sequence is meaning test, not the converse, see Bunge 1974b. And, as mentioned above, empirical tests involve indicator hypotheses, that is, bridges between unobservables, such as neural disorders, and observables, such as behavioral disorders. See Figure 2.3. Finally, constructivism comes in 4 varieties: A. Ontological, or Berkeleyan, that is, things are bundles of perceptions; B. Social, that is, all scientific facts are social constructions rather than occurrences in the external world; C. Psychological, or Piagettian, that is, as they grow, children construct by themselves the concepts of object, time, number, conservation, and so on; and D. Pedagogical, that is, the student must be allowed to learn by himself with minimal guidance. We dealt with ontological constructivism before, and concluded that it is the double delusion that the subject is the center of the universe and that there can be observations without things observed, or phenomena without noumena. This is classical or individualist constructivism. Its contemporary successor is social constructivism, example Berger and Luckman 1966, Latour and Woolger 1986, Norsetna 1981, Collins 1998. This is the opinion that, A. the scientific communities, not individual investigators, discover and invent, and, B. those groups construct not only ideas and experiments, but also the objects they study. Thus Woolger, 1988, 65 representation gives rise to the object. Representation of what? Of the object, of course. For want of logical rigor, the sociology of knowledge, a once promising discipline, Merton 1973, was turned into an extravagance. Unobserved U indicator hypothesis observed A. Conjecture about U. Reference evidence. Figure 2.3. A conjecture about an unobservable trait U is tested by means of an indicator hypothesis of the form U equals F, O, where O is an observable feature. 47. This is not to deny that scientists are embedded in social networks of various kinds, so that every one of them is indebted to several others. Nor is it to deny that scientific ideas are active and sophisticated constructions rather than automatic responses to environmental stimuli. But it is also hard to deny that only individuals can think, and that the natural and social scientists study only external items, such as earthquakes and the emotions felt by fellow humans. Among the many facts worth studying are the serious social problems of science, such as the shortage of funding, the declining enrollments in science programs, the distortion of problems and results by economic and political interests, and the popular appeal of the pseudosciences and the anti-scientific philosophies. But the social constructivists overlook these problems; they are more interested in criticizing science than in defending it. Let us finally glimpse at the 2 remaining varieties of constructivism, psychological and pedagogical. Psychological constructivism is an important scientific theory. Its philosophical interest lies in the fact that it opposes the empiricist view that all constructs are distillates of experiences. True, when Piaget wrote about the child's construction of reality, he sounded as if he had adopted Berkeley's subjectivism. But his research shows that he was a realist. Pedagogical constructivism will be dealt with in Chapter 3, Section 9. Suffice it here to state that it is just as extravagant as Berkeley's, only even more destructive, because it implies that teachers are expendable. Let us now go back to the sources of all of the above philosophical extravagances in the 18th century. 7. The Counter-Revolution, Phase 2, Hume. Like Locke and Berkeley before him, David Hume was a radical empiricist. But, contrary to Berkeley,
Hume owned that the operations of nature are independent of our thought and reasoning, 1888 1734, 168. However, he denied the difference between primary and secondary qualities. Indeed, he stated that colors, sounds, heat and cold, as far as appear to the senses, exist after the same manner with motion and solidity, and that the difference betwixt them is founded neither on perception nor on reason, but on the imagination, ibid. Consequently, Hume thought that we have no satisfactory idea of matter, ibid. 229. Thus his phenomenalism, like Protagoras', was epistemological, not ontological. Matter may well exist, but we cannot know it because the sense organs are the only organs of cognition, and all knowledge comes from perception. Although Hume writes about laws of nature, he regards them all as inductions from observations and, as such, as superficial and contingent. Nature 48. Has kept us at a great distance from all her secrets, and has afforded us only the knowledge of a few superficial qualities of objects. Hume 1902 1748, section 4, pt 2. He goes as far as explicitly questioning Newtonian mechanics because it goes beyond sense data. Sight or feeling conveys an idea of the actual motion of bodies, but as to that wonderful force or power, which would carry on a moving body forever in a continued change of place, and which bodies never lose but by communicating it to others, of this we cannot form the most distant conception, ibid. If the laws of nature are not necessary, then anything can happen. This is what Hume asserts in the most famous passage of his Inquiry: the contrary of every matter of fact is still possible, because it can never imply a contradiction, and is conceived by the mind with the same facility and distinctness as if ever so conformable to reality. That the sun will not rise tomorrow is no less intelligible a proposition, and implies no more contradiction, than that it will rise. We should in vain, therefore, attempt to demonstrate its falsehood. Hume 1902, section 4, pt. I. Not surprisingly, David Lewis, 1986, a champion of many worlds metaphysics, was also a Humean. More on this in Chapter 8, Section 9, and Chapter 9, Sections 4 and 5. What a far cry from the thesis of the founders of modern science, all of whom swore by lawfulness, and sought constant laws and imperceptible mechanisms behind fleeting appearances. Remember, for instance, how Descartes, 1664, conceived of creation. God created matter, endowed it with the laws of motion, and withdrew henceforth from it. There can be no miracles in his world or in Galileo's, while anything can happen in Hume's. Whereas Galileo, Descartes, and Newton conceived of the universe as the self-winding clock, Hume saw it as a patchwork of sense impressions, which is also, presumably, the way primitive humans saw it. Scientists, unlike fiction writers and many worlds metaphysicians, distinguish clearly between real and conceptual possibility. A fact is really possible just in case its occurrence is compatible with the laws of nature, whether causal, probabilistic, or mixed. Otherwise it is really impossible except in fiction. Hence, scientists abstain from populating the universe with utterly fictitious entities. For, as Saki once wrote, when once you have taken the impossible into your calculations, its possibilities become practically limitless. Hume's worldview allows for miracles. In this regard, the justly celebrated sceptic is nearly as gullible as the pious religionists he was criticizing. The peculiarity of Hume's miracles is that they are secular, not religious. Presumably, he would have tolerated the belief that flying pigs might eventually be sighted, since they would be visible. Likewise, Hume might have encouraged 49. Research on the spontaneous unscrambling of eggs and on telepathy, since he would have doubted that any laws of nature could prohibit any such processes. It is tempting to speculate that he would have been taken in by many of the pseudo-scientific projects that went on in Jonathan Swift's Academy of Lagadugue. True, Hume famously characterized miracles as violating laws of nature.
However, he adopted the primitive conception of laws, namely, as regular successions of phenomena, such as the days-night sequence, with no hint of mechanism, and therefore devoid of explanatory power. This is exactly how primitive and ancient man conceived of natural regularities. Changes can be explained by primitive and ancient man very simply as two different states, one of which is said to come forth from the other without any insistence on an intelligible process, in other words, as a transformation, a metamorphosis. Frankfurt et al. 1949, 27. Thus, the phenomenalist program of accounting for invariable succession in a purely descriptive way, without inquiring into the mechanism of change, is in fact characteristic of a poorly developed culture rather than peculiar to the positive stage of mankind. Bunge 1959a, 73. The dynamical laws underlying the fluxus formae were beyond Hume's reach, both because they refer to facts behind appearances, and because their understanding requires some mathematics, which was above Hume's head. The Newton-Euler equations of motion, which Hume could neither read nor accept, are a case in point. They imply, in particular, that the spin of a frictionless spinning top, such as our planet, is a constant of the motion. In turn, this invariance implies that the regular succession of days and nights is necessary, not contingent, provided of course that no large meteorite strikes our planet. Consequently, that the sun will rise tomorrow is not just a shaky forecast on the strength of a mere inductive generalization from a finite number of observations, it is a feature of a necessary process ruled by laws. Hume excluded the supernatural only because it is inaccessible to the senses. The religious hypothesis, therefore, must be considered only as a particular method of accounting for the visible phenomena of the universe, but no just reasoner will ever presume to infer from it any single fact, and alter or add to the phenomena in any single particular. 1902, section 11. Religion is then at best useless to understand experience. However, phenomenalism does not protect us from lay superstition. Moreover, it places forces and atoms on the same level as gods and ghosts. Thus, ironically, phenomenalism kills both science and religion with a single stone. And for this reason, religious skepticism, Hume is regarded as a member of the Enlightenment despite his scientific skepticism. The same holds for Kant, to whom we turn next. 50. 8. The Counter-Revolution, Phase 3, Kant. It is well known that Kant started out as a realist, so much so that he wondered at the evolution of the nebulae, our galaxies, an original problem at the time. In fact, in 1755 he published his General History of Nature and Theory of the Heavens, which contained the valuable Kant-Laplace hypothesis, as well as the false conjecture that the solar system is stable because the gravitational attraction is balanced by a repulsive force that had no place in standard astronomy. Kant, like Hume, could not read Newton because he had no higher mathematics. However, his ambition to carve for himself an academic niche led Kant to imbibing Christian Wolff's speculative system. This was Kant's undoing, not because Wolff was a systematic philosopher, as has been said, but because he was a second-rate follower of the great Leibniz. In jettisoning Leibniz's metaphysical baggage, in particular his doctrine of monads, Kant is likely to have overlooked the great man's Nouveaux Essays, published in 1756 but written in 1704, and which in my opinion constituted a definitive refutation of Locke's empiricist epistemology. At the same time, Kant ceased to take an interest in natural history, and read only other philosophers, a custom that has been continued up to our days. Kant tells us that the reading of Hume awoke him from what he called his metaphysical slumber. What is less well known is that his phenomenalism was even more radical than Hume's. In places it was, indeed, ontological as well as epistemological, and therefore closer to Berkeley's. Recall the difference between the two varieties of phenomenalism, section 3. In fact, Kant, 1787, b. 724, asserted that Die Welt ist eine Summe von Erscheinungen, that is, the world is a sum of appearances. Allow me to repeat,
According to Kant, the world is made of appearances, that is, facts as perceived by some subject, not facts in themselves. Consequently, the existence of the world would depend on that of sentient beings. Shorter, no sentient beings, no universe. As Norbert Elias, 2475, put it, the Kantian subject of knowledge, shut up in his a prioristic shell, can never break through to the thing in itself, his is the homo clauseus. This fiction, central to individualism, has been pervasive in modern epistemology since Descartes, and in the social studies since about 1870, when it was used and popularized by the neoclassical microeconomists. It also occurs in the neo-Kantian philosophy of the influential sociologist Max Weber, though not in his scientific work, which is rigorously realist. However, Kant is hard to nail down, for he sometimes vacillates and backtracks. Indeed, on the same page B724 of his great work he admitted that there 51 are things in themselves, different from our experiences, and moreover that these are the foundations and causes of phenomena. As Torridi, 1967, 490, puts it, the effect is sometimes pathetic, and at other times nearly comic. In any event, when Kant admits the existence of things outside us, he does so reluctantly, in thinking that such admission must be taken on faith rather than on the strength of either experience or reason. Indeed, in the preface to the second edition to his first critique, Kant states that it is a scandal of philosophy, and of the general human understanding, that we must admit merely on faith bloß Aufglauben the existence of things outside ourselves, 1902, B36. But he is inconsistent, for elsewhere in the same work he tells us that space and time are in the mind, and, since he also asserts that all things are in space and time, it follows that all things are in the mind. 9. Kant concluded, neither nature nor God. A realist takes nature for granted, and he may ask how knowledge of nature is possible. By contrast, Kant, the subjectivist, asks how nature itself is possible, and answers in his Prolegomena A, 2002, 110 by means of the constitution of our sensibility. Consequently the laws of nature are just the laws of the connections of appearances, Ibid, 111. And the understanding does not draw its, a priori, laws from nature, but prescribes them to it, Ibid, 112, Kant's emphasis. If in doubt concerning the autonomous existence of nonsensuous things, consult Naterp, 1912, 94, one of the most prominent neo-Kantians. He assures us that for Kant the thing in itself is just a possible experience. Hence, no percipient, no thing, just what Berkeley had claimed. All this is not just a funny academic eccentricity, it is scandalous, as Kant himself declared, because the independent reality of the world is taken for granted by anyone, kitten or scientist, who endeavors to explore the world around himself, whether out of sheer curiosity or just to stay alive. The uncurious animal does not learn much, and has no great chances of noticing predators or potential mates, or of discovering food or shelter. In other words, whether or not we can prove the existence of the external world, we must recognize that such existence is no less than a precondition of survival and a presupposition of inquiry. However, let us return to the phenomenalist argument. Not being perceptible, space, time, and causation are further casualties of the phenomenalist reduction. In fact, Kant renders them subjective, yet necessary for experience and therefore prior to it. Indeed, according to him, we cannot experience sounds, smells, colors, or textures except against the background of those a priori categories. As well, Kant's scheme makes no 52 room for the laws of physics and chemistry, since these interrelate only primary properties of material entities. True, until some decades ago chemists still listed the organoleptic or secondary properties of chemicals, but only as practical indicators useful to identify them quickly in the lab.
Kant thus completed the radical counter-revolution in philosophy started by Berkeley and continued by Hume, except that, paradoxically, he called it a Copernican revolution. Note that Kant built his subject-centered philosophy 1 century after Newton's great work, which crowned the view of the world as the maximal clock. That was also over 1.5 centuries after Galileo and Descartes had argued that the world is composed exclusively of material things, and that the secondary qualities are in us, not in the external world. Little could Kant suspect that his subjectivism would be reinvented 2 centuries later in combination with sociologism, and under the name of social constructivism, by scholars who are unlikely to ever have read him, recall section 6. Nor is modern science the only victim of Kant's phenomenalist onslaught. Ironically, a further casualty is religion, whether theistic or deistic. Indeed, Kant asserts that the concept of a higher intelligence is a mere idea in blosse idee, b. 698. And again, the idea of a highest being and uppermost cause is only a mere something in the idea, of which we have no conception of what it is in itself, b. 707. Now, anyone who, like Kant, holds that God is an idea rather than a real being, is normally deemed to be an atheist. But Kant wavered between atheism and agnosticism, just as he wavered with regard to things in themselves. Indeed, earlier in the same book, b. 481 ff., he had stated that we cannot decide between the thesis that the world contains a necessary being, that is, God, and its antithesis. True, a few years later, in his Critique of Practical Reason, 1788, Kant held that belief in the existence of God is a postulate of practical reason, perhaps a way of saying that, even if God does not exist, it is prudent to pretend that he does. So, God entered Kant's philosophy through the service door, and never made it beyond the kitchen. Furthermore, Kant drew a firm line between knowledge and belief, in particular religious belief. The knowing subject, not God, was the center of Kant's world. Fichte took this blasphemy farther, he stated even more clearly that the self is the fountain of reality. And he added that the advantage of this view is that it guarantees the freedom of the will, provided, presumably, it is strong enough to will the creditor and the hangman away. Kant's religious scepticism did not go unnoticed in his own day. In fact, his sovereign, Friedrich Wilhelm II, King of Prussia, wrote him on October 1, 1794. 53. That the publication of such ideas constituted an abdication of his responsibility as a teacher, Kant 1913, 3, 48-9. Consequently, the king demanded from his subject that he abstain from any further utterances of the kind. And he threatened that, were Kant to persist, he would be subjected to disagreeable procedures. On October 12 of the same year the professor, being a civil servant, humbly promised his king to abstain from any further utterances about religion. Kant kept his word during that king's life. But he did not fool his contemporaries, some of them regarded him as the earliest German atheist. Only some historians of philosophy have had the impudence of holding that the adult Kant kept the fideism of his parents. 10. Phenomenalism restricts reality to a tiny portion of it, namely, the collection of appearances or pre-analytic experiences. Hence, it excludes most of the universe, either from existence, ontological phenomenalism, or from knowledge, epistemological phenomenalism. For instance, a phenomenalist will say that grass is green, whereas a realist will say that it looks green to us under white light. Besides, the realist can explain why this is so, namely, because grass reflects the light of all wavelengths except for those that cause the sensation of green in the primary visual system of a normal person. The realist can also ask certain interesting questions that the phenomenalist cannot, such as, at what stage in evolution did perception, as different from mere sensation or detection, emerge? And how is it possible for physics and chemistry to study a single noumenal, material, universe, so utterly different from the phenomenal? Furthermore, whereas the realist posits a single noumenal universe,
the phenomenalist must put up with as many phenomenal worlds as sentient organisms, unless he takes the solipsistic plunge. For example, he will say that what you see as a rabbit he sees as a duck, and such ambiguity cannot be resolved because nature contains neither animal, both are only in the mind. But of course the hunter, the farmer, the butcher, the cook, and the zoologist are bound to laugh at the phenomenalist's predicament. They know that there are real rabbits and ducks out there. An epistemological correlate of phenomenalism is descriptivism. This is the view that description is to be preferred to explanation, because, a, the latter goes necessarily beyond phenomena, and, b, there can be no law statements, because there are no objective connections and patterns, only constant conjunctions and regular sequences. According to this view, the generalizations 54. That night follows day, that drinking water quenches thirst, or that pricking hurts do not require explanation, they are well-confirmed inductions. By contrast, the realist takes such empirical generalizations as givens to be explained by higher-level laws involving transphenomenal concepts, such as those of field, gene, and nation. Since scientific research at its best is the search for objective laws, phenomenalism is inconsistent with science. Luckily, some phenomenalists failed to notice such contradiction, and produced good science. Fortunately, natural science had already attained maturity and prestige in mid-18th century, so that it was not crippled by either Kant's subjective idealism or Hegel's objective idealism. But the social studies were then still at an embryonic state, and they were seriously distorted by the idealist philosophies of Kant and Hegel, in particular Dilthey's. This can be seen, for instance, in the thesis, common to both methodological individualism and hermeneuticism, that the task of the social scientist is not to study social systems, such as families, schools, businesses, and polities, but to try and understand or interpret the values and intentions of unembedded and rational individual actors. For the stealthy convergence of hermeneutics and rational choice theory, see Bunge 2003a. A consequence of the idealist and individualist approach is of course that the large social transformations, such as industrialization, militarization, colonization, secularization, feminism, trade unionism, the concentration of capital, and globalization, are lost sight of. It is thus no coincidence that Max Weber, who passes for being the founder of modern sociology, missed all the great social transformations of his own time, such as the rise of imperialism and democracy. He also missed the rise of science and technology, both of which happen to be the cultural engines of modern society. Instead, he was obsessed by religion, charismatic leaders, and the legitimacy of political power. By contrast, historical materialism, once purged of dialectics, economism, and Laplacian determinism, has exerted a decisive and healthy influence on historiography, see Barraclough 1979, anthropology, see Harris 1979, and archaeology, see Trigger 2003b. There are several reasons for the superiority of the realist materialist over the subjectivist idealist view of society. One is that people have to work in order to eat, and they have to eat before they can think. Another reason is that, as Durkheim, 1901, 77, urged, the social facts must be treated like things, that is, objectively. A third reason is more subtle. Only one thing is absolutely sure in history, all that is particular is more or less doubtful, Tocqueville 1985, 351. For instance, we all know that the Great Depression occurred, but no one knows for sure what started it, much less what fateful decisions its main characters made. 55. In sum, anti-realism is not just false, it also hampers the study of reality. However, this has not prevented its diffusion, because the worth of a philosophy is seldom measured by its contribution to the advancement of knowledge. Indeed, anti-realism is, if anything, more popular nowadays than 3 centuries ago. However, this topic deserves a new chapter. 56. 3. Anti-realism today. Positivism, phenomenology. Constructivism. The standard histories of philosophy suggest that Kant's line died out with the now forgotten neo-Kantian philosophers, such as Lang, Wegener, Naderp, Cohen, Windelband, Rickert, Weber's philosophical mentor, Cassirer, and Bosch, Carnap's thesis supervisor. I submit that Kant's subjectivism was also a major source of several other schools, some of which have been far more influential than orthodox neo-Kantianism. Those schools are the radical subjectivisms of Fichte and Schopenhauer, the classical positivist doctrines of Comte and Mill, Nietzsche's combination of pragmatism and relativism, pragmatism, or instrumentalism, from William James, but not Charles S. Peirce, and John Dewey onwards, Wegener's fictionism, Husserl's phenomenology and Schutz's phenomenological sociology, logical positivism from Mach to the Vienna Circle and beyond, and the constructivism relativism that Kuhn and Feyerabend revived and made fashionable in the 1960s. Furthermore, Kant, along with Hegel, exerted a strong influence on the hermeneutic movement, which includes Dilthey, Husserl, Heidegger, Gadamer, Habermas, Ricoeur, and Derrida among others, see Müller-Volmer, ed. 1989. This movement exploited Kant's dichotomy between the natural and the cultural. In particular, Dilthey wanted the social studies to shift focus from objective social facts to the actors in them, from trade to traders, from war to warriors, and from the polity to politicians. This is why the hermeneuticists hold that the cultural, social, world is to be understood very differently from the natural one, namely, through the Verstehen, understanding, interpretation, of individual actions. This peculiar operation would consist in grasping the meaning, intention, goal, of behavior and texts. Hence, the study of social life would be a Geisteswissenschaft, that is, a science of the spirit, or cultural science. Whence, too, the indifference of hermeneuticists to everything lying outside the word. 57. Meaning interpretation triangle. This is how the environment, manual work, scarcity, poverty, oppression, segregation, and war fall beyond the purview of the hermeneuticist. Only das Höhere, the higher, is worthy of the attention of the Herr Professor. Leave the daily life miseries to the lesser beings. More in Bunge 1996. In sum, Kant's philosophy spawned three main lines: Neo-Kantianism, classical positivism, which eventually gave rise to logical positivism, and German Romantic philosophy, which in due course engendered philosophical hermeneutics, see Figure 3.1. All of the above-mentioned philosophies rejected the hylorealist theses that the external world is material and exists by itself, and that science can grasp reality. However, of all the philosophies stemming from Kant's, positivism was the only one that made no concessions to irrationalism, and that proclaimed its love of science. Moreover, some of the positivists, such as Mill, Mach, Pearson, Duhem, Bridgman, and Bauer, were outstanding scientists who left far deeper marks on science and its philosophy, and even on the ruling worldview, than did the self-styled neo-Kantian philosophers, who, except for Ernst Cassirer, never reached the public. Most of this chapter will be devoted to renalising logical positivism, also known as logical empiricism, neo-positivism, or just positivism. A scientific realist like this writer can engage in a fruitful dialogue with a positivist because both share two important principles, those of rationality and scientism. The former principle states that all ideas are rationally debatable as long as they are fairly clear, and the second holds that the best way to study facts, whether natural or social, is by using the scientific method. A good reason for re-examining positivism is that it is still the explicit philosophy of most experimental scientists. Indeed, when in a didactic mood, they claim that all research is data-driven. They forget of course that they do not pile up data mindlessly, but use always more or less explicit hypotheses. Figure 3.1. Kant. Hermeneutics, Dilthey, Husserl, Heidegger. Neo-Kantianism, Cohen, Naderp, Cassirer. Logical positivism, Schlick, Carnap, Reichenbach. German Romanticism, Hegel, Fichte, Schelling, Classical Positivism, Comte, Mill, Mach. 58. Ordinarily, data are sought or produced in the light of some hypotheses, and these are in turn checked by pertinent evidence. So, neither data nor hypotheses have the last word. Another reason for re-examining positivism is that it is often confused with realism or even with materialism. In fact, roughly between the 1870s and the 1930s, what passed for positivism was actually a jumble of positivism proper, scientism, evolutionism, Spencer's or Haeckel's rather than Darwin's, materialism, naturalism, and energetism. Anyone who admired science and rejected organized religion called himself a positivist. All this was true of Mexico, Rio de Janeiro, and Buenos Aires, as well as of London, Paris, and Berlin, see Biagini, ed. 1985. All this changed in 1927 with the foundation of the Vienna Circle, which reclaimed the heritage of Hume and Mach. Kant was unmentionable because of his blunders over mathematics and science. But his phenomenalism was adopted wholesale. The Circle's members, the logical positivists, claimed to have overcome the realism/anti-realism and the materialism/idealism dilemmas. In particular, they held that the question of the autonomous existence of the external world was a pseudo-problem, Schlick 1959. Little did they suspect that such epistemological agnosticism would be resurrected by the postmoderns towards the end of the century. Thus, the self-styled postmodern psychologist Gergen, 2001, 806, proclaims that arguments about what is really real are futile. However, in practice most logical positivists sided with idealism, since they conceived of physical things as either possibilities of sensation or logical constructions out of percepts, example Carnap 1967. Later on, under Wittgenstein's influence, they adopted glossocentrism, or linguistic idealism. Thus, Carnap, 1950b, 23, held that to accept the thing world objective reality means nothing more than to accept a certain form of language. That is to be talked about, or to play a language game. Ironically, Heidegger, 1987, 11, whom Carnap rightly despised, held a similar view, that the word is the abode of being. Moral, falsity plus logic, as in Carnap, or minus logic, as in Heidegger, equals falsity. The best known features of logical positivism are its empiricist semantics and epistemology, the advocacy of logical analysis, an unrequited love of science, and an allegedly anti-metaphysical stand. Besides, the logical positivists, like Kant, attempted to combine empiricism with rationalism. However, it is arguable that Kant combined the wrong half of empiricism, namely phenomenalism, with the wrong half of rationalism, namely a priorism. By contrast, logical empiricism retained phenomenalism but joined it with the best component of rationalism, namely modern logic. Thus, whereas Kant's writings were 59. Plagued by obscurities and inconsistencies, as we saw in the previous chapter, those of the logical empiricists constituted the clearest and most consistent philosophical works of their time, particularly in comparison with those of their main rivals, the intuitionists, phenomenologists, existentialists, Thomists, neo-Hegelians, and dialectical materialists. This is why one can learn far more from debating with them than from criticizing their rivals. Because of the enduring influence of the logical positivists, engaging them in debate is not a mere academic exercise. Let a couple of examples suffice. The first will be the fiasco of the American intelligence agencies at the dawn of this century, who spent many millions to no avail because they did not know what to do with their huge pile of data, they framed no hypotheses based on serious social studies, and consequently they did not test any either. As Charles Darwin stated, to discover anything interesting and plausible one must make some conjectures and put them to the test. But to make reasonable conjectures concerning political facts, such as the production of weapons of mass destruction or the planning of terrorist attacks, one must use the ABC of social psychology and political science in addition to gathering intelligence, which is mostly unconfirmed gossip anyway. Consequently, effective anti-terrorist work requires the cooperation of spies with scientists on a daily basis. Our second example is the quantum theory. It is often forgotten that empiricism lurked behind the standard or Copenhagen interpretation of the mathematical formalism of quantum mechanics, particularly from 1935 on. Consequently, a realist reinterpretation of this theory must be preceded by an effective critical analysis of logical positivism. And such analysis must not ignore the phenomenalist metaphysics of logical empiricism, which is usually overlooked although it is no less than the root of its epistemology. After all, epistemology may be regarded as an application of ontology to the cognitive process. Tell me what there is, and I'll tell you what and how we can get to know it. If the world is either an idea or a mass of appearances, just look inward, but if it is concrete, go out and explore it, and if all we can do is perceive, just record your sense impressions, but if you can also think, be prepared to think very hard. 1. Logical positivism. The original name of the Vienna Circle, 1929-36, was the Ernst Mach Verein, c. Example Fagel 1943, Kraft 1953, and Ayer, ed. 1959. This learned society was constituted by philosophers such as Moritz Schlick and Rudolf Carnap, scientists such as Philipp Frank and Otto Neurath, and mathematicians such as Karl Menger and Richard von Mises. Its declared purpose was to update and 60. Publicize the positivist philosophy of Ernst Mach, who had regarded himself as an heir to Hume and Kant with regard to phenomenalism. Mach had been a distinguished experimental physicist and physiological psychologist, as well as a popular historian and philosopher of science. He was proud of having had invented the economy of thought, the quaint principle that the aim of science is not to understand reality but to spare us experiences by their reproduction, colligation, and anticipation in thought. Mach 1910, 238, 1942 1893, 578. Mach did not care to have his name associated with the classical positivists Auguste Comte and John Stuart Mill. But in fact he took over their phenomenalism and descriptivism, as well as their rejection of metaphysics and religion. In particular Mill, following Kant, had defined a thing as a possibility of sensations, an idea that agrees with the popular metaphysics according to which factual existence is the same as its ordinary knowledge criterion, namely, the possibility of seeing, touching, smelling, and the like. Mach, 1914, adopted Mill's definition of a thing, which he regarded as a stable complex of elements, where element was a synonym for sensation and his substitute for the physical atom. He warned that thing is an abstraction, the name of a symbol, for a compound of elements sensations from whose changes we abstract, and that the concept of a thing in itself is an absurdity, for sensations are not the signs of things, but, on the contrary, a thing is a thought symbol for a compound sensation of relative fixedness. Ibid. 580. He also adopted Kant's view that nature is composed of sensations as its elements. Mach 1942 1893, 579. In a famous book, Lenin 1908 rightly criticized Mach and others for having revived Berkeley's subjective idealism, which, regrettably, he did not attempt to refute. Nearly half a century later Popper 1953 confirmed Lenin's diagnosis: Mach was a Berkeleyan. True, the head of the Vienna Circle Schlick 1959-85 rejected this characterization, and claimed that Mach and his heirs took no sides in the realism/subjectivism controversy. But he did not quote chapter and verse to make his case. Mach did not explain how his phenomenalism squared with his own pioneering study of bullets moving at supersonic speeds, which he was the first to photograph. Surely neither the bullets nor the shock waves they generated could have been sensations, not only because they did not occur in anyone's brain,
but also because they could not be seen directly. To be sure, the moving bullets could be touched, but the ensuing sensation would have been a datum for the surgeon, not the physicist. Nearly all the members and affiliates of the Vienna Circle, particularly Rudolf Carnap, Hans Reichenbach, and Philipp Frank, adopted Mach's phenomenalism. This earned them an unexpected if unwelcome and silent ally, the 61. Inquisition. Indeed, Reichenbach, 1951, 107, held that the Copernican system differs from Ptolemy's only in that it is another mode of speech. Thus, the heliocentric and the geocentric models of the solar system are equivalent descriptions, since at the time both accounted equally well for the empirical evidence. And Frank, 1957, 352, held that the Copernican theory was mathematically simpler and had the greater heuristic value. Truth was not in question. Cardinal Bellarmino, Galileo's accuser, must have chuckled in Hades. Two reasons have been adduced in favor of the said equivalence. The first is that all the coordinate systems are equivalent. In particular, a rectangular coordinate system centered in the Sun is equivalent to a spherical coordinate system centered in the Earth. But such geometric equivalence is irrelevant, because all motions are relative to reference frames, not coordinate systems. Reference frames are physical things, and coordinate systems mirror only some geometric features of reference frames, Bunge 1967b. This point is important because, a. the Galileo and Lorentz transformations relate reference frames, not coordinate systems. The former can move, since they are physical entities, whereas the latter cannot, because they are mathematical objects, and, b. the Earth, being accelerated, is not an inertial system. That is, the equations of mechanics, whether classical or relativistic, are not satisfied exactly relative to our planet. The second reason given for the alleged equivalence was that, since all motion is relative to some reference frame, it makes no difference whether this frame is the Sun, heliocentric system, or the Earth, geocentric system. But it does. In fact, the less massive of two nearby bodies is forced to orbit around the far more massive one because it is the source of the more intense gravitational field. Further reasons in Bunge 1961, 139-40. In short, the planetary orbits are really, objectively elliptical or nearly so. The metaphysical phenomenalism advocated by Mach was not systematic. The first attempt to build a phenomenalist theory was Whitehead's, 1919. It was so unsuccessful that its author soon turned to his process metaphysics, which was closer to Hegel's than to Mach's. The next effort in the phenomenalist project was Carnap's logical construction of the world, 1967-1928. The basic tenet of this system was that in principle all physical objects can be reduced to psychological ones and conversely, Ibid, 92. Amazingly, this principle was a generalization from a single example, a wrong one. Consider. Statements about physical objects can be transformed into statements about perceptions, i.e., about psychological objects. For example, the statement that a certain body is red is transformed into a very complicated statement which says roughly that, under certain circumstances, a certain sensation of the visual 62. Sense, red, occurs, Ibid. Carnap did not realize that he was just expanding a phenomenalist statement about seeing red. If psychological and physical objects and statements were indeed equivalent or mutually reducible, why prefer the physicalist phenomenalist translation to the converse one? Presumably, just attachment to the empiricist tradition. But one of the reasons advanced by the founders of modern science for the converse preference was that primary properties are subject-independent, and thus lend themselves to impersonal universal generalization, recall Chapter 1. In any case, scientific theories do not contain concepts denoting qualia unless they happen to concern qualia, in which case they belong in psychology, not in physics, chemistry, or biology. Consider for example the following two elementary mini-theories or theoretical models, the classical model of a linear oscillator, and the standard model of a direct current metallic circuit with resistor R and inductor L connected in series. Although the things described by the two models, springs and circuits, may be perceptible, the predicates employed to describe them denote primary properties, not qualia. The measurement of M, K, W, V, I, and R requires instruments that embody indicator hypotheses, such as the relation between current intensity and the angle of a pointer in an ammeter. Thus, the premises of the preceding theoretical models do not entail observations, contrary to the popular philosophical accounts of scientific theories, such as Van Frassen's, 1980. We shall return to this subject in Chapter 7. 4 decades after Carnap's unsuccessful attempt to eliminate theoretical terms in favor of observational ones, Donald Davidson, 1970, one of the last. Classical linear oscillator RL circuit MD2X/DT2 equals, KXVLDI/DT equals RI. X equals A cos omega t, omega equals square root, K/M, I equals V/R plus AE, R/L, T, where X equals position, V equals impressed potential difference, M equals mass, K equals tension, I equals current intensity, A equals amplitude, omega equals frequency, R equals resistance, L equals self-inductance, T equals time. 63. Positivists turned Carnap's alleged proof into a cornerstone of his popular philosophy of mind. To prove that mental and physical events are mutually exchangeable, he chose a slightly different example. Two stars in distant space collide with one another at the same time that Jones notices that a pencil starts to roll across his desk. The collision has now been picked out by a mental description and must be counted as a mental event. 1970, 211. Notice the strategy. Discuss a single case in ordinary knowledge terms, and leap twice in succession, first to an outrageous generalization: all physical events can be described in mental terms and vice versa, then from common sense to science, physics and psychology. 2. World-making. At first sight, positivism and post-Kantian German idealism have little in common. The former is pro-scientific and clear, whereas post-Kantian German idealism is both unscientific and often hermetic to boot. However, since both have the same sources, namely Berkeley, Hume, and Kant, their coincidences should come as no surprise. In fact, both factions coincided in rejecting realism and materialism, although they fought these in different fields. While the positivists specialized in the natural sciences, the hermeneuticists focused on social studies. In particular, while the positivists stressed phenomenalism and criticized atomism, the hermeneuticists emphasized the role of ideas in social life at the expense of macro-social facts and the so-called material factors, such as natural resources and work. So, each faction blocked the advancement of knowledge in its own way, the positivists by banning microphysics or distorting its philosophical import, and the hermeneuticists by rejecting the macro-social studies, or by attempting to reduce them to the interpretation, verstehen, of the intentions of individual actors. The point of entry of idealism into the social studies is the ontological thesis that there is no such thing as society, there would be only individuals, and these act freely following their own interests, beliefs, and intentions. This ontological thesis generates methodological individualism. This is the thesis that the goal of the social studies should be to find out how social facts emerge exclusively from individual choices and actions. The individualist project sounds attractive by comparison with the holist thesis that individuals are but pawns of higher instances, such as God, destiny, nation, race, church, or party. But the project is unrealistic and even logically untenable, because social roles cannot be defined except by reference to social systems. For example, a warrior is, by definition, someone who is expected to fight in a war. And in 64. Turn wars, far from being intimate affairs, consist in armed clashes between groups of individuals characterized by super-individual traits, such as imperial or colonial, oil-rich or oil-hungry, right-wing or left-wing, and so on. As with social roles,
So with social ranks. For instance, the landowning class is not just the collection of persons who possess land cultivated by others, those persons are also backed by a state that enforces that privilege. And a state or government is not reducible to individual items or features, it is a social system characterized by emergent properties, such as having the monopoly on taxation and legal violence. And methodological individualism denies the very existence of social systems, supra-individual entities that have emerged in the course of history to overcome the limitations of individuals. Thus, the individualist idealist anthropologist, economist, sociologist, political scientist, or historian will attempt to interpret, hypothesize, individual actions exclusively in terms of personal beliefs and intentions. In particular, if he is a rational choice theorist, he will focus on subjective utilities and subjective probabilities. Consequently, he will either miss or seriously misunderstand all the macro-social events and processes that have shaped our societies, such as capitalism, imperialism, nationalism, war, democracy, secularism, socialism, fascism, feminism, technology, and science. Further criticisms in Bunge 1996, 1998, and 1999. Max Weber, one of the two fathers of modern sociology, is a case in point. Indeed, he missed all the above-mentioned macro-social developments, while rightly and forcefully insisting that the social sciences should be objective, see Bunge 2005a. This incongruence was an inevitable consequence of Weber's adoption of Dilthey's philosophical hermeneutics, which had been at once idealist and individualist. This approach can at best shed some light on the products of culture, such as texts, while keeping the cultural communities and their societies at large in the dark. In general, most of reality is bound to escape the individualist idealist, and this for several reasons, because reality is a system of systems, see Bunge 1979a, ideas have no existence except in brains, and every thinking person is a component of several social systems that have preceded him. A moral of Weber's failure to understand the society he lived in is that idealism stunts realism. Realism can flourish only when allied with materialism, recall Chapter 1. Phenomenology constitutes an even more drastic retreat from reality. Its founder reproached Galileo and Descartes for distinguishing primary from secondary properties, and for regarding nature as devoid of mental features, Husserl 1970-1936. Previously he had stated that an actual object belonging to a world or, all the more so, a world itself, is an infinite idea, an idea related to infinities of harmoniously combinable experiences, a complete 65. Synthesis of possible experiences, Husserl 1960-1931, 62. In short, the world would be subject-dependent, and we would get to know it through ordinary experience rather than through experiment, analysis, and modeling. Characteristically, Husserl offered no evidence for his subjectivist extravagance, he regarded it, like all of his opinions, as self-evident a priori. Nor did he mention any of his sources, in particular Berkeley, Kant, Fichte, Mill, Mach, and Dilthey. Originality and concern for evidence are not precisely the trademarks of modern idealism, in particular phenomenology. Instead, obsoleteness, dogmatism, hostility to science, and opaqueness are, see, example Kraft 1957. In the previous section we recalled a parallel attempt to reduce the world to what Mach had called a complex of sensations, namely, Carnap's logical construction of the world, 1928. This work was generally ignored until Nelson Goodman unearthed and updated it with the help of Lesniewski's mereology. His structure of appearance, 1951, is a formally more refined system based on the assumptions that the stream of experience is both structured and constituted by indivisible, atomic, qualia. Still, unlike Carnap, Goodman admitted at that time that the problem of accounting for the physical world upon a phenomenalist basis was still open, and he offered no clue for its solution. Yet, he was unshakable in his faith that the said reduction would eventually be accomplished, Ibid. 304-6.
After trying in vain for 3 decades, Goodman adopted an easier strategy, that of arbitrary world-making or subjectivist constructivism, Goodman 1978. Don't worry over how to discover new extrasolar planets, flying dinosaurs, missing links, or the organ of consciousness, since we are free to imagine them. When told by a fellow philosopher that we cannot make stars the same way as we make bricks, Goodman, 1996, 145, became more cautious. The world making mainly in question here is making not with hands but with minds, or rather with languages or other symbol systems. Yet when I say that worlds are made, I mean it literally. In other words, when pressed he admits that the worlds he claims to be able to make are symbolic systems. Still, Goodman refuses to distinguish them from the only real world there is. Now, if someone claims to know how to make a star, one is entitled to tell him, show me, or shut up. One is also entitled to ask, why should the taxpayer be made to pay for astronomical observatories, if we can have any desired stars constructed by philosophers? Goodman seems to have been the latest, if unsuccessful, attempt to reduce primary properties, or physicalist predicates, to secondary properties, or phenomenalist predicates, or qualia. If his attempt failed even at the ordinary knowledge level of massive bodies such as chairs, is there any reason to expect 66. That it might succeed for quanta or galaxies, cells, or nations? Hint: start by trying to reduce some classical law statements, such as Fourier's for heat conduction, or Maxwell's for electromagnetic induction. Warning: don't forget to include the translation of such elementary expressions as sin wt into sense data. Hint: don't waste your time. Besides the individualist constructivism of Berkeley, Kant, Fichte, Schopenhauer, Avenarius, Mach, Husserl, Carnap, Goodman, and a few others, there is collectivist subjectivism, or social constructivism relativism. This doctrine, fashionable among sociologists of knowledge since the mid-1960s, holds that all facts, whether social or not, are social constructions, that is, products of social groups. See example Fleck 1979, Latour and Wilger 1986, H.M. Collins 1981, Barnes 1983, Norsetna 1983, Norsetna and Mulcahy, eds 1983, and Fisk and Schroeder, eds 1986. There is of course some truth to social constructivism, namely, the tautology that all human social facts, from greeting and trading to child rearing and warring, are social facts. But nobody starts from scratch, and nobody constructs social reality by himself. To be sure, humans make themselves, and invent, maintain or repair social systems, but, as Marx famously added, they do so starting from a pre-existing social reality and with the help of others. Only philosophers and inmates in a lunatic asylum think that someone can create reality rather than just alter it. Correction: a senior advisor to President George W. Bush told a veteran journalist that guys like him were in what we call the reality-based community. That's not the way the world really works anymore. We're an empire now, and when we act, we create our own reality. We're history's actors, and we, all of we, will be left to just study what we do. Susskind 2004. The claims of the social constructivists are just as grandiose. For example, according to Fleck, syphilis was constructed by the medical community. Latour and Wilger claimed that TRF, a certain brain hormone, was constructed by its discoverers. Pierre Bourdieu held that the visible differences between the masculine and feminine sexual organs are a social construction. The thesis of the anti-psychiatry movement is that all mental illnesses are inventions of psychiatrists, and some feminist philosophers have maintained that the scientific laws, and even the concepts of objectivity and truth, are only tools of male domination. Of course, there is no evidence for any of these egregious claims. But there is evidence for the hypothesis that they originated in the confusion between fact and idea, or thing and model, typical of magical thinking. See criticisms in Bunge 1991 and 1992, Gross and Levitt 1994, Sokol and Brickmont 1998, and Brown 2001. In short, social constructivism is blatantly false, the overwhelming majority. 67. Of facts are independent of any minds, and ideas occur only in individual brains. This is not to deny that all thinkers, however original, are intellectually indebted to other people. Nor is it to deny that all the social systems and the norms that regulate them are constructed by social groups, albeit not always consciously. The point of realists is that, although all organisms, not just humans, construct their niches, they all employ materials, and abide by laws, that pre-exist them. 3. Phenomenalism and quanta. John Dalton put the atomic theory to work in chemistry one generation after Kant wrote his masterpiece. Most chemists embraced it eagerly because it seemed to explain the chemical compositions and reactions. By contrast, most physicists resisted atomism during most of the 19th century because there had been no direct evidence for the existence of atoms before 1905. An additional reason was that physicists were eager to toe the positivist line traced by Auguste Comte and John Stuart Mill, and retraced by Ernst Mach, Pierre Duhem, Karl Pearson, and Wilhelm Ostwald, a line that at the time seemed to demarcate science from non-science, in particular religion and metaphysics. The line in question was of course that enclosing the directly observable facts. In other words, the claim was that science deals only with the observable. The attempt to accommodate modern science in this Procrustean bed gave rise to a funny paradox. Between 1925 and 1935, Heisenberg, 1947, Bohr, 1958, Born, 1949, Weizsäcker, 1951, Pauli, 1961, and a few other eminent physicists paid lip service to the phenomenalist tenet, at the same time that they were building the first successful, true, theories about such transphenomenal things as electrons, atoms, and photons. Indeed, they claimed that their theories dealt exclusively with observations. Thus, Heisenberg's foundational paper of 1925 announced the construction of a quantum theory based exclusively upon relations among quantities that are observable in principle. But observations, even when automated, involve observers at some point. And one cannot observe electrons and the like, one can only observe macrophysical manifestations of microphysical events, such as the clicks of a Geiger counter. And physics does not account for perception anyway. Besides, one may ask naively, observations of what? But one would then be rebuked, for that question presupposes the existence of things observed and distinct from the means of observation, as is the case of the atoms in the experimenter's brain or in the sun's interior. Phenomenalism was not restricted to microphysical entities, Bohr, Heisenberg. 68. And their followers stated confidently that macrophysical things, such as street cars, result from repeated observations. Even half a century later we were told that quantum physics has taught us that the moon is not there when nobody looks, Merriman 1981, 405. The universe as a whole would be in an even worse predicament, since there can be no observers external to it. But if so, why do cosmologists persist in exploring it? And what do the latter-day Berkeleyans and Kantians make of the recent discovery that most of the matter in the universe is dark, that it is there but cannot yet be studied? Did the founders of quantum physics practice the subjectivism they preached? Of course not. In fact, when calculating energy levels, transition probabilities, scattering cross-sections, and the like, all quantum physicists assume tacitly that these are objective properties of quantum mechanical objects, so much so that no reference to the measurement device, much less to the observer's mind, occurs in their calculations. That this is so, that the basic laws of quantum mechanics and their main applications do not refer to any measuring instruments, let alone observers and their mental states, is best shown by axiomatizing the theory, Bunge 1967b, Perez Bergliafa, Romero, and Vucinic 1993, 1996.
The reason is that, when working in an axiomatic theory, one is not allowed to smuggle in extraneous items in mid-course, as is done when interpreting eigenvalues as possible measurement outcomes rather than as sharp values of objective properties, statistical variances as disturbances due to the measurement device rather than inherent fuzziness, and so on. The axiomatization of quantum mechanics shows that the assumptions of this theory, like those of any other scientific theory, are of two kinds, whereas some are mathematical formulas, the rest are semantic assumptions, the old correspondence rules, stipulating the factual items that those symbols stand for. And such factual items are things in themselves, such as electrons, and their primary properties, such as energy. For instance, the axiomatization in question, in exhibiting that quantum mechanics is really about quantum objects, helps interpret correctly Heisenberg's so-called uncertainty relations. These inequalities state that the variance of the position is inversely related to that of the momentum. Actually, the formulas in question involve the square root of the variance, that is, the mean standard deviation. Heisenberg himself launched in 1927 the popular interpretation of these variances as measuring the disturbances caused by the observation device. Ironically, most positivists and naive realists agree on this point. Positivists overlook the fact that such interpretation presupposes that the micro-object in question has at all times a sharp position and a sharp momentum, while they should be saying that both properties are generated by the act of observation. And the naive realists forget that quantum mechanics does not contain classy 69 cal position and momentum variables with sharp values at all times. In other words, formulas such as xt equals f t and p t equals g t belong in classical mechanics, not in the standard quantum theory. Only Bohm's reformulation of the theory does contain such classical variables on top of the quantum mechanical ones. Another point overlooked by the two conflicting parties is that Heisenberg's inequalities are derived in all generality, without assuming anything about measuring instruments. Indeed, these are not mentioned in the premises that entail the formulas in question, see Bunge 1967b. The truth is that the Heisenberg inequalities show that, in general, the position and momentum of microsystems are blunt rather than sharp. In other words, quantons are smeared both spatially and dynamically. The limit cases, where one of the two variances is nil, point-like localization and infinite plane wave, are extreme idealizations. At all events, the general quantum theory describes noumena, that is, physical things, not phenomena, that is, mental processes. Moreover, when a measuring instrument is involved, the general theory proves insufficient precisely because it is general. Hence, it must be enriched with assumptions concerning the apparatus's mechanism, such as condensation of water droplets around ionized particles. And, because every apparatus is macrophysical, it is describable largely if not wholly in classical terms, as Bohr, 1958, rightly insisted. Even Heisenberg, 1958-55, admitted eventually that certainly quantum theory does not contain genuine subjective features, it does not introduce the mind of the physicist as a part of the atomic event. 2 decades later, Heisenberg told me that he, like Newton, had attempted to explain things, not just to account for data, Bunge 1971. So, Planck, 1933, Einstein, 1958, and Schrödinger, 1935, had been right in criticizing the positivist interpretation of quantum mechanics. Where some of them went wrong was in their nostalgia for classical physics. On this point, Einstein was wrong and Bohr right. Realism does not imply classicism, Bunge 1979c. To understand why most of the creators of the quantum theories could fall for such a rudimentary philosophy as phenomenalism, it must be admitted that there is method in their madness. The point of method is that the elicitation and measurement of typical microphysical events, such as the artificial transmutation of elements, requires elaborate experimental devices, though not more so than the ones involved in optical measurements.
So, it is true that, as Leon Rosenfeld, 1953, once said, the experimenter conjures up the quantum facts. But Mother Nature does the same all the time and without philosophical obfuscation. Thus, the quantum object and the measuring instrument are intimately 70. Coupled to one another, as long as an experiment is running. And, since measuring instruments are set up and handled by experimenters, one can speak of the object apparatus observer supersystem. However, contrary to the Copenhagen dogma, this is not an indivisible whole, connection does not entail indistinguishability. Indeed, one can adjust an instrument without poking into the experimenter's brain. Besides, the vast majority of quantum facts, such as nuclear reactions, atomic collisions, and chemical reactions, occur all the time outside laboratories. Furthermore, every quantum observation bears on a quantum object, such as a photon, not on an apparatus, let alone on an experimenter. For instance, physicists measure the wavelength of light emitted by an ionized gas, not its effect on the experimenter's brain. Finally, experiments can be automated, allowing the experimenter to go home for the night and thus cease influencing the object. See Figure 3.2. Let us go back to the reason that might be invoked for refusing to talk about quanta in themselves. Bridgman, 1927, 150-3, a superb experimentalist and the systematizer of operationalism, reasoned as follows with regard to light. He started by reminding us, correctly, that we do not see light, all we can see are things lighted. In particular, we see light emitters, such as fires and lamps, and light detectors, such as photoelectric cells and eyes. Hence, Bridgman. Object. Recorder, example observer. Signal. Apparatus. Disturbing reaction. Figure 3.2m. The measured object, the measuring apparatus, and the recording device, whether observer or automated, are interconnected but distinguishable. So much so, that either component can be disconnected from the other two. 71. Reasoned, to speak of light traveling between source and sink must be recognized to be a pure invention, Ibid, 153. Bridgman overlooked the fact that Maxwell's equations describe the propagation of light in intermediate space, so they would be violated if they were interrupted arbitrarily in mid-space. Furthermore, these equations contain the universal constant c, which happens to denote the velocity of light in a vacuum, a quantity that Roemer first measured in 1676. Clearly, if only phenomena are allowed to exist, one is forced to give up any hope of understanding how the light emitted by a star, or even by a nearby electric bulb, can reach us, even if the light source ceased to exist millions of years ago. Moreover, as Einstein stressed repeatedly, the realization that electromagnetic fields exist on their own, rather than riding on the mythical ether, and on par with bodies, constituted a milestone in the history of science, since it coincided with the definitive breakdown of the mechanical worldview. The same year that Bridgman's book appeared, Heisenberg published his famous if flawed paper on the gamma-ray microscope, where he stated that electrons do not have continuous trajectories, but jump from one observation to the next, an instance of the operationalist confusion of evidence with reference. This led Hans Reichenbach, 1944, the prominent neo-positivist, to writing about interphenomena, that is, whatever is alleged to lie between observable events. He claimed that taking interphenomena seriously leads to the so-called quantum mechanical paradoxes, such as that an electron interferes with itself after passing through a double-slit device. Obviously, Reichenbach did not wonder how it was possible for photons to travel undetected all the way from the sun to his eyes. Reichenbach, like Bridgman and Heisenberg before him, overlooked the law statements, such as those involved in calculating time travels and scattering cross-sections, that describe the uninterrupted travel of a particle between source and target. If we admit these law statements as at least approximately true, we must also admit that interphenomena are just as real as phenomena. And unless we admit that there are real facts between observations,
we cannot hope to understand how a television set works, since what we see are flashes caused on the screen by the impacts of the electrons emitted by the cathode ray tube behind the screen. The TV repairmen know this, since they earn their living looking behind screens. Realism, then, is not optional for the experimental physicist and the electronic engineer. They count on the existence of electrons and photons and things even while they are not being measured. Nor is it optional for the managers of particle accelerators and other large devices, who must find billions of dollars to fund research into such problems as weather strings. 72. Gravitons and Higgs bosons exist. Only a philosopher could persuade himself that one may dismiss the issue of realism, Fine 1986, Teller 1995, which sounds like the hermeneuticists' denial that there is anything outside of texts. Who but scientists are expected to find out what there is? And who but philosophers of science can be expected to dig up the philosophical presuppositions of the scientific exploration of reality? In sum, the subjectivist components of the Copenhagen interpretation of quantum mechanics are inconsistent with the way the theory is actually being applied and tested. Those components are just philosophical contraband. This is why they are cheap and hard to control. More in Bunge 1959b and 1973, Jammer 1966, and Beller 1999. 4. Ptolemy Redux. The well-known philosopher Bas van Frassen, 1980, embraced phenomenalism, claiming that every successful scientific theory saves the phenomena, that is, correctly describes observable facts. The phrase "to save the phenomena" had been coined nearly 2 millennia earlier by the great astronomer Ptolemy. Duhem, 1908, adopted it as the devise of his own brand of phenomenalism, which he regarded as the nucleus of the qualitative physics that he advocated as a good Christian and hater of Galileo, whom he once contemptuously called le mécanicien florentin. But of course there is no hint of phenomena, appearances to a sentient being, in any of the formulas of the quantum theory, any more than in any other physical theory. None of them contains variables denoting secondary properties or qualia. A weaker empiricist claim is that the evidence for microphysical theories is constituted by perceptible macrophysical features such as angles of pointers of measuring instruments and tracks in cloud chambers. This argument is wrong because it ignores the fact that all such evidence is indirect. It works only thanks to hypotheses that bridge microphysical events, such as charged particle trajectories, to macrophysical ones, such as the condensation of water molecules resulting from the ionization caused by those particles. True, many textbooks in quantum theory discuss such experiments as double-slit diffraction and the Stern-Gerlach one. But they describe them in sketchy terms and with few if any formulas, glossing over the fact that in both cases one needs to read the end results, such as the impacts on a detecting screen, with the help of indicator hypotheses that bridge the micro to the macro level. More on indicators in Chapter 7, Section 9. Interestingly, the places of evidence and reference are often reversed in other sciences. For instance, what is observable in the social sciences is usually 73. Individual behavior. Thus, the data on GDP, income inequality, and birth rate are aggregates of individual data. In other cases, macrosocial data, such as documents about fortresses, roads, and tombs, point ambiguously to features of unobservable individual lives. In the historical sciences, from evolutionary biology to archaeology, the only observables are such things as fossils, arrowheads, hearths, earthworks, and tracks, which are just traces left by the referents of those sciences. To state that the theories in these disciplines correctly describe what is observable is a gross distortion. In this case, what is observable is only evidence for hypotheses concerning unobservable referents. For example, paleontology describes extinct organisms, whose fossil remains are described by a different discipline, namely taphonomy. In all cases, data never speak for themselves, they have to be interpreted via indicator hypotheses, such as those linking barometer readings to atmospheric pressure, or the number of new construction permits to economic prosperity.
Such indicators bridge objective facts to the evidence relevant to theories about the former. Regrettably, most philosophers overlook indicators, whereas personal experiences seldom fail to interest them, as shown by the persistent interest in qualia. Let us glimpse at the latter. 5. To phenomena through noumena. Human knowledge comes in many kinds, from experiential or egocentric, such as I feel hot, to impersonal and theoretical, such as heat is random molecular motion. Correspondingly, our concepts lie on a broad spectrum, from the particular and phenomenal, such as sweet, painful, and elated, to the universal and abstract, such as extended, alive, and fair. However, empiricists find the former more basic and reliable than the latter, whereas traditional rationalists regard universals as prior and immediately apprehensible. I shall contend that we need both categories, each for a different purpose, the phenomenal concepts for self-description, and the universals for third-person accounts, in particular, objective accounts of sensations, feelings, moods, and the like. Qualia are pre-analytic experiences, such as seeing blue or tasting chocolate, feeling lust, or a toothache. Qualia are also called experiences, raw feels, and even what it's like, as in what is it like to be a bat? An unanswerable observation indicator hypothesis. Fact datum evidence. 74. Question that earned Thomas Nagel instant celebrity. Qualia have baffled philosophers for more than 2 millennia. In particular, their mere occurrence has been regarded as refuting materialism because they are not describable in physical terms. See, example Bloch, Flanagan, and Guzeldier, eds 2002. A few philosophers, such as Berkeley, Kant, Mill, Mach, Avenarius, Carnap, and Goodman, regarded qualia as primary, and even as the ultimate constituents of the universe, but they failed to show how to construct physical concepts out of phenomenal ones. A few others, such as Dennett and Rorty, have denied the existence of qualia. However, most philosophers admit them, but hold that they are beyond the ken of physics, whence they render materialism untenable, which of course assumes the illegitimate equation of materialism with physicalism. To be sure, physicalism, or vulgar materialism, cannot tackle qualia because these occur in brains, which are superphysical systems. It is likewise incapable of accounting for much more as well, such as the peculiarities of life, example evolution, and society, example culture. However, physicalism is only the primitive version of materialism, one that is not accepted by materialist psychologists, such as Hebb, 1980, or materialist social scientists, such as Trigger, 2003a. The alternative to physicalism is emergentist and systemist materialism, which has been around at least since Holbeck's time. This ontology makes room for superphysical, though not aphysical, levels, see, example Bunge 1959c, 1977c, and 2003a. Indeed, according to this ontology, a quaily is just a subjective process, hence one in some brain. As such, qualia can only be studied in depth by cognitive neuroscientists. In other words, although qualia are first-person processes, they can be studied by a third person, though conceptually and experimentally rather than experientially. Of course, qualia are not transferable. For instance, though I may empathize with you, I can feel neither your joy nor your pain. But psychobiologists have made enormous strides in the description and explanation of what it is like to have experiences such as smelling coffee and suffering phantom limb pain. As a matter of fact, qualia have always been among the objects of study of psychology and neuroscience. We have learned, for instance, that tasting is a long causal chain of events that starts at the taste buds and ends in various regions of the neocortex. We also know that taste can be refined as well as blunted, by, for instance, repeated exposure to very spicy food, some of which kills the taste buds. To summarize up to this point, there are no qualia in the physical world, for they are located in the subject-object interface. Indeed, every quaily has two sources, the brain and something else, whether outside the body or inside it, example in a tooth nerve. In other words, whereas some physical properties, such 75 as chemical composition, are intrinsic, all phenomenal properties, qualia, are relational, they are all for us, none exists in itself. However, subjectivity does not exclude objectivity, all it does is to challenge the neuroscientist or psychologist, asking her to try to give a third-person account of first-person experiences. However, this point deserves a new section. The first of Newton's, 1947 1687, 398, Rules of Reasoning in Philosophy reads thus: we are to admit no more causes of natural things than such as are both true and efficient to explain their appearances. Shorter, noumena are to explain phenomena. This is why Newton's laws concerned only primary properties of matter, such as mass and force, and that is also why his axioms were laws of motion, not descriptions of subjective experiences. Contemporary psychologists follow Newton's advice, and attempt to explain phenomena along the lines sketched by the great Hermann von Helmholtz, a polymath and pioneer of physiological psychology. Among Helmholtz's many contributions is the idea that perceptions are signs, indicators, not images, Abbildungen, of outer world facts. We can only learn how to interpret these signs by means of experience and practice. Helmholtz 1873, 274. In other words, sensory stimulation triggers complex brain processes involving cognition and memory, and sometimes expectation and emotion as well. Shorter, the ability to sense is innate, whereas the ability to perceive is learned. Leonardo said it centuries earlier, we must learn to see. Incidentally, Lenin, 1947, took Helmholtz for a subjectivist. Actually, Helmholtz was a sophisticated realist, who would not have accepted Lenin's reflection theory of knowledge or Wittgenstein's picture theory of language, their names for naive realism. Helmholtz taught that, to understand phenomena, one must study not only external stimuli, but also the organ of perception. His prescription was lost on the behaviorists, from Watson to Skinner, who were materialists but ignored the organs that transduce inputs into outputs. Helmholtz's injunction was also lost on the phenomenologists, who denounced realism as absurd, and claimed to have superseded the objective study of subjectivity with their absolutely subjective discipline, phenomenology, which stands in the extremest contrast to science in the hitherto accepted sense. Husserl 1960, 30. Unsurprisingly, no phenomenologist has found any new facts about phenomena, let alone any new laws about them. Much the same holds for cultural psychology, a closely related school inspired by Wilhelm Dilthey, a follower of both Kant and Hegel, see, example Ratner 1997. Its members too reject positivism, which they mistake for the scientific method. They make much of Verstehen, arbitrary interpretation of both behavior and utterances, and they extol qualitative and non-experimental procedures. This is why they cannot boast of 76. Any findings, whereas scientific psychology, in particular the science of perception, has made sensational advances over the past few decades, see, example Gazzaniga, ed. 2004. Some appearances can be explained in purely physical or chemical terms. For instance, a sun eclipse is explained by the interposition of the moon. And the variety in the colors of quartz, beryl, diamond, and other gems is explained by the presence in them of tiny amounts of chemical impurities. For example, emeralds are beryl stones that look green under white light because they include tiny amounts of chromium, which absorbs the light waves of all wavelengths except for those that cause the sensation of green. Emeralds can lose that color when strongly heated or subject to acids, but not spontaneously. Hence Goodman's, 1954, infamous grue, or bleen, imaginary emerald, green before a certain arbitrary date and blue thereafter, is an idle fantasy. Indeed, Emeralds cannot change colors spontaneously at any date unless strongly heated or unless their chemical composition is altered. Thus, the value of the group paradox to shed light on induction is only this: beware appearances and artificial examples concocted just to support or undermine philosophical speculations, Bunge 1973b. However, the scientific explanation of most appearances requires invoking the brain. For instance, we perceive more readily and vividly events we value, perhaps because of their survival significance, than events to which we are indifferent. This suggests that emotion strongly colors cognition, to the point that we remember best the items, even if trivial, that we first encountered in association with pleasure or pain, joy or sorrow, surprise or embarrassment. None of this should be surprising given the anatomical connections among the cortical, cognitive, and the limbic, emotive, regions of the brain. What is amazing is the persistence of most cognitive psychologists, particularly those of the information processing persuasion, in trying to account for cognition without feeling and emotion, motivation, and spontaneity, as if our brains were dry, cold, and unimaginative computers. See Damasio 1994, Ledoux 2003. The unscientific philosophers of mind claim that phenomenal qualities, or qualia, are inaccessible to scientific investigation, and perhaps even to ordinary knowledge, because they are private. I cannot feel your pain or taste strawberries in the same way as you do. Admittedly, mental experiences are not transferable, but they are describable, and some descriptions can be understood because all adults share not only roughly the same basic brain organization but also myriad similar experiences. In any event, subjective experiences are being studied objectively as neurophysiological processes influenced by cultural traditions and social circumstances. For example, it is well known that many tastes are acquired, and it has been found that Himalayans have a 77 significantly higher pain threshold than Mediterraneans. That is, phenomena are being explained by noumena. What about social attitudes, such as selfishness and altruism? The sociobiologists contend that altruism is selfishness in disguise, as Dawkins, 176, 5, put it, copying the old utilitarian maxim. This certainly holds for reciprocal altruism: I scratch your back and you scratch mine. But what about authentic altruism, as exemplified by giving without prospects of reward? The sociobiologists claim that such gifts are offered, if at all, only to kin, because genes are selfish and force us to behave in such a manner as to propagate them. However, there is ample ethological evidence for the occurrence of cooperation among biologically unrelated individuals, even of different species. Example: Coburn 1998, Cluttenbrock 2002, Griffin 2001, Hammerstein, ed. 2003. Hence, an alternative explanation of altruism is needed. This comes from the study of primates, example Duvall 1996, and people, example Bateson 1991. These studies have shown that humans and the great apes are empathic, and that the performance of generous deeds makes us feel good, Rilling et al. 2002. Other studies found a significant reduction in mortality among old people who help others, Brown et al. 2003. Still other research has shown that the social emotions, in particular altruism and fear of the other, can be manipulated in the interests of political organizations, to the point that the real social engineers are today's political consultants, Massey 2002, 21. In short, altruism is sometimes what it appears to be, namely, selflessness. The epistemological morals are obvious. One of them is that explaining a fact need not involve denying it. Another is that it is foolhardy to seek explanations of social facts at the molecular or even cellular level. All of this has certain consequences for the problem of reduction, to be examined anon. 6. Interlude, reduction. Consider the following purported examples of reduction. 1. Water equals H2O, 2. Evening star equals morning star, 3. speech understanding equals specific activity of the Wernicke brain area. An anti-materialist might object to, 1. Arguing that this alleged identity does not account for such familiar properties of water as its ability to flow, freeze, and be poured, much less feel wet on contact. And he would be right. The well-informed materialist too will deny, 1, though on different grounds. The emergentist materialist will assert instead that, 1, water equals a body composed exclusively of H2O molecules. He will add that fluidity and the ability to evaporate and freeze are emergent. 78. Properties absent from the component molecules, though rooted in the hydrogen bonds among them. He will also contend that, whereas physics can explain the first three properties, only psychology can, eventually, explain the wetness sensation as a brain process triggered by a process in the skin and transmitted to the brain by certain peripheral nerves. Example 2 highlights the difference between physical and phenomenal objects. The physical referent of the two descriptions is the same, namely, the planet Venus. But whereas the first description points to Venus seen at dusk, the second points to Venus observed at dawn, one physical object behind two experiential objects. The two perceptions are different for two reasons. First, ordinarily the air is cooler and less polluted at dawn than at dusk, so that a morning star image is brighter and more distinct than an evening star one. Second, most people are more tired in the evening than in the morning. In short, the perceptions and descriptions of one and the same physical object seen in different circumstances are likely to be different. But this difference, far from being ineffable and mysterious, can be expressed rather clearly and demystified with the help of science. The case of the purported identity, 3, is different from the previous cases, in that it is a genuine identity in the context of neurolinguistics. It is a contingent, or non-logical, identity as much as heat equals random molecular motion and light equals electromagnetic radiation of wavelength lying between so many and so many angstroms are reductive identities in physics. Certainly, speech understanding has further properties, such as eliciting pleasure or fright, admiration or boredom, and so on. But some of these are effects of speech processing in different brain subsystems. The identity occurring in 3 is ontological, not epistemological. That is, the materialist does not claim that a deaf-mute from birth can ever get a first-person knowledge, or knowledge by acquaintance, of speech. All he claims is that speech comprehension is essentially a brain activity. But he also admits that only people with speech experience can do neurolinguistics, and this not because speech has an immaterial component, but because neurolinguists study the speech organ, which is defective in a deaf-mute. In other words, knowledge by description may account for knowledge by acquaintance, but neither is a substitute for the other. Neuroscience alone cannot give a comprehensive account of any speech experience, but cognitive neuroscientists hope to perform this task. See a similar argument in Chitchland 1989 and Lewis 2002. In short, ontological psychoneural identity does not imply epistemological identity. The problem calls for the merger of neuroscience with psychology rather than for the reduction of the latter to the former. Bunge and Ardila 1987. 79. 7. Psychological and social appearances. It is well known that every one of us is perceived differently by others. It is also well known that some personal characteristics are conceptualized differently in different societies at different times. Thus, although being red-haired, left-handed, hunchbacked, or melancholic, depressive, are not social constructions, but objective and harmless biological characteristics, they were stigmatized until recently. Mental illness passed from a feared sign of divine or genetic curse to a manifestation of an unresolved Oedipus complex, or even a social construction, to a medically treatable condition on a par with the other sicknesses, see Shorter 1997. Some of what holds for persons also holds, mutatis mutandis, for social systems, institutions, and norms. Indeed, some of these are perceived, conceptualized, differently by different people, sometimes because of ideological bias, and at other times because they perform more than just one function. Social status is a case in point. Most American blue-collar workers see themselves as members of the middle class, not the working class, and they perceive their wages to be significantly higher than what they really are. Religion is similar. Denounced by some sociologists as a fig leaf to cover up oppression, and exalted by religionists as the most sublime spiritual experience, actually it is both a tool of social control and a view of the cosmic and social orders. Because it may be embraced willingly by large segments of the population, religion should not be dismissed as just a tool of the ruling classes on a par with the police. In particular, in early civilizations the cosmos was conceptualized as a kingdom, but it was a kingdom in which the powers of the upper classes were based more on the consent of the governed and less on the exercise of coercion than in many later pre-industrial societies. Trigger 2003a, 491. This is not to deny that there are genuine social constructions. All institutions and social practices are social constructions, and as such they cannot be explained in purely biological terms. So is the postmodern movement that conceptualizes everything, even nature and illness, as a social construction. In particular, it is not by chance that the anti-psychiatry movement, which proclaimed that mental illness is a fabrication, and denounced psychiatry and insane asylums as tools of social control, was launched in 1960, at a time of radical questioning of the establishment, by such popular writers as Michel Foucault, Thomas Szasz, Ronald Lang, and Irving Goffman. Little did Foucault suspect that AIDS, which he had described as a social construction, would eventually kill him. Cognitive and affective neuroscientists attempt to explain appearances in 80 terms of primary properties, those of the central nervous system. For them, as for physicists and chemists, an appearance only poses the problem of its origin. And this problem is solved by looking for the mechanism whereby a noumenon is transformed into a phenomenon, which in turn is described in strictly noumenal terms. For instance, perception, such as color vision, is gradually being explained in terms of processes occurring in several neuronal systems in the neocortex, see, example Zeki 1993. And emotions, such as fear, are being explained in terms of processes in the cerebral amygdala and other components of the limbic system, see, example Rugg, ed. 1997, Squire and Coslin, eds. 1998, and Gazzaniga, ed. 2000. In sum, mental events are being accounted for as processes in neural systems involving synapses, neurotransmitters, and the like, much as the electric current in a wire is explained in terms of electrons and electromagnetic fields. However, because human brains are embedded in society, neuroscience is not enough to explain the mental. This is why psychology has a social component. However, social psychology too endeavors to explain the brain-society interactions in terms of primary properties, those of society in addition to properties of the brain. A famous example is that of the dime illusion. Poor children tend to perceive coins as larger than do their rich counterparts. In social matters, the noumenon-phenomenon relation is far more complex than in other realms. This is because of the so-called Thomas theorem. We do not react to social facts but to the way we perceive, actually imagine, conceptualize, and evaluate them. Merton 1976, 174-6. For instance, many of us buy well-advertised junk food and vote for friendly-looking crooks. And in all early civilizations the rulers were regarded as either supernatural beings or as intermediaries between deities and commoners, and were revered and feared in consequence. The very maintenance of the cosmos was supposed to depend upon the strict observance of the social and religious conventions. This may explain why class conflict was not a major feature of early civilizations. Trigger 2003a, 671. Another case in point is self-appraisal, which depends on the reference group. For instance, an Afro-American who complains that his salary is meager is comparing his income with that other members of his workplace, not with that of derelict Afro-Americans, let alone with the subsistence level income of the land of his ancestors. His perception of relative deprivation is thus perfectly objective, so that his grievance is legitimate and may be traced back to racial discrimination. The sociologist is expected to handle his social perception as a fact just as objective as both the chosen reference group and the discrimination that originates it. 81. Much the same holds for the new perception that emerges when the agent adopts an alternative reference group, or acts in a different social circle, such as the personnel of another firm in the same industry. In short, one and the same agent combines with both an objective social circumstance and a reference group to yield a perception of the circumstance. Change the agent, the reference group, or both, and the perception is likely to change as well. This explains why people may react differently to the same social fact. The real chain is not the direct behaviorist two-step process circumstance action. Rather, it is the indirect chain, perception decision action. Of course, every enrichment in explanation must be paid for by the uncertainties associated with the inclusion of perceptions and decisions. However, experimental psychologists have devised a whole battery of objective indicators of such mental processes. Just as the psychologist studies illusion and hallucination in addition to normal perception, so the social scientist studies the deliberate creation of misleading appearances. Mimesis is found among many animals, such as certain butterflies, fish, and cephalopods. Humans and other primates cheat in various ways, from simulation to dissimulation, but, unlike other animals, we are also capable of self-deception. What would social life be without a modicum of dissimulation and hypocrisy? What then of Durkheim's, 1988, classical methodological injunction, that sociologists should describe social facts in the same objective fashion as physicists, because they are just as real as physical facts? It stands, with the proviso that some of the processes occurring in his subject's brain, in particular his beliefs, attitudes, evaluations, intentions, and decisions, are among the facts of interest to the sociologist. In particular, social phenomena, that is, the way an individual perceives the social facts around him, are to be studied from the outside as so many objective facts. After all, they occur in the student's external world. Thus, what the subject regards as a phenomenon, the student of society views as a noumenon. Undoubtedly, this expansion of the domain of facts to be studied by the social scientist to include the agent's subjective experience requires techniques that go beyond the mere recording of overt behavior. But, if conducted scientifically, this study will lead to testable hypotheses, not to literary images that tell more about the student than about his subjects. See Burawa 2003 for a criticism of the fashionable interpretive turn that replaces social facts with texts, and scientific papers with literary essays. In sum, appearances are part of the reality of many animals, particularly ourselves. This contradicts the popular view that appearance is the opposite of reality. Appearances are real, but they are only skin deep, literally so. 82. Since they occur in the subject-object interface. And, being superficial, they call for explanation in terms of unobservable, yet scrutable, things and properties, instead of being explainers. However, this point deserves a separate section. 8 scientists in the crib. Chomsky, 1965, 27, famously attributed extraordinary linguistic abilities to newborns. According to him, every child is born knowing a universal linguistic theory that allows him to determine which of the, humanly, possible languages is that of the community in which he is placed. This extraordinary hypothesis of the instant linguist has recently been enlarged. Babies think, construct theories, look for explanations, and perform experiments much like scientists do. In particular, see Hildren create and revise theories in the same way that scientists create and revise theories. We think there are very strong similarities between some particular types of early learning, learning about objects and about the mind, in particular, and scientific theory change. In fact, we think they are not just similar but identical. We don't just think that the baby computers have the same general structure as the adult scientist computers. We think that children and scientists actually use some of the same machinery. Gonick, Meltzoff, and Cole 1999, 155. A first reaction to this amazing claim is that the words theory and experiment in the preceding statements cannot possibly have their standard significations. Indeed, a theory proper is a hypothetico-deductive system and, moreover, one that does not contain phenomenal, or observational, predicates, unless it happens to be a psychophysical one. And an experiment is not just any old trial and error process but a carefully designed and controlled one. True, Lashley, Tolman, and Kreshevsky conjectured that rats make hypotheses and check them while exploring their environment. Kreshevsky, 1932, and other scientists checked and confirmed this conjecture, but they did not claim that rats construct scientific hypotheses and perform scientific experiments, or even that they are conscious of such operations. This is why their favorite rats did not occur as co-authors of their papers. Presumably, the theories that Gonick and her colleagues attribute to infants are vague and tacit, not explicit, hunches such as yummy stuff comes out of that when I suck it. And the baby's experiments are likely to be trials such as babbling or crying to draw the caregiver's attention. How could the mental processes of babies be identical to those of trained adults, or even naive adults, if the respective neural architectures are so different, as revealed more than half a century ago by microscopic examinations? See Conal 1939, 67. 83. Or are we to believe, with Thomas Aquinas, that the Holy Ghost grafts a fully formed soul upon the embryo or the fetus? The theories referred to by the theory psychologists are even more primitive than the view of scientific theory held by the logical positivists, such as Carnap, 1936-7. This influential author held that scientific theories are composed of statements of two kinds: observational, such as this red thing is hot and hissing, and theoretical, such as the photon absorption caused the ejection of an electron from the atom. The logical positivists claimed further that only the former are fully meaningful, whereas the latter are only partially interpreted, and acquire a vicarious meaning through their association with the former. However, even a superficial examination of scientific theories and experimental designs will show that they are made up of concepts and propositions, not percepts and feelings. And there is no evidence that a baby can form any concepts, such as that of mother, rather than a rather blurry visual, tactual, olfactory, and auditory image of its particular mother. Besides, the babble of infants has a heavy emotional and observational, or phenomenal, load. By contrast, scientific theories lack emotional and observational terms, in particular terms denoting qualia, unless they happen to be about sense perception. Recall section 1. Another objection to the scientist in the crib hypothesis is that it is doubtful that babies know of any properties other than phenomenal ones, such as sweet, warm, loud, rough, prickly, and wet. Nor are their inquiries disinterested like those of the basic scientist. Infants are curious only about their immediate present environment, and just because they need to know in order to survive. And, being practically minded, they are likely to put together quite disparate things just because they occur jointly in their experience, such as mother and milk, or diaper and urine. The analytical skills of infants are likely to be very limited not only because of the primitive state of development of their brains, but also because their thinking is action-oriented rather than contemplative. In this regard, an infant, and Rachmat, the uneducated and illiterate Central Asian adult studied by Luria, 1979, 69-71, are likely to perceive their environment in similar ways. Thus, Luria once showed Rachmat a picture and told him, "Look, here we have 3 adults and a child. Now clearly the child doesn't belong in this group." Rachmat replied, "Oh, but the boy must stay with the others. All 3 of them are working, we see, and if they have to keep running out to fetch things, they'll never get the job done, but the boy can do the running for them. The boy will learn, that'll be better, then they'll all be able to work well together."
Rockmut's worldview seems to have been holistic, dynamic, and above all pragmatic. 84. Besides, what infants can get to know is very limited, if only because they do not have the same brains as adults, let alone scientists. In fact, pathologists have shown that the neural circuitry in babies is very rudimentary. In particular, the prefrontal cortex, which is critical for cognition, valuation, planning, and decision, is hardly active in early childhood, and takes 2 decades to fully myelinate. Furthermore, ever since the epoch-making experiments of Hubel and Wiesel, 1962, it has been known that the mammalian brain develops along with experience. We are born learners, not learned. It is even likely that scientists sculpt their own peculiar brains as they learn and do science, and that consequently their brains differ in significant ways from those that musicians or managers sculpt for themselves. A third reaction to the thesis in question is this. If babies and scientists have basically the same cognitive abilities, why is science so hard to learn that the vast majority of people of all ages, even many who have taken science courses, tend to think in unscientific ways, in particular in magical terms? And why did science emerge as recently as 2,500 years ago, only to submerge a few centuries thereafter, and to re-emerge precariously only 400 years ago? One reason may be because science deals in primary properties, which are not accessible to the senses. A second reason may be that science posits laws, in particular invariances, that are not found in experience. A third may be that scientific work is done in the midst of scientific communities that regulate themselves in accordance with the exacting scientific ethos first identified by Merton, 1968, disinterestedness, epistemic communism, and organized skepticism. In sum, science is qualitatively different from ordinary knowledge. In particular, it is far more rational and less wasteful than trial and error guessing. As Wolpert, 1992, put it, science is quite unnatural. If scientific research did start in the crib, it should flourish in grade school, and even more so in high school. That it does is the distinctive thesis of pedagogical constructivism, an increasingly influential pedagogical school, particularly in science education, see Fensham, ed. 2004. This doctrine, particularly as articulated by von Glasersfeld, 1995, is philosophically just as wrong as its prime sources, namely, Berkeleyanism, Kantianism, and operationalism, all three of which are proudly acknowledged by von Glasersfeld. Pedagogical constructivism is also psychologically false because modern science is so counterintuitive that it is quite hard to learn, and impossible for an individual to reinvent by himself. For example, most physics teachers know that freshmen hold Aristotelian rather than Newtonian opinions about motion. In particular, beginning mechanics students, just like Kant, find inertia hard to grasp. Consequently, they are baffled by the fact that the planetary orbits are perpendicular to the gravitational attraction. 85. Pedagogical constructivism is not only false. It is also harmful because it denies the existence of objective truth, suppresses criticism and debate, and renders teachers expendable. Can any teacher seriously maintain that normal teenagers can rediscover, or rather reinvent, by themselves the calculus or the theory of evolution? And can any serious scholar claim that one should never contradict anyone because there is no such thing as truth? Is not lack of debate the mark of dogmatism? And is not relativism a tacit confession of an inability or unwillingness to learn how to check for truth? Further criticisms in Matthews, ed. 1998, still, a smart self-styled constructivist teacher may occasionally be more successful than a realist but dull one who believes that students must be spoon-fed rather than motivated to study on their own. This will be the case if the teacher encourages her students to think for themselves, whereas her realist colleague demands uncritical parroting. The reason for her success is that, as Maria Montessori and John Dewey stated long ago, exploration prompted by curiosity is more interesting, hence far more motivating and rewarding, than the repetition of half-understood formulas. Still, Science instructors are expected to provide some guidance, if only to avoid the waste of time and the accompanying discouragement that characterize blind trial and error endeavors. Teachers are also expected to check whether their students give correct answers, and whether they estimate correctly the measurement error. That is, the constructivist teacher, if minimally competent and responsible, will have to admit that error, and therefore truth too, matters after all. 9. Science and technology are realist. The phenomenalist philosopher, like the second-hand car dealer, assures us that what we get is what we see. By contrast, the realist philosopher, like the experienced car buyer, assumes that we always get far more than what we see, because the perceptible, secondary, qualities constitute only the tiny tip of the iceberg of facts. Because of this ontological presupposition of science, any non-trivial project in empirical scientific research aims at finding out what lies beneath said tip. Most of us can see, but only a few understand what they see. As St. Georgi once said, discovery consists in seeing what everybody has seen and thinking what nobody has thought. The assumed nature of reality, that it consists of facts and events that are mostly beyond the reach of perception, dictates the nature of the scientist's method of inquiry. Indeed, the scientist's first move is to step out of his subjective and pre-analytic bubble, that of qualia, feelings, inner speech, and the like. That is, the scientist takes the external world for granted, and keeps his 86 own perceptions, feelings, and reasoning for himself and under strict control. They are only the starting point. Moreover, he attempts to discover the primary qualities underneath the secondary ones, for example, the molecular and cellular processes felt as a pleasurable sensation. In sum, the scientist's procedure is the exact opposite of the poets, the musicians, and the idealist philosophers, where the latter may give free rein to their untutored imagination, the former must discipline his to keep in touch with reality. The same holds of course for the technologist's tinkering and designs. No reality checks, no science or technology. The scientist's imagination is disciplined but, at the same time, it is far richer than the artist's because the latter, even if a devotee of abstract, non-representational, art, is bound to sensory experience. Even a blind plastic artist fashions visible things, and even a deaf musician creates sounds, whereas a theoretical physicist, chemist, biologist, or social scientist creates conceptual systems. Moreover, the theorist, contrary to the artist, conceives of items and properties that have no experiential counterpart, such as force fields, quanta, atomic nuclei, black holes, genes, viruses, government budgets, and the decline of empires. What is more, scientists construct predicates representing primary properties and events of two kinds, superficial, like temperature and visual acuity, and deep, like quantum tunneling and neuronal plasticity. Thus, contemporary science has enriched the primary-secondary dichotomy introduced by Galileo, to read thus. The scientist's procedure is also the opposite of Husserl's phenomenological method, which allegedly dispenses with all presuppositions, and brackets out the world. It does this to concentrate on the stream of one's own perceptions, memories, feelings, expectations, imaginations, and the like, Husserl 1970. How this differs from the mystic's navel contemplation is not explained. Nor are we shown any list of the wonderful findings that this ancient method is said to have garnered. The phenomenologist spends all his time preparing for inquiry, promoting his program as that of a rigorous science, and denigrating standard science and objectivism. He trains for a race that he will never run. Basic, example atomic number, social class. Primary properties. Derivative, example density, social status. Secondary, example cold, wet, bitter. 87. The ultimate rationale for the scientific method is the wish to attain objective truths, that is, data and hypotheses that are adequate to their objects or referents, regardless of the mood or preference of the investigator. And using this method involves transcending sense data and constructing conceptual systems, such as classifications and theories, that contain only predicates representing primary properties, unless the theory happens to refer to phenomena such as tastes, smells, colors, and feelings, as is the case with certain neuroscientific and psychological theories. Given that scientific theories are conceptual systems rather than piles of sense data, expecting untutored children or illiterate villagers to come up with scientific theories on the sole strength of their daily life experiences is to betray naive faith in the power of the most rudimentary of philosophies, namely, phenomenalism. Yet this is precisely what the ontological, social, and pedagogical constructivists ask us to believe, that everyone constructs the world by herself. In summary, contemporary subjectivism is not only preposterous and an obstacle to the exploration of reality, it is utterly unoriginal. Berkeley had said all that much earlier, in clear and elegant prose to boot. 10. The great 18th-century mathematician, physicist, engineer, and amateur philosopher Leonhard Euler, 1846, 323, was rightly called second only to Newton. Euler called the irrealist philosophers clowns, and said that their motivation was not the hope of finding truths but just to draw attention to themselves. Euler's harsh judgment on anti-realism would be regarded as bad form in contemporary academia, where all philosophical and pseudo-philosophical doctrines, even the most preposterous, least original, most barren, most obnoxious, and most boring, are given equal time as serious schools of thought. In particular, anti-realism is regarded as academically far more sophisticated and respectable than scientific realism, materialism, or scientism. Anti-realism is out of step with science and technology, intent as they are on exploring or altering reality. Anti-realism is not just wrong, it is utterly destructive, because it proclaims a total void, ontological, epistemological, semantic, methodological, axiological, ethical, and practical. Such integral nihilism or negativism, reminiscent of Buddhism, discourages not only objective evaluation and rational action, but also the exploration of the world. It is at best an academic game. 88. 4. Causation and chance. Apparent or real. Appearances do not exhibit causal connections, all we perceive are events, simultaneous or successive, contiguous or distanced, external or internal, real or illusory. For instance, we hear a clap of thunder after seeing a flash of lightning, but we do not perceive the causal connection between the two events, we only conjecture that the latter caused the former. This is why phenomenalists, from David Hume, 1888-1734, to David Lewis, 1998, have had no use for the notion of objective causation, even though, presumably, they took part in myriad causal chains. And this, in turn, is why the word causation all but disappeared from the vocabulary of the positivist philosophers between about 1880 and the time when it was rescued from oblivion, Bunge 1959a. Fortunately, the positivist fatwa against causation did not discourage scientists from seeking causal connections and explanations. For example, in the 19th century the lightning-thunder hypothesis was confirmed in the laboratory by producing electric sparks and detecting the succeeding shock waves, and neuroscientists proved that insults to the brain may cause mental deficits. During the first half of the 20th century atomic physicists showed that the cause of light emission is the decay of atoms or molecules from excited states, geneticists proved that some mutations cause phenotypic changes, social scientists proved that the cost of maintaining colonies ends up by exceeding the benefit deriving from exploiting them, and so on and so forth. The scientific evidence for causality became overwhelming. Causal determinism ruled in the sciences nearly undisputed during more than 2 millennia until the emergence of quantum mechanics in 1925. From then on it has had to contend with probabilistic determinism, often misleadingly called indeterminism. Moreover, it is often claimed that causation is a particular case of randomness, namely, when the probabilities concerned equal. 89. Unity. However, as will be seen below, This is a mistake. The concepts of causation and chance are mutually irreducible. Interestingly, though, sometimes they combine, as when one calculates the probability that a certain event will cause another. In any event, we still need the traditional concepts of efficient and final causation, even though we now admit that their extension or applicability is limited. For example, the causal principle does not hold for particles or photons traveling in far-out space, since nothing pushes or pulls them. Nor does it hold for the spontaneous occurrence of sensations and thoughts in the absence of external stimulation. In short, not all facts call for causal explanations, only some of them do, namely, changes, and not even all of them. For instance, the presence of this book on your desk is a fact but not an event, whence it does not require a causal explanation. What does call for explanation is why the book came to occupy this unusual place. And here several causes may be invoked, perhaps because you placed it there, efficient cause, to consult it, final cause. In short, causation implies change, but the converse is false. What about chance? What if any is its ontological status? The oldest and most popular view about chance is that it is not real, that it is only a name for our ignorance of the relevant causes. This has been a fertile view, for it has encouraged the search for causal connections. This search has been so rewarding that until recently causal determinism was regarded as part and parcel of the scientific worldview, example Bernard 1952, 92. George Boole, 1952, 249, echoing Leibniz and Kant, went even further. He believed that the idea of universal causation seems to be interwoven in the very texture of our minds. Much later, Jean Piaget discovered that young children learn to attribute changes to causes, and ethologists found that the same holds for apes and corvids when they are making or using tools such as sticks and hooks. However, certain scientific advances in the 19th century, notably the invention of the calculus of accidental errors of observation, and statistical mechanics, suggested that chance is just as real as causation. The emergence of quantum mechanics, genetics, molecular biology, and communication engineering in the 20th century confirmed the firm place of chance in the world, and the concomitant role of the theory of chances in factual science. Think of quantum jumps, chance mutations, and noisy communication channels. Still, none of this has proved that chance is basic or irreducible. It has only proved that the concepts in question are necessary ingredients of scientific knowledge on certain levels of analysis. We must therefore inquire whether or not chance is part of the fabric of the world, and whether probabilities can be attributed to facts, or whether they only measure the strength of our beliefs. 90. In this chapter we shall glimpse at the concepts of causation and chance, and discuss some of the philosophical problems they raise. However, chance will get here the lion's share because it is the more slippery of the two concepts. The upshot will be that science needs both concepts, as a consequence of which metaphysicians should update determinism to include probabilistic as well as causal laws. 1. Causation. Let us characterize briefly the notions of causal relation, causal principle, and causal determinism. The latter's limitation will also be noted. For details see Bunge 1959a and 1982. The standard analysis of causation is in terms of necessary and sufficient conditions, X causes Y if and only if Y. Though correct, this explication is not quite satisfactory in ontology, and this for two reasons. First, because the notions of necessary and sufficient conditions occur in the explication of logical equivalence, not of real processes. Second, because in the biconditional X if and only Y, the events called X and Y are interchangeable, whereas in reality causes cannot be exchanged for their effects, the causal relation is asymmetric. In ontology we need a concept of causation that will fit facts, such as the brain process that goes from hearing the shout "watch it," to looking at its source, imagining and evaluating the imminent dangerous event, making the decision to avoid it, and jumping away from it. This complex process between auditory stimulus and muscular response is a causal chain, a succession of events in a material system, a human body. We need then an explication of causation in terms of events and energy fluxes. We start by making the usual if sometimes tacit assumption that the causal relation obtains between events, changes of state in the course of time, not between things or their properties. A simple classical example is Hooke's law: the strain or deformation of an elastic body is proportional to the applied tension or load. Because only events can cause, we must disallow such expressions as gene G causes trait T and brain causes mind. We should say, instead, that the expression or activation of gene G causes it to intervene in the biochemical reactions resulting eventually in the emergence of phenotypic trait T. Likewise, we must say that mental event M is identical with brain event B, the only difference being that M is ordinarily described in psychological terms, whereas B is described in neuroscientific terms. To hold that brain processes cause consciousness, as Searle, 1997, 7, does, is like maintaining that bodies 91. Cause motions, or that the gut causes digestion. Things do not cause processes, they undergo processes, and these in turn cause changes, events or processes, in other things. Shorter, the causal relation holds only among changes, events and processes. We are now ready for our first convention. Definition 4.1 Event C in thing A causes event E in thing B if and only if the occurrence of C generates an energy transfer from A to B resulting in the occurrence of E. A more precise definition can be constructed with the help of the concept of a state space introduced in Chapter 1, Section 2 Bunge 1977a, 1982. Let A and B be two different things, or two different parts of a thing, such as the prefrontal cortex and the amygdala of a human brain. Call H, A, and H, B, the histories of things A and B respectively over a certain time interval and in the total state space of A and B. Further, call H, B A, the history of B when A is present or, rather, active. Then we can say that A acts on B if H, B, H, B A, that is, if changes in A induce changes in B. The total action, or effect, of A on B is then definable as the set theoretic difference between the forced trajectory of B, that is, H, B A, and its free trajectory H, B. In symbols, A, AB, equals H, B A, H, B, C, where H, B, C is the complement of H, B. Likewise for the reaction of B upon A. Finally, the intensity of the interaction between things A and B is the set theoretic union of A, AB, and A, BA, dot. A familiar example is the energy cascade involved in shooting an arrow, chemical energy stored in the ATP molecules of the muscle cells, kinetic energy of the arm tensing the bow elastic, or strain, energy stored in the bow, kinetic energy of the arrow, mechanical and thermal energy absorbed by the target and the atmosphere. Another familiar example is this: the activity in the amygdala we call fear stimulates the prefrontal cortex, which in turn orders the motor strip to activate the legs. Shorter, fear causes flight. The energy transfer mentioned in definition 4.1 is negligible in two cases: when the patient is in an unstable state, touch and go, and when the energy flux is a signal, such as the movement of a neurotransmitter across a synapse, or an order to fire a missile or an employee. Social life is rife with events caused by signals. For example, consumers signal their intentions to the market, by buying or abstaining from buying, which signals back to them, just by posting prices, what they can afford to buy. This is obvious, but the direction of the causal arrow is not, so much so that there are two schools of thought on this matter. Let us look briefly into it. The neoclassical theorists claim that supply generates its own demand, Say's law, that is, produce and someone will buy, because the market abhors disequilibria. The Great Depression falsified this dogma, and John 92. Maynard Keynes, 1973, suggested that the arrow actually points in the opposite direction. The reason is that demand, far from being a source fact, is an effect of expenditure decisions.
This view is not only more realistic than the no-glut assumption, it also connects the microsocial level of individual decisions to the macrosocial level of mass supply and demand. At all events, the controversy on the causal arrow in question can be summarized as follows. In sum, for practical purposes we distinguish two kinds of causation: energy transfer and triggering signal. However, it should be remembered that a signal, whether physical, chemical, biological, or social, is a process involving energy transfer. Besides, a signal carries information proper only if it is coded, that is, if it is coupled with an artificial code, such as the Morse code, capable of being decoded by a natural or artificial sensor. Shorter, information is signal together with meaning. We are now ready to state the causal principle in its simplest version. Postulate 4.1 Every event has some cause, S. This principle is true in very many cases, but not in all. The exceptions are constituted by the spontaneous events, that is, those that are not elicited by external stimuli. Examples of such changes are self-movement, such as that of a particle or a photon once it has been ejected, natural radioactivity, the spontaneous firing, discharge, of neurons, the spontaneous emergence of new ideas, and the emergence of social norms alongside with that of social systems such as teams or gangs that emerge spontaneously, without coercion, around a task or a leader. It might be objected that some of the preceding examples are cases where cause and effect occur in one and the same thing, such as a neuron or a society. True, but if we keep definition 4.1 for a process to qualify as causal, the thing in question must have at least two distinct parts. For example, in principle one may explain radioactive disintegration either as a case of spontaneous tunneling through a potential barrier, or as a result of the ejected particle having attained, through random collisions with other particles in the same nucleus. Neoclassical theory. Macrosocial level supply-demand. Keynesian theory. Macrosocial level demand-supply. Microsocial level expenditure decisions. 93. The kinetic energy required to jump over the said potential barrier. Second example, the deliberate movement of a limb follows upon a decision made in the frontal lobe. Third, a political revolt is internal to a society, but it opposes two parts of it, government and insurgents. In short, a cause proper is always an event external to the thing upon which it acts. A cause may not always produce its effect, the latter may occur only with a certain probability. That is, in some cases C causes E must be replaced with C causes E with probability P, or PR, EC, equals P for short, where PR, EC, stands for the conditional probability of the occurrence of E given the concomitant or previous occurrence of C. In short, there are probabilistic, or stochastic, laws in addition to causal laws. The best examples of probabilistic laws are those of the quantum theory. The above formula, PR, EC, equals P, is the nucleus of the probabilistic theory of causation, according to which causation obtains in the particular case when P equals 1, example Supps 1970, Popper 1974. But surely we need the concepts of cause and event before we can even write down the above formula. In other words, the concepts of causation and probability are not interdefinable. What is true is something far more interesting, namely, that in many cases the two categories intertwine, even though at first sight they are mutually exclusive. Our explication of causation in terms of energy transfer is at odds with the fashionable account in terms of counterfactuals, Lewis 1973, 1983. According to the latter, if X and Y are actual events, then Y depends causally upon X if and only if X had not occurred, then Y would not have happened either. I submit that this analysis is flawed for two reasons. One is that it is tacitly parasitic upon the law statement if X happens, then Y too occurs. The second flaw is that counterfactuals are logical outlaws because they are not propositions proper, and consequently they cannot be assigned truth values. Let us indulge in a bit of counterfactual history,
imagine what would have happened to physics if Newton had stated his second law of motion in the following form: a body of mass m would acquire the acceleration a equals f/m if it were acted upon by force F. Why would anybody have bothered to write, solve, or test the corresponding equation of motion for different cases? Counterfactuals are heuristic or rhetorical tricks, not law statements belonging to scientific theories. We shall return to them in Chapter 9, Section 6. Besides, in the sciences and technologies, causal considerations focus on properties rather than on whole events. A standard definition is this. Let A and B denote two properties of things of a given kind, and assume that B is a certain function of A, that is, B equals f, A. Then a change B in property B is said to be caused by a change A in property A if either theory or experiment show that change B follows in all cases, or at all times, upon the occurrence of A, and 94. Moreover, approximately in the amount B equals f, A, where f, A, is the value of the slope of the graph of f at A. The corresponding empirical criterion is obvious: to ascertain whether B is causally dependent upon A, wiggle A and check whether B does change as hypothesized. That is, to make sure that a hypothesized causal connection obtains, make the cause occur, and check the presumed effect. The counterfactual account of causation is qualitative, and thus provides no precise criterion to ascertain whether or not B equals f, A. Holds. So much for efficient causation, the only type of causation admitted by the founders of modern science and philosophy, all of whom rejected the other three types postulated by Aristotle: material, formal, and final. However, the news of the decease of final causation is exaggerated. Indeed, contemporary science and engineering admit goal-seeking behavior in higher vertebrates and in artifacts equipped with control mechanisms such as thermostats and orbit-correcting devices. Still, this view of final causation is very different from the old teleological view, according to which the future somehow causes present events. In purposive behavior, a mental representation of the future, understood as a brain process, triggers a decision in the prefrontal cortex, which in turn causes a change in the motor strip, which in turn causes a limb to move, which in turn may act on a lever or a button. This is a chain of ordinary efficient causes, so much so, that the intention-motion part of the chain can be replaced by an electromechanical prosthesis. As for automatic control, Norbert Wiener and his co-workers explained it long ago in terms of feedback, or circular causation, loops. In short, teleology is perfectly admissible provided it is analyzed as emerging from chains of efficient causes. In sum, causal determinism has a wide range of application, but it does not cover all events. Not all interconnected events are causally related, and not all regularities are causal. Chance too has its place in the universe, and consequently determinism should be broadened to include probabilistic laws. However, we have already reached the next section. 2. Chance, types. The word chance is notoriously polysemous. We should distinguish at least three distinct kinds of chance: accident or chance encounter, disorder, and spontaneous or uncaused event. As the Stoic Chrysippus explained 22 centuries ago, a chance encounter, or coincidence, or contingent event, consists in the crossing of two initially independent causal lines. Familiar examples are the accidental meeting of two acquaintances, finding a treasure when digging a hole to plant a tree, the involuntary collision of two vehicles. 95. And the unanticipated consequences, beneficial or perverse, of social action, or inaction. This first type of chance was known to ancient philosophers, particularly Aristotle, who devoted to it several pages of his Physics, 196b. Chance in the sense of unique or unrepeatable opportunity, or concours de circonstances, plays an important role in history as well as in individual life. This is why biological evolution has been described as opportunistic or tinkering rather than designed, Jacob 1976. There is a special term for this, a feature that has been co-opted to perform fitness-enhancing functions other than the original ones is called exaptation. This is why Gould, 2002, emphasized the role of contingency, that is, accident, in biological evolution. For example, it is conceivable that certain biospecies, in particular ours, might not have emerged had it not been for the accidental combination of certain genic mutations with favorable environmental circumstances. Much the same holds for human history. Thus, it has been argued that the Florentine Renaissance was partly a side effect of the Black Plague, which favored the concentration of wealth, and thus rendered bolder commercial enterprises possible. Again, the worldwide influenza epidemic of 1918 was particularly lethal because it attacked populations that had been weakened by 4 years of war. And some scientific discoveries have been happy accidents, though, as Pasteur and others have noted, it takes well-prepared minds to seize them, see Taton 1955. The word serendipity is often used as a synonym of accidental success. The cases of the discovery of X-rays, radioactivity, penicillin, and stellar radio waves, see Merton and Barber 2004. The admission of the occurrence of coincidences marked an advance over magical thinking, according to which coincidences are indicators of inscrutable connections. This kind of thinking survived, for instance, in Carl Gustav Jung's doctrine of synchronicity. This is an ingredient of Jung's combination of psychoanalysis with the occult sciences that has become a component of New Age thinking. However, we all know that our life histories are full of chance encounters of many kinds. For instance, not even the most carefully arranged marriage might bypass the genetic features, such as recessive genes and blood type, that have no obvious phenotypic, observable, counterparts. Hence, every one of us has issued from pairings that are random to some extent. Only the original sin was presumably free from chance. The second kind of chance is disorder, such as that caused by dissolving, shaking, shuffling, scrambling, stirring, heating, rioting, and the gathering of mutually independent items, such as births and road accidents, into a statistical population. This is the kind of disorder that statistical mechanics, actuarial statistics, and the sociology of deviant behavior deal with. It is patent in white noise, the patterns of raindrops, diffusion, the dispersal of genes and seeds, the 96. Propagation of nerve impulses along an axon, the outcomes of games of chance, life expectancies, and experimental errors. Its mark is the statistical fluctuation or variance. The very existence of the life insurance companies depends on this kind of chance. As Poincaré, 1908, pointed out, they would still be in business even if their physicians could foresee the date of death of every one of their policy holders. Causation on one level may result in chance on the next, and conversely. It has been argued that the games of chance are not really such because coins, dice, playing cards, and the like move according to the laws of classical mechanics. True, but in this case chance inheres in the initial conditions resulting from deliberate randomization, as when a deck of playing cards is shuffled. Certainly, an omniscient being should have no difficulty in finding the pertinent initial conditions. But the outcome would still be random because the gist of such games is a randomization mechanism, such as the thorough shaking or shuffling that will produce an objectively random initial distribution of possibilities, leading to a matching outcome. This is only an instance of the general law that the future depends not only on the pertinent laws but also on the initial and boundary conditions. This type of chance was recognized only at the beginning of the scientific revolution. Of course, people had played games of chance much earlier, but only for entertainment or divination. Cardinaux, Galileo, Pascal, Descartes, Fermat, and the Chevalier de Mere were the first to try and discover laws of chance, a seeming oxymoron. Another century went by before Daniel Bernoulli applied the Young probability theory to physics. And it took a further century for it to be applied to social statistics, which deals with the regularities found in large populations of mutually independent human events, such as births and car accidents, see,
Example Porter 1986 and Geigerenzer et al. 1989. Epicurus introduced a third kind of chance. He speculated that atoms deviate irregularly and spontaneously from the straight line, in a motion that Lucretius dubbed Clin Amen. The great botanist Robert Brown was the first to discover, in 1828, a real example of this kind of chance, namely, the Brownian motion of pollen particles. 6 decades later, Einstein explained such visible irregular motions as the effects of random molecular impacts of molecules assumed to abide by causal laws. Moreover, he pointed out the variables, such as the mean free path, that had to be measured to test this hypothesis. In this case, randomness on the mesoscopic level of pollen, and dust and soot, particles resulted from the crossing of mutually independent trajectories of microscopic particles, which the theory assumed to satisfy the laws of classical mechanics. Shorter, chance on one level may result from causation on a lower level, Bunge 1951. This does not render chance illusory, it only 97. Makes chance relative to the level of organization. See Bunge 1959b, 1969, and 1977c for the multilevel structure of the world. The late 19th century positivists, particularly Mach, Duhem, and Ostwald, had derided both the atomic hypothesis and statistical mechanics for postulating the existence of transphenomenal entities as well as the reality of chance. The eminent Wilhelm Ostwald, 1902, proposed his energetics, a wild extension of classical thermodynamics, which he claimed to embrace even value theory, as well as to overcome the materialism/idealism conflict. Most physicists around 1900 shared this anti-atomistic prejudice. Fortunately, Ludwig Boltzmann and Max Planck, along with a handful of young Turks, notably Albert Einstein, Jean Perrin, Victor Henry, and Marian Smoluchowski, took the unorthodox line. They put the atomic hypothesis to work, and supported realism. In 1905, Perrin performed the first accurate measurements of Brownian motion, confirming the key theoretical formulas, and thus proved the reality of atoms. He stated that at every instant, in a mass of fluid, there is an irregular spontaneous agitation due to the random molecular motion, in Brush 1968, 31. Such fluctuations showed also that the irreversibility postulated by the second laws of thermodynamics holds only in the large. In fact, decreases in entropy, albeit small, infrequent, and short-lasting, are possible even in closed systems. The third type of chance, or spontaneous fluctuation, is prominent in quantum physics. Think of spontaneous radiative and radioactive decays. Even more astonishing examples are the vacuum fluctuations postulated by quantum electrodynamics, and the self-acceleration inherent in the Zitterbewegung, trembling motion, that relativistic quantum mechanics attributes to the electron. Both are reminiscent of Epicurus's swerve. Sheer coincidences, type 1 chance events, though. It has been speculated that there might be a subquantum level devoid of chance. The entities on this level would be described by hidden variables, that is, variables with zero variance, or fluctuation. David Bohm's extension of quantum mechanics has been the most prominent attempt in his direction. However, it did not prosper, mainly because it failed to derive the quantum mechanical probability amplitude, the famous function, from non-stochastic variables. So, the chance postulated by quantum theory is of the rock-bottom type, until new notice. However, the idea of real or objective chance is not obvious. Ironically, one way to get rid of real but unrealized possibilities is to consign them to parallel universes, the way Everett, 1957, has done. Suppose a quantum theorist obtains the result that a certain thing can have infinitely many energies, each 98. With a given probability. Suppose further that you measure the energy of the thing in question, a sharp energy value emerges from the original blob distribution. What became of the infinitely many remaining energy values? Everett's answer is, every one of them is realized in an alternative world, where a counterpart of yours performs a similar experiment. Although this extravagant interpretation of quantum mechanics has few adherents, it is generally treated respectfully, as if it were a piece of serious if useless science. And yet the many worlds interpretation of quantum mechanics belongs squarely in science fiction. This is so for the following reasons. First, the parallel worlds are in principle inaccessible and therefore inscrutable, and thus beyond the reach of science. Second, a measuring act is assumed to transform the single initial thing into infinitely many copies of it, which violates all of the conservation laws. Third, the same experiment is assumed to generate infinitely many copies of the same experimenter, in defiance of all the norms of polite society. In short, it is possible to treat every possibility as an actuality in a different world, but at the staggering price of escaping the real world that one is expected to study. Let's face it, actuality is pregnant with real possibility. Biological evolution involves chance of the first two types, coincidence and disorder. Indeed, whereas certain phases in the evolution of the Earth favor some forms of life, they harm others. Think of continental drifts, meteoritic impacts, oceanic currents, glaciations, floods, and droughts. And once organisms emerged, they altered the composition of the soil and the atmosphere, which changes in turn induced transformations in organisms, which is why ecologists speak of the biosphere, as well as of active niche, or habitat, construction, Odlingsme, Lolland, and Feldman 2003. Then, there is often plain disorder, as when air and water currents, as well as fires and floods, disperse seeds more or less at random, as seen, for instance, in the distribution of weeds in some regions. The occurrence of chance of either kind would suffice to push conspecific organisms along different evolutionary trajectories, and thus they would end up as different species. In short, as Monod, 1970, emphasized, biological evolution is half random and half causal. Darwinism introduced what at first blush looks like a fourth concept of chance. The gist of the evolutionary notion of chance is that events are independent of an organism's need and of the direction provided by natural selection in the process of adaptation. G.T. Ebel 1999 in Gould 2002, 1036. This is the sense in which mutations are usually said to occur randomly. But this kind of chance seems to be just a particular case of the first type, since it consists in the crossing of two initially independent trajectories, those of the 99 genome and the environment. Whether or not mutations are random in the sense of being spontaneous, type 3 chance, is another matter, and one that should eventually be solved by theoretical biochemistry. Human evolution is an instance of the combination of chance processes of all three types intertwined with causal processes. Indeed, in the case of humans, in addition to genic mutation, there is creativity, conceptual, technical, artistic, ideological, and social. Indeed, we know that original ideas in any realm are inventions rather than knee-jerk reactions to external stimuli. Moreover, some innovations are non-adaptive. Think of crime, warfare, gender inequality, racism, exploitation, and the worship of cruel deities and despotic rulers. The occurrence of radical innovations renders biological and social prediction chancy. By the same token, unforeseen novelties render foolproof plans illusory. Yet of course we must plan, though making room for the unforeseen. All three kinds of chance are covered by the single formula individual irregularity underneath aggregate order. In other words, probabilistic laws in the small entail statistical regularities in the large. This is the gist of the law of large numbers and the central limit theorems of the calculus of probability. For example, although the successive high-precision measurements of a magnitude can be made to be mutually independent, their outcomes distribute ordinarily on a bell-shaped, or Gaussian, curve. That is, deviations from the mean in one sense compensate for deviations in the opposite sense. Cournot, 1843, Peirce, 1986 1878,
and a few others realized early on that the admission of objective chance necessitates a revision of the traditional ontologies, all of which had been causalist, or deterministic in the narrow sense. Peirce went as far as to claim that chance is basic, so that we should adopt what he called ethicist ontology. However, his argument was flawed, because he conflated the two main concepts of law that occur in the sciences, those of objective pattern or regularity and law statement or conceptual representation of the former. Peirce noted correctly that the latter are seldom if ever exact, as shown by the ever-present accidental, non-systematic, errors of measurement, but he concluded that reality itself is irregular. Boutru, 1898-1874, and others were led to the same mistake by the same confusion. Ampere, 1834, and, much later, a few others, example Bunge 1959b, Armstrong 1978, Meller 1991, drew the pattern statement distinction and were thus saved from the said reification. Popper, 1950, and others have suggested that the admission of chance in the ontological context requires replacing determinism with indeterminism. However, the word indeterminism suggests lawlessness, and we know that chance events have laws of their own, such as the Gauss and Poisson distributions. We 100. Also know that purely negative doctrines have no heuristic power. In general, negativism is to be avoided if only because only assertions can be precise and fertile. All of the negative mathematical, scientific, and technological statements are logical consequences of affirmative assumptions. Think, for example, of the irrationality of 2, the impossibility of a perpetuum mobile, the forbidden transitions in the quantum theory, or Arrow's impossibility theorem in social choice theory. What the admission of objective chance does necessitate is an extension of determinism to include not only causal laws but also probabilistic laws. Moreover, chance and causation, far from being mutually incompatible, may transform into one another. For example, quantum mechanics recovers the laws of classical particle mechanics as averages, Ehrenfest's theorem. 3. Objective probability. For better or for worse, the three concepts of chance distinguished above, accident, disorder, and spontaneity, are handled with the help of a single mathematical theory, namely, the calculus of probability. This is an abstract theory with three basic, undefined, primitive, concepts, those of probability space, event, and probability measure. The events in the pure theory of probability are just measurable sets belonging in the probability space, they need not be interpreted as changes of state. And a particular probability, such as 1/3, is a value of a function PR from that space to the unit real interval 0, 1, such that, if A and B are disjoint, mutually exclusive, events, then PR, AB, equals PR, A, plus PR, B. Paradoxically, the general theory of probability does not include the concept of chance, even though it is applicable only to chance events. Indeed, the general theory is just a special case of measure theory, a semi-abstract theory where the argument of the probability function are sets that may be interpreted as line segments, areas, or volumes in some space. This is why every application of the general probability calculus requires the specification of the probability space, example as the power set of the state space of entities of some kind. It also necessitates the addition of one or more substantive assumptions sketching the random mechanism in question, such as the extraction of balls from a lottery urn with or without replacement, or the spontaneous jump of an atom from one state to another. For example, quantum mechanics predicts, and spectroscopy confirms, that the probability of the 3p3's transition of the sodium atom, which is manifested as a bright yellow line, is 0.629.10, 8 per second. This probability is neither a frequency nor the strength of a belief, it quantitates the possibility. 101. Of the said event, which occurs to an excited sodium atom whether or not someone observes it. Moreover, unlike frequencies and credences, that probability is expected to approach unity, Actuality, as time tends to infinity. Notice, actuality, not certainty. That is, given time, a sodium atom in state 3p will necessarily decay to state 3s. Such a transformation of possibility into necessity goes against the grain of modal logic, which ignores time as well as natural laws, as a consequence of which it is irrelevant to science. In short, a probabilistic model M of a chance process consists of the said mathematical formalism F together with a set of substantive, non-mathematical, assumptions, M equals Fs. This concept of a theoretical model, namely, as a special factual theory, is unrelated to the model theoretic concept, which is merely a mathematical example of an abstract theory, see Bunge 1983. Yet an entire philosophy of science, namely, the so-called structuralist theory proposed by Supps, Sneed, Stegmuller, and Moulins, rests entirely on the confusion between the two concepts. The oversight of this feature of the applications of probability theory to the study of facts is responsible for many popular mistakes. One of them is the belief that any mindless application of Bayes' theorem will lead to correct results. This theorem states that the conditional probability PR, BA, of B given A, equals its inverse PR, AB, multiplied by the prior probability PR, B, and divided by the prior PR, A. In short, PR, BA, equals PR, AB, PR, B, PR, A. This formula is symmetric in the arguments, that is, A and B are mutually substitutable as long as they do not stand for facts. If they do, a mindless application of the formula may lead to ridiculous results. Here is one: let A stand for the state of being alive, and B for that of being dead. Then, PR, BA, may be interpreted as the probability of the living-dead transition in a given time interval. But, since the converse process is impossible, the inverse probability PR, AB, does not exist in this case. It is not even nil, because the death process is not stochastic. According to Humphreys, 1985, counterexamples like the preceding prove that the probability calculus is not the correct theory of chance. This remark is correct but incomplete. The failure in question shows that, to be applied, the probability calculus must be enriched with non-mathematical hypotheses. At least one of these must be the assumption that the process in question has a random component. For example, the gambler assumes that the roulette wheel is not biased, and that its successive turns are mutually independent. In the kinetic theory of gases, one assumes that the initial positions and velocities of the particles are distributed at random. The measurement errors are assumed to be mutually independent and distributed at random around zero, and Shannon's statistical theory of information assumes that the emitter, and possibly the 102 channel as well, are subject to random perturbations, which translates as white noise, the opposite of message. The axiomatic probability calculus does not involve the notion of chance because it is just a special case of measure theory, which belongs in pure mathematics. But this is no different from other pieces of mathematics. For example, the real variables x and y related by the linear function y equals a plus bx must be interpreted in factual terms if the formula is to count as a physical, chemical, biological, sociological, or economic law statement. In other words, the reason pure mathematics does not define the concept of chance is that every instance of genuine chance is a real process, hence one that can be understood only with the help of some specific factual hypothesis, such as the weakening of the interatomic bonds caused by heating a solid, or the weakening of the social bonds following a natural disaster or a social revolution. If the concept of chance were mathematical, it would be possible to concoct formulas for generating random sequences. But no such formula is conceivable without contradiction, since randomness is the opposite of mathematical lawfulness, so much so that the currently accepted definition of a random string of zeros and ones is roughly this: such a string is random if it cannot be described efficiently other than by exhibiting the string itself, see Volkan 2002.
This negative characterization is strikingly at variance with the positive ways mathematical objects are ordinarily defined, whether explicitly, by an identity, or implicitly, example by an equation or an axiom system. In other words, the concept of chance, or randomness, occurs only in the applications of the probability calculus. No randomness, no probability, see also Bunge 2003a. In other words, probability is a measure of physical real possibility, Cournot 1843, 81. Hence, it is mistaken to assign probabilities to hypotheses. For the time being, the best way to construct a random sequence is to watch nature generate one, for instance, to record the clicks of a Geiger counter in the presence of radioactive material. The next best move is to try and mimic chance, for example, to construct formulas or algorithms for generating pseudo-random sequences that come close to random distributions. But in either case one would obtain a special frequency distribution, such as Poisson's. The general concept of probability is rather abstract. By the same token, there are no tests for the presence or absence of regularity in general, only tests of some given or proposed specific regularity, Popper 1959b, 359. However, the general concept of probability allows one to define the concept of random, or blind, choice, namely, that for which all the outcomes are equally probable. See, example Feller 1968, 30. The best known example of random choice occurs in games of chance. Thus, the two possible outcomes of 103 coin flipping have the same probability, namely 1/2. But the requirement of equal probability is so strong that it is unlikely to be satisfied outside casinos. Indeed, the values of the vast majority of random, or stochastic, variables are assigned different probabilities. Think, for example, of a Bell, or Gaussian, curve for the distribution of a given biological feature, such as height, in a population. Similar distributions occur in the statistical theories of physics, chemistry, biology, social psychology, and social science. If one of the possible outcomes of a chance process is far more likely, probable, than the others, we may speak of propensity, or tendency, proneness, leaning, or bias. For example, in the game of craps, which is played with 2 dice thrown at the same time, the total 7 is 3 times more likely to turn up than 11, because there are 6 ways of getting 7, but only 2 of getting 11. In gamblers' words, the betting ratio is 6:2, or 3:1. However, this is a very special chance outcome. Hence, it is mistaken to call the objectivist, or realist, interpretation of probability the propensity interpretation, as I myself have occasionally done following Popper, 1957. This denomination is particularly wrong in the case of equiprobable outcomes, which is precisely what characterizes uniform or perfect randomness. See Figure 4.1. For probability in science and technology. The concept of chance as accidental encounter is ubiquitous in science and technology. One example among many is any queuing theory, such as a model of the times of arrival of calls at a telephone exchange, or of customers at the cash of a supermarket. Another common example is random sampling, performed routinely at the quality control phase of a manufacturing process. The simplest and most familiar procedure for building a random sequence is to flip a coin. However, this is a rather artificial example. Processes with only A, B, P, P. Figure 4.1 m, A, flat distribution, perfect randomness. B, symmetrical distribution, cancelling out of deviations from the mean. C, skewed distribution, simple propensity or tendency. D, bimodal distribution, 2 different propensities. C, D. Sigma. pp. 104. 2 equally possible outcomes are extremely rare in reality.
A far more common scientific occurrence is that of a statistical aggregate obtained by extruding individuals, such as persons, from their systems, such as workplaces and neighborhoods, and measuring a single feature of theirs, such as age, height, weight, ability, or wealth. It will be observed that the given feature distributes randomly, typically on a bell-shaped curve. Randomness is here a result of cutting bonds so as to produce mutually independent items. Physical analog: as an ice cube melts, and the resulting pool of water evaporates, the water molecules become increasingly detached and disorderly. In both cases, the physical and the social, the process has three mutually dependent features: weakening of inter-individual bonds, increasingly independent individual behavior, and increasing disorder on the micro level. These are the ideal conditions for the applicability of the probability calculus. The concept of chance as disorder occurs in the kinetic theory of gases and its generalization, classical statistical mechanics. These theories assume that a gas is constituted by comparatively distant, and therefore nearly independent, particles, atoms or molecules, and that these obey the laws of classical particle mechanics. But the theories in question also assume that the initial positions and velocities of the particles are distributed randomly rather than in an orderly manner. The two hypotheses, taken jointly, entail stochastic laws such as the Maxwell-Boltzmann distribution of molecular velocities. This law assigns a probability, or rather a probability density, to every value of the velocity. Thus, the latter is a random variable on the macrophysical level. In general, classical laws and initial randomness stochastic laws. Consider, for example, the second law of statistical thermodynamics: a closed system tends to evolve from less probable to more probable states until it reaches a state of maximum probability, which is the one of equilibrium. The probability in question quantitates the notion of objective disorder, and it is functionally related to the entropy, a measurable emergent, systemic, property of the system. A simple example is this. Take a new pack of playing cards and shuffle it many times, and honestly, to make sure that the initially ordered configuration has evolved into a thoroughly disordered mixture. The total number of possible final configurations is 52. 1050. This figure is so huge that no card player could obtain all of the permutations in his entire lifetime. Thus, whereas the initial configuration is unique, the total number of possible disordered configurations is astronomical. The probability of getting a configuration other than the initial one has increased with every shuffling. Thus, in this case probability measures disorder. 105. The situation in quantum mechanics is nearly the opposite. Here the basic laws are stochastic, and, whereas some of the derived laws are likewise probabilistic, others are not. For example, the formulas for the possible energy levels and the scattering cross-sections are probabilistic, whereas the formulas for the averages and variances of the dynamical variables, such as linear momentum and spin, are not. A famous example is that of a single electron, photon, or some other quantum, diffracted by two slits in a screen, and impinging on a detecting screen placed behind the first. Such a quantum has a definite probability of going through each of the slits, and it hits the screen at some point, very small region, on the detector. As the number of hits increases, a regular macrophysical diffraction pattern gradually emerges. Thus, individual behavior is erratic though governed by probabilistic laws, whereas the resulting collective behavior is patterned. In sum, the success of probabilistic theories in science suggests that chance is for real, that it is a basic ontological category, not a psychological or epistemological one. See, example Cournot 1843, Peirce 1935, Poincaré 1908, Du Pasquier 1926, Fréchet 1946, Bunge 1951 and 1981a, and Popper 1957. Consequently, determinism should be enlarged to accommodate probabilistic laws. This enlarged view may be termed neo-determinism, Bunge 1959a. According to this view, a. all events satisfy some laws,
whether causal, probabilistic, or mixed, and b. nothing comes out of nothing or turns into nothingness, a basic ontological principle found in both Indian and Greco-Roman antiquity, see Dragonetti and Tola 2004. The sensational success of probabilistic theories in natural science has stimulated probabilistic thinking in psychology, sociology, economics, management, and even epistemology. The idea behind this spillover is that all events, even making business decisions and evaluating truth claims, can be assigned probabilities. Shorter, it is assumed that society, and perhaps even the whole universe, is a casino, a colossal yet tacit ontological hypothesis. However, probability assignments to human actions are legitimate only in the case of trial and error behavior, which is neither typical nor efficient. For example, a subject asked to guess the sequence of letters Rfezu has only one chance in 5 equals 120 of succeeding. In all walks of life we follow rules, imitate, make educated guesses, or conduct research before acting. Trial and error is too irrational, slow, and wasteful to account for human behavior. Under total uncertainty, that is, total ignorance, the wise thing to do is not to gamble but to refrain from acting on the strength of subjective probabilities. This concludes my defense of the thesis that chance is objective. Let us now examine the opposite opinion. 106. 5. Chance as ignorance. An alternative to the realist view of chance and probability is the subjectivist doctrine. This is also known as Bayesianism because of its heavy reliance on a certain interpretation of Bayes' theorem. Bayesianism is the opinion that probabilities are just opinions, that every probability value is a measure of the strength of the belief of a person in a fact or in a statement. See example de Finetti 1972, Jeffreys 1975, Keynes 1957, and Savage 1954. This opinion was held by no less than Jacques and Daniel Bernoulli, Pierre-Simon Laplace, Augustus de Morgan, and John Maynard Keynes. More precisely, Bayesianism holds that a. probabilities are properties of beliefs, propositions, or statements, rather than of facts of a certain kind, and b. probability measures the confidence that a particular individual has in the truth of a particular proposition, for example, the proposition that it will rain tomorrow, Savage 1954, 3. Because of thesis, a. some philosophers have discussed probability with total disregard for the factual sciences of chance, such as statistical mechanics, the quantum theory, and population genetics. And because of thesis, b. Bayesianism is also rightly dubbed the subjectivist or personalist interpretation of probability. And for both reasons, Bayesianism is an alternative to the empiricist, or frequency, theory as well as to the objectivist, or realist or propensity, interpretation. For all its popularity among philosophers, and its throng of faithful among statisticians, Bayesianism is a minority view in the scientific community. Not even the upholders of the Copenhagen, or semi-subjectivist, interpretation of the quantum theory are Bayesians. They deal with facts, not beliefs. As Heisenberg excitedly told a graduate student who had started saying "I believe," "we do not do belief science here." State your reasons, Yamazaki 2002, 31. The reason scientists have to avoid Bayesianism is that, because it is subjectivist, it invites arbitrary probability assignments to anything, hardly a scientific procedure. Besides, as Venn, 1962, noted more than a century ago, any strong emotion or passion will influence our estimates of the likelihood of events. For instance, we tend to overrate the likelihood of pleasurable events, such as lottery winnings, while underrating the likelihood of disagreeable events, such as traffic fatalities. More on this in section 5. A major reason for adopting Bayesianism may be that, because it preserves most of the formulas of the calculus of probability, it confers a veneer of mathematical respectability on such fantasies as the infamous Drake formula for the probability of the occurrence of civilizations in extrasolar planets, as 107.
the product of a dozen or so probabilities of independent events, such as the emergence of planets and that of industrial civilizations. A second reason for the persistence of Bayesianism is that, since the notion of subjective probability is imprecise, it can be used to perform the facile but bogus exactification of some 20 important philosophical notions, such as those of causation, truth, evidential strength, confirmation, plausibility, and simplicity. See, example Good 1967. A third reason for adopting Bayesianism is the mistaken belief that it is the only respectable alternative to the frequency doctrine proposed by such eminent empiricists as John Venn, 1962, and Richard von Mises, 1926. According to it, probability is definable in terms of long-run relative frequency. This view is intuitively appealing to experimental scientists because it conflates chance, or randomness, with its tests, an instance of the operationist confusions of definition with test, and reference with evidence. Indeed, to determine whether a given set of data is random, one looks for certain fairly constant global properties of the set, particularly the shape and scatter, variance, of a distribution, such as the bell curve. In particular, when observed frequencies are available, one contrasts them with the corresponding calculated probabilities. But one should remember that probabilities, and probability densities, are properties of individuals, whereas the statistical parameters are properties of aggregates. Besides, statistics are restricted to past events, the only ones on which statistical parameters, such as frequencies and variances, can be counted. More in Bunge 1981a and 1988. Last, but not least, the frequency theory of probability happens to be mathematically flawed, Ville 1939. So, the frequency theory of probability must be discarded. However, contrary to popular belief, Bayesianism is not the sole alternative to it. Indeed, as suggested in the previous section, there is a tertium quid, namely, the objectivist, or realist or propensity, interpretation, the one usually employed in theoretical physics and biology. For example, the probability distributions calculated in classical statistical mechanics are deemed to be objective properties of the systems concerned. Furthermore, those distributions depend on the system's energy and temperature, neither of which can be estimated by counting frequencies. When such a count is possible, it serves to test probability estimates, not to assign them meanings. Finally, in addition to frequentism and subjectivism, there is probabilistic dualism. This comes in two varieties. A. Probability can be interpreted either as frequency or as credence, example Carnap 1950a, and B. Probability can be interpreted either as propensity or as credence, example Sklar 1993, Gillies 2000. However, this won't do because, as will be seen presently, the subjectivist interpretation is wrong. 108. Bayesianism is wrong because it originates in an ontological dogma and two major confusions. The dogma in question is classical determinism or causalism, so brilliantly described by Laplace 2 centuries ago, and certainly justifiable at his time. This is the belief that everything happens according to laws that, such as Newton's, have a broad causal domain. These laws are not strictly causal because they include the self-movement due to inertia, Bunge 1959a. If this were true, chance would indeed be but a name for our ignorance of causes, so that an omniscient being would be able to dispense with the concept of chance. However, the basic laws of quantum theory and population genetics are probabilistic, and they do not derive from causal laws. Rather, on the contrary, many a macro law is a law of averages, and it can thus be deduced from probabilistic micro-laws. So much for the error that lies at the root of the subjectivist interpretation of probability. Let us now turn to the accompanying confusions. A first confusion is that between propositions and their referents. Suppose, for example, that V designates a random variable, such as the number of points scored in a die throw. Further, call PR, V equals V, the probability that, on a given occasion, V takes on the particular value V, such as the ace. The proposition PR, V equals P involves the proposition V equals V, but it should not be read as the probability of this proposition, since such expression makes no clear sense. The gambler knows that the proposition PR, V equals 1/6 states the probability of the fact of getting an ace when throwing a well-shaken dice cup. He is interested in the outcome of a real process characterized by objective disorder, the one resulting from shaking. Likewise, the quantum physicist who writes a formula of the form PR, NN, equals P, where N and N denote two different energy levels of an atom, states that the probability of the quantum jump NN during a certain time interval equals the number P, which is analyzable into parameters that describe certain features of the atom and its environment. Indeed, the expression NN describes the objective transition in question, not the corresponding proposition, let alone the associated belief. This is why the scientist checks the formula against measurements on the atom in question rather than polling expert opinions. A second major source of Bayesianism is the confusion of objective chance with subjective uncertainty. This is a conflation between an ontological category and a psychological, and epistemological, one. To be sure, this confusion is rather natural, because indeterminacy implies uncertainty, though not conversely. For example, while one is vigorously shaking a dice cup, every one of the 6 sides of a die acquires the same chance of coming up when the die is cast. Shaking is, of course, a randomization mechanism. However, 109. Once the die is cast, determinacy has replaced indeterminacy, whereas subjective uncertainty remains as long as we do not look at the die. The Bayesian has no right to say that the probability that he will see an ace is 1/6, because the random process that culminated in this fact is over, alia jacta est. If an ace is what came up, the gambler is allowed to look, and his eyesight is normal, he will see an ace regardless of his expectations. Moreover, the gambler's mental process is quite different from the random physical process that he triggers when rolling dice, so much so that the gambler who ignores the laws of chance is bound to form irrational expectations, such as the popular gambler's fallacy: the next throw must be an ace, since no ace occurred in the last 5 throws. That is, our expectations may not mirror objective chance. If they did, neither casinos nor lotteries would be profitable. The only way to defeat chance is by cheating. 6. Uncertainty. Though inadequate for forming rational expectations, the calculus of probability includes an objective measure of uncertainty. This is the variance, or dispersion, or spread, of a distribution such as a scatter plot. The variance, or square of the standard deviation, is a function of probability. In the simplest case of a binomial distribution, when the random variable assumes only the values 0 or 1 with corresponding probabilities p and 1, p, the variance is 2 equals pp2. The shape of this curve is an inverted U around the point p equals 1/2, it vanishes at the extremes p equals 0 and p equals 1, and attains its maximum at the midpoint p equals 1/2. This particular maximal uncertainty value is 1/4, whereas the corresponding improbability is 1, p equals 1, 1/2 equals 1/2. See, example Feller 1968, 230. See figure 4.2. There are alternative measures of the objective uncertainty of a distribution. One of them is the Shannon information theoretic entropy H, which is the sum over pi log pi. This famous formula, the basis for the definition of a bit, has been overinterpreted as measuring a number of features of systems of many kinds. This is not the place to criticize these extravagances. Here we are. U. Figure 4.2. M. The uncertainty, probability relation when there are only 2 possibilities, with probabilities p and 1, p. 110. Only interested in the fact that, like the variance, H is a measure of objective uncertainty rather than of subjective or psychological uncertainty. Moreover,
This measure is similar to the variance in the case of an experiment with only two possible outcomes, like the one discussed above. Indeed, in this case h equals p log p, 1, p log 1, p, the graph of which is again an inverted U, see, example Yaglom and Yaglom 1983, 49. In short, given a probability distribution, one can calculate, among other statistics, the objective uncertainty, or indeterminacy, associated with it. This is an objective feature of the given population and the corresponding data, not of anyone's beliefs. Whether a given human subject will feel or intuit the same subjective uncertainty, is a matter for experimental psychologists to find out. In any event, the upshot is clear: improbability, or 1, p, is not an adequate measure of uncertainty, whether objective or subjective. We all know that predictions of certain kinds are dicey. However, they should not be cast in probabilistic terms if they concern non-random events, such as collisions between tectonic plates, rainfalls, crops, the onset of sickness, the outcomes of political elections, or Armageddon. True, the weather forecasts reported in the media are usually cast in probabilistic terms. But this practice is wrong, because such forecasts are not calculated with the help of probabilistic meteorology, which so far is only a research project. The meteorological probabilities in question are mere likelihoods, in the non-technical sense of the word, because they are estimated on the strength of weather records, satellite images, and measurements of the velocity of displacements of the major weather makers. See Bunge 2003 for the differences between likelihood, plausibility, and probability. As for election outcomes, the reason that they should not be cast in probabilistic terms is that such results depend on the candidate's track record and promises, as well as on carefully planned, smartly advertised, and well-financed campaigns, or even on the complicity of electoral officers and judges. Yet, two prominent academics, Kaplan and Barnett 2003, have proposed a Bayesian model for estimating the probability of winning the United States presidency. It had certainly been noted that the American political process was being privatized, but no one had suggested before that the gaming industry was about to take it over. 7. Bayesianism is confused. So far I have argued that the idea of assigning probabilities to statements originates in both outdated metaphysics and sheer confusion. However, I have yet to prove that the idea is wrong. There are several reasons why it is mistaken. One of them is that the formula the probability of statement S 111 equals P, or PR, S, equals P for short, does not include a variable denoting a person, which is not surprising since the calculus of probability is not a branch of cognitive psychology. Another objection is that propositions do not pop up or vanish at random. Of course, one could think of picking a proposition at random from a set of propositions, and ask what its probability is. But this would be just a parlor game, unrelated to the scientific search for truth. If the expression in question is intended to mean that the proposition of interest has a truth value lying between 0, total falsity, and 1, complete truth, then this can and must be said clearly, namely thus, the proposition is partially true. For example, equals 3 and our planet is spherical are approximately true propositions, whereas their negations are completely true, Bunge 2003a. However, partial truths are not probabilities. To make this point, the following counterexamples should suffice. First example, the proposition Aristotle was a Mongolian philosopher is half true, since it is true that Aristotle was a philosopher, but false that he was Mongolian. Yet, if partial truth is equated with probability, we must regard it as false, since its probability equals the product of the probabilities of the two constituent propositions, one of which is 1 and the other 0. Second example, let P be the proposition equals 1. Since the relative error incurred in making this statement is approximately 2.14/3.14 equals 0.68, the truth value of P is V, P, equals 1 to 0.68 equals 0.32. Now, the negation of P, that is, 1, is completely true. That is, V, not P, equals 1. However, if truth values were probabilities, we should set PR, not P, equals 1, PR, P, equals 1 to 0.32 equals 0.68, which is significantly smaller than 1. All the calculi cast in terms of probabilities of propositions, such as those of Reichenbach, 1949, Carnap, 1958, Popper, 1959b, and their followers, are wrong because, a, the concept of truth is more basic than that of probability, and, b, propositions, unlike random events, cannot be assigned probabilities except arbitrarily. Further reasons in Bunge 1963b. 8 beliefs are not Bayesian. Whether probabilities measure credences, or degrees of rational belief, is an empirical question. Hence, it cannot be settled a priori, the way subjectivists claim. Let us therefore ask cognitive psychologists whether people actually think in accordance with the said calculus when reasoning about uncertain matters. The many experiments of Daniel Kahneman and his students have conclusively shown that our subjective judgments of likelihood and plausibility, or verisimilitude, are often incorrect, and do not meet the axioms of the probability calculus, Kahneman, Slovic, and Tversky 1982. To begin with, when considering a branching process, such as a decision. 112. Tree, there are rarely enough data to include all the possible forks, a condition for ensuring that the sum of the probabilities over all the branches equals unity. Next, we tend to exaggerate the probabilities of certain unlikely events, such as that of contracting the West Nile virus. Fear, greed, wishful thinking, superstition, strong emotion, and association with pleasurable or painful experiences are among the factors that distort our judgments of the objective likelihood and actual frequency of an event. In short, perceived likelihood, objective likelihood. In other words, probability degree of rational belief. Furthermore, beliefs do not satisfy the probability laws. One of these is PR, A and B, PR, A, PR, B, where equality holds if A and B are mutually independent. Set A equals liberty is good and B equals equality is good. Libertarians swear by A, egalitarians by B, and neither by both. In my opinion, neither liberty nor equality is by itself a social good, or even viable, because liberty is impossible among the unequal, and forced equality muffles liberty. But it is arguable that the combination of liberty with equality is both viable and good. So, if we had a reasonable doxastics, or logic of beliefs, I would state the dual of the probabilistic inequality, namely, D, A and B. D, A, D, B. Where D would stand for a strength of belief function. In sum, the probability calculus is not a true theory of beliefs. Hence, Bayesianism is not a true account of beliefs. Which is not surprising, because the truth in question is objective, something Bayesians do not much care for. Something similar holds for the view that probability exactifies the vague notion of inductive, or empirical, support. This is essentially the idea that the conditional probability of hypothesis H given evidence E, or PR, HE, for short, must differ from the probability PR, H, assessed before having produced E. But how do we assess the prior PR, H, except by fiat? Hence how do we compare the prior probability PR, H, to the posterior probability PR, HE? And what does PR, H, mean anyway? It cannot mean plausibility or verisimilitude, because this is relative to context, and it is hardly a numerical concept. Let's face it, the so-called probabilities of hypotheses are opinions on opinions, das A squared. Yet, Bayesians claim that they hold the key to understanding the advancement of scientific knowledge, from data to hypotheses and back. For instance, hypothesis H would be confirmed by evidence E if PR, HE, PR, H. However, to my knowledge no one has been foolhardy enough to assign probabilities to any scientific laws, such as those of classical, relativistic, or quantum mechanics. Let us contrast the scientific and the Bayesian uses of Bayes' theorem, the centerpiece of both Bayesian statistics and inductive logic. As will be recalled, that theorem, which is a correct piece of neutral mathematics, reads thus: PR, AB, equals PR, BA, PR, A, PR, B. Let A and B denote two states of a concrete 113 system, PR, BA, the probability that, given that the system is in state A, it will go over to state B, and PR, AB, the probability of the reverse process. According to non-Bayesians, at least two conditions must be met to introduce these conditional probabilities into Bayes' theorem. A. Both processes, AB and BA, must be really possible, that is, they must be consistent with the pertinent objective laws, and, B. Both processes must be random, that is, describable by a probabilistic model. Yet, Bayesians require neither condition. Therefore, as noted in section 3, a Bayesian might be tempted to assign a non-vanishing probability to the impossible transition dead-alive. Furthermore, since the definition of PR, AB, involves PR, A and B, the Bayesian must admit that it is possible to be alive and dead at the same time. Incidentally, this counterexample confutes the opinion that the transition probabilities calculated in quantum mechanics and other theories are conditional probabilities. A third condition for the legitimate application of Bayes' theorem is that 3 out of the 4 probabilities occurring in the theorem be known. When the prior probabilities PR, A, and PR, B, are unknown, as is the case when A equals hypothesis H, and B equals evidence E, writing PR, HE, and PR, EH, in terms of them amounts to scribbling squiggles. And yet this is how Bayes' theorem is used in both Bayesian statistics and inductive logic. For instance, when estimating the probability of an event, or the plausibility of a proposition, the Bayesian consults a panel of experts. That is, he seeks a consensus view of informed opinion, just the way one proceeds in everyday life with regard to everyday matters, with the difference that the Bayesian assigns numbers to strengths of belief. See, Example Press 1989. True, the self-styled objectivist Bayesians equate PR, HE, to the corresponding frequency, for example, that a positive clinical test is evidence of a certain sickness, but they make up the other probabilities, in particular PR, H. Besides, in equating certain probabilities with frequencies, they violate the credo that probabilities are credences. A half-Bayesian, half-frequentist, such as Carnap, 1950a, Hacking, 1990, or Ehrman, 1992, is still a Bayesian, in that he has no qualms about committing the original sin of Bayesianism, assigning probabilities to hypotheses, jury verdicts, and the like. Moreover, he takes the two wrong sides of the controversy over probability. The occurrence of unknown prior probabilities, which must be stipulated arbitrarily, does not worry the Bayesian any more than God's inscrutable designs worry the religionist. Thus Lindley, 1976, one of the leaders of the Bayesian school, holds that this difficulty has been grossly exaggerated. And he adds, I am often asked if the Bayesian method gives the right answer, or, more particularly, how do you know if you have got the right prior probability? My reply is that I don't know what is meant by right in this context. The 114. Bayesian theory is about coherence, not about right or wrong. 359. Thus the Bayesian, along with the philosopher who only cares about the cogency of arguments, fits in with the reasoning madman. Lastly, from a methodological viewpoint, the entire debate over subjective versus objective probabilities boils down to the following argument, the second premise of which was unwittingly supplied by no less than the statistician, De Finetti 1962, 360, who started the contemporary phase of Bayesianism: if a hypothesis is untestable, it is not scientific. Now, the Bayesians maintain that a probability evaluation, being but a measure of someone's belief, is not susceptible of being proved or disproved by the facts. Bayesianism is unscientific. This should settle the question for scientific realists. But these are still a minority among philosophers, so that Bayesianism may survive for a while, along with mind-body dualism, many worlds metaphysics, and other philosophical eccentricities. Meanwhile, let us hope that it will be gradually discontinued in medicine, seismic engineering, policy making, and other fields where lives are at stake. 9. Bayesianism is heart-sardis. Unsurprisingly, Bayesianism can have catastrophic practical consequences. Let us note 3 examples. The first concerns experimental design, which is crucial in determining the efficacy and safety of drugs, agricultural techniques, social programs, and more. Since about 1930, it has been standard practice in the biosciences and the social sciences to randomize both the experimental and the control groups, see Fisher 1951. Now, Bayesians do not practice randomization because they have no use for the concept of objective randomness. For them, chance is only in the eyes of the beholder. Hence, if the U.S. Food and Drug Administration were ever to be dominated by Bayesians, it would become a public peril rather than a guardian of public health. Another example of the high risk incurred by Bayesians is the probabilistic risk assessment used by the NASA managers to estimate the risk of manned space flights in the cases of the ill-fated space shuttles Challenger and Columbia. I submit that juggling with probabilities is inappropriate in the case of the failure of components of a machine, because this is a causal chain, not a random one, such as a Markov chain, every link of which has an objective probability that depends only upon the preceding link. In general, disasters, from computer crash to early death, from bankruptcy to biospecies extinction, from hurricane to earthquake, and from epidemics to 115. War, are non-random events, hence unaccountable in probabilistic terms. True, the extinction of species and the decline of ecosystems have often been modeled assuming that the events in question are random. But they are not, for actually the dominant ecological variables are non-random. Think of rainfall, species rarity, body size, and the presence or absence of carnivores, keystone species, like starfish, and of aggressive invaders, such as elephant grass. Recent experiments have shown that ecosystems decline faster than expected if they happened by chance, Raffaelli 2004. The reason is that, when removing species, or rather populations, at random, one treats them all equally, while actually some are more important than others. In any event, the experiments in question have falsified the probabilistic models of ecosystem sustainability. Obviously, this result should have dramatic consequences for environmental policies as well as for theoretical ecology. The moral is that probability without randomness can be deleterious to the environment. Our third and final example will be the Bayesian approach to medical diagnosis and prognosis, adopted by Wolff, 1981, and many others. Since we know that the disease-symptom association is causal rather than random, there is no reason to expect that their probabilities exist and are related the way Bayes' theorem stipulates. Unsurprisingly, the available statistics concerning cancer detection fail to satisfy Bayes' formula, Eddy 1982. In sum, Bayesian medicine is unrealistic, and therefore unreliable, because it does not match the actual diagnostic process, which involves plausibility judgments based on anatomy and physiology, and to a lesser extent also on epidemiology. Much the same holds for the medical application of Popper's methodology. It, too, is unrealistic though for different reasons, namely, because, a. In medicine the only conjectures that researchers attempt to falsify are the lowly null hypotheses, which Popper and his followers have ignored, rather than high-level theories, so far non-existent in medicine, and, b. Biomedical researchers pay close attention to epidemiological data and statistical inference, neither of which is countenanced by the Popperians, see Murphy 1997.
The unrealistic nature of the Bayesian approach is of course part of its subjectivism. But Bayesians believe that this is a shining virtue rather than a fatal flaw. Thus, Howson and Erbach, 1989, 288, state that science is objective to the extent that the procedures of inference in science are. But if those procedures reflect purely personal beliefs to a greater or lesser extent, then the inductive conclusions thus generated will also reflect those purely personal opinions. This statement contains three elementary mistakes. The first is the quaint idea that objectivity resides in inference rather than in 116. Reference. Inferences are valid or invalid regardless of reference and even truth. This is why formal logic, the theory of inference, does not contain the semantic concept of reference. The second mistake of Howson and Erbach is the Bayesian dogma that purely personal beliefs have a scientific standing. If they had, religious beliefs would play a role in the finished products of scientific research. The third mistake is the statement that all scientific inferences are inductive, when in fact induction plays an insignificant role in advanced science before one reaches the stage of contrasting theoretical predictions against empirical data, Popper 1959b, Bunge 1960. No wonder that Howson and Erbach do not examine any of the scientific theories about chance events, such as quantum mechanics and genetics. Likewise, Berry and Stangl, 1996, 8, write about Bayesianism in biostatistics. Although it is comforting when two statistical analysts give the same answer, subjectivity leading to diversity is quite appropriate. Differences of opinion are the norm in health science and in science generally, so an approach that explicitly recognizes differences openly and honestly is realistic, forthright, and welcome. An obvious rejoinder to that extraordinary statement is this. First, biomedical models are expected to tell us something about diseases, not about the opinions that experts hold about them. Second, science and technology, including medicine, are not mere matters of subjective assessment or opinion. True, the 6 Sumerians would exhibit themselves in front of their houses and solicit the opinion of the passerbys. But 1 millennium later Hippocrates started transforming medical daza, opinion, into medical episteme, science. Can we afford to go back 4 millennia? It might be rejoined that any ideas can have bad consequences if handled incompetently. My point is that there is no way that Bayesianism, or alchemy, or parapsychology, can be handled competently, because it is radically false. Indeed, a. probability estimates should be just as objective as length or weight estimates, and b. probability applies legitimately only to genuine random events, such as quantum tunneling, the drips of a leaky water tap, gene mutation, the distribution of weeds in a cultivated plot, the arrival of calls at a telephone exchange, and random sampling. To appreciate the enormity of the Bayesian attempted counter-revolution, consider, for instance, the relation between the HIV virus and AIDS. It is well known that, whereas those who have this disease test HIV positive, the converse is not true. Some individuals have lived with the virus for a decade or more without developing AIDS. Suppose then that a given individual has 117 contracted that virus, and that we wish to ascertain the probability that he also has, or will soon develop, AIDS. Presumably, a Bayesian would set PR, AIDS HIV, equals PR, HIV AIDS, PR, AIDS, PR, HIV. Further, since the individual in question has tested HIV positive, our Bayesian is likely to set PR, HIV, equals 1. And, since it is known that whoever has AIDS also has the HIV virus, PR, HIV AIDS, equals 1. Thus, Bayes' formula simplifies to PR, AIDS HIV, equals PR, AIDS. However, this is known to be false. In fact, HIV is necessary but not sufficient to develop AIDS. So, if AIDS researchers were to adopt Bayesianism, they would not try to discover the causes that, jointly with HIV infection, lead to AIDS. Talk of probability without chance is pseudo-scientific and therefore imprudent, particularly if the alleged probabilities are subjective, in which case they are actually intuitive plausibilities or verisimilitudes. One should not gamble with life, peace, or truth. And one should not confuse the objective probabilities of random events with mere judgments of the likelihood of such events or the plausibility, or verisimilitude, of the corresponding hypotheses. Bunge 2003a. As Peirce, 1935, 363, put it, this confusion is a fertile source of waste of time and energy. A clear case of such waste is the current proliferation of rational choice theories in the social sciences, to model processes that are far from random, from marriage to crime to business transactions to political struggles. See Bunge 1996, 1998, and 1999. In short, Bayesian statistics and inductive logic are doubly wrong, because they assign probabilities to statements, and because they conceive of probabilities as subjective. Popper, 1959b, was right in indicting inductive logic. Regrettably, he too assigned probabilities to propositions when proposing his various theories of corroboration and verisimilitude. Popper also erred in asserting that all the probabilistic hypotheses are unfalsifiable. The probabilistic hypotheses of quantum mechanics and genetics are perfectly testable through their consequences for large masses of mutually independent events of the same kind, such as the typical radiative decays of zillions of sodium atoms, which we see as yellow light. Another mistake that Popper shared with the Bayesians is that of assessing hypotheses one by one, regardless of the conceptual systems, theories, classifications, and even worldviews, to which they belong. This was due partly to his conflating the concepts of theory and hypothesis, and partly to his severing the ties of science with the rest of culture. As a matter of fact, scientists prefer the hypotheses that are not only the better corroborated, but also best jibe with other well-confirmed hypotheses, and even with the ruling worldview. Bunge 1959b and 1967a, Thagard 1978. 118. 10. Causation and chance are not just in the mind, they are in the world as well. That is, some real processes are causal, others random, and still others have causal as well as stochastic aspects. That is, the fields of causation and chance have a partial overlap. Moreover, causation on one level may emerge from chance on another, and conversely. Furthermore, causation and chance may combine with one another on the same level, as when a causal process randomizes a collection of items, or when a random process triggers a causal chain. Besides, the expressions of the forms X is a causal process and Y is a random process should be understood as abbreviations of detailed descriptions rather than as exhaustive accounts. After all, the concepts of causation and chance are so general that they are philosophical. Note also that, though vast, the field of causation is limited to events of certain kinds. It does not include spontaneous events, such as the jump of an isolated atom from an energy level to a lower one. Nor does it include non-events, such as the permanence of a boulder on the ground. The mutual gravitational attraction of boulder and earth does not cause the acceleration of either. The causal relation obtains only between events, no change, no causation. Chance is just as real as causation, both are modes of becoming. The way to model a random process is to enrich the mathematical theory of probability with a model of a random mechanism. In the sciences, probabilities are never made up or elicited by observing the choices people make, or the bets they are willing to place. The reason is that, in science and technology, interpreted probability exactifies objective chance, not gut feeling or intuition. No randomness, no probability. In short, through finding causal and probabilistic patterns, science and technology break the phenomenalist ban on unobservables. But of course they meet the scientistic imperatives to quest, guess, and test in all human endeavors. 119. 5. Scientists and technologists endeavor to find out how things work, that is, what their mechanisms or modi operandi are.
This is how they advance from appearance to reality, and from description to explanation. By contrast, the superstitious do not look for mechanisms. For example, some parapsychologists believe in the possibility of moving things by sheer mental power, psychokinesis. If they were to inquire into the way psychokinesis works, or rather does not, they would realize that it is impossible if only because it involves the creation of energy. A similar reasoning is used in evaluating inventions. No patent is ever granted unless the inventor succeeds in explaining how the novel device works. This is why the most effective way for a patent office to deny a patent for an allegedly revolutionary design is to point out that the proposed mechanism is incompatible with a well-known law, such as the law of conservation of energy. No law, no possible mechanism, and no mechanism, no explanation. No wonder then that the hallmark of modern science is the search for mechanisms behind facts, rather than the mindless search for data and statistical correlations among them. To elucidate these ideas, and motivate the subsequent discussion, let us begin by considering a handful of examples drawn from several fields. 1. A handful of examples. Here is an example from elementary physics. Ohm and Kirchhoff described electric circuits, but did not know what makes electric charges move around them. This explanation was only provided by electrodynamics. The electric charges, electrons, in a metallic wire are dragged by the impressed electric field, voltage, and in turn the electric field that accompanies the electrons generates a magnetic field, which in turn opposes the electric current. 120. Our second example is taken from chemistry. There are several mechanisms for the synthesis of molecules out of atoms. The most prevalent of them are electron transfer and electron sharing. In the first case, one of the atoms donates an electron to the other, as a consequence of which a positive and a negative ion are formed, which attract one another electrostatically. A textbook example is the combination of a positive sodium ion Na+ with a negative chlorine ion Cl, to produce a sodium chloride molecule NaCl. By contrast to this, electrovalent bond, the covalent bond emerges when the precursor atoms share their outer electrons. The simplest example is the formation of the hydrogen molecule H2. This is not just the juxtaposition of two hydrogen atoms, since the two electrons from the precursor atoms now interpose between the atomic nuclei, protons. Here emergence results from restructuration. Another clear example is that of catalysis. Theoretical chemists want to know how catalysts, such as enzymes, work. They have known for decades that a catalyst does not work by its mere presence, as it had been believed in earlier times. A catalyst works by combining with the substratum into a short-lived complex that subsequently dissociates into the product and the catalyst. The reaction schema is S plus C SC C plus P. But in turn, why does that complex form, and why is it unstable? These problems are still under investigation. Let us now jump to the next level, that of organisms. Biological evolution had been suspected long before Charles Darwin established it. His great merit is that he explained evolution in terms of two mechanisms, inheritance with modification, and natural selection. Whereas he succeeded in describing the latter, the mechanism of the inborn modifications was discovered only many decades later. It turned out that they arise from genic mutations and recombinations, which are in turn explained in molecular terms. Focus on genes led Theodosius Dobzhansky to define evolution as a change in the frequencies of certain alleles in a population. But a frequency change, a statistical feature of a collection, is only an effect of the alterations occurring in the course of individual development. And these are changes in developmental pathways or mechanisms. Moreover, these are the roots of speciation, as recognized by the new science of evolutionary developmental biology, or EvoDevo, see, example Wilkins 2002. That is not all. To explain evolution we must add environmental factors, such as temperature, humidity, sunshine, soil acidity, and above all interactions with other organisms, for any of these factors may influence development. Such factors explain why, contrary to an earlier belief, the genetic composition of a biopopulation may show drastic changes in a short period rather than in 121. Evolutionary time. A recent example is the overfishing of cod, which has all but eliminated the fish that grow before attaining sexual maturity. In a few decades, commercial fishing has dramatically skewed the genetic pool of the cod population. This discovery suggests the need for the merger of population genetics with ecology, Roughgarden 1979. However, organisms are not passive toys of their environment, they construct their own habitats, so that biological inheritance entwines with ecological inheritance. Odlingsme et al. 2003. In short, bioevolution is explained by various concurrent mechanisms on several levels, from molecule to cell to organ to organism to biopopulation to ecosystem. Mario and Bunge 1997, Gould 2002. An interesting psychological example is the mechanism of the extinction of aversive memories, such as those of fearful episodes. This is not accomplished by Freud's mythical immaterial superego, but by the cannabinoids produced by our own bodies. Those molecules wreck the neuronal processes in the amygdala that store aversive memories. Marcicano et al. 2002. Another recent spectacular finding in cognitive neuroscience is the experimental induction of out-of-body experiences, blank et al. 2002. This is achieved, not by extrasensory means or by mystical meditation, but by electrical stimulation of the somatosensory region, body map, of the cerebral cortex. Although the details of the mechanism are still hazy, the outline is clear. Whether normal or illusory, perception is a process localized in the cortex, and thus sensitive not only to external signals but also to internal stimuli. Thus, the alleged paranormal is explained by the normal. Let us finally glance at social science. In a classic paper, Robert K. Merton, 1936, identified the mechanisms of unanticipated purposive social actions. One of them, perhaps the most pervasive, is this, with the complex interaction that constitutes society, action ramifis. Its consequences are not restricted to the specific area in which they are intended to center and occur in interrelated fields ignored at the time of action. The neoclassical economists, by contrast, ignore the very concept of a system, and consequently fail to explain the functions and dysfunctions of the economy. For instance, Ludwig von Mises, 1966, 257, an influential neoconservative economist, claimed that the market is not a thing or a collective entity, but a process. But of course there are no processes except in concrete things, recall chapter 1. And a market is a thing, in particular a concrete system, whose central mechanism and raison d'être is the exchange of goods and services. The actions of central banks and stabilization funds, monopolies and oligopolies, as well as the implementation of commercial codes and government. 122. Regulations, though not the norms in themselves, may in turn be regarded as mechanisms for the control of the trade mechanism. They may therefore be called metamechanisms. So is the application of any free trade agreement among unequal nations. It forces the weaker party to grant national treatment to foreign firms, hence to abstain from favoring national development, while at the same time the very same champions of free trade practice protectionism at home. Unfettered free trade is thus a mechanism for strengthening the stronger and thus perpetuating underdevelopment. Standard microeconomic theory focuses on market equilibrium, which it purports to explain as an outcome of the mechanism, increase in supply, drop in price, rise in demand, price hike. Regrettably, this zigzagging and self-correcting mechanism works better in textbooks than in real markets, for it ignores oligopolies and state subsidies, and it overlooks persistent market disequilibria, in particular gluts, chronic unemployment, and the irregular and sometimes enormous fluctuations of financial markets. See Bunge 1998 for further criticisms of standard economic theory. The economic sociologists have been baffled by the steady rise of income inequality in the United States and other countries since about 1980,
Despite spectacular gains in both productivity and gross domestic product, the so-called Great U-turn. Several mechanisms, operating concurrently, have been proposed to explain this trend, notably the following ones, which are involved in globalization: Anderson and Nielsen 2002, the deindustrialization caused by the export of manufactures, the cheapening of low-skill labor, and the weakening of the bargaining power of labor consequent upon both anti-labor legislation and the increased labor supply. Thus, as Hobson, 1938-1902, observed a century ago with regard to the British Empire, economic imperialism is self-destructing in the long run. Here is a clear politological example: democracy is a social mechanism for resolving the problem of societal decision-making among conflicting interest groups with minimum force and maximum consensus, Lipset 1959-92. Of course, democracy is also the mechanism allowing for political participation and civic responsibility. By contrast, dictatorship, unprovoked military aggression, and state terrorism are by far the most destructive, divisive, and irrational, and therefore also the most barbaric and immoral, of all the social mechanisms. Social mechanisms have two peculiarities: they are purposeful, and they are linked. For example, democracy may be regarded as a mechanism for favoring participation, the latter is a mechanism for reinforcing social cohesion, which favors stability, which reinforces democracy. The four mechanisms are thus linked in a self-sustaining causal chain, and so are their duals. See Figure 5.1. 123. The moral should be clear, whereas the constructive mechanisms should be oiled and repaired whenever necessary, the purely destructive ones should be thwarted. For example, the mechanism of grassroots terrorism is the self-sustaining cycle: provocation, terrorist attack, retaliation, provocation, terrorist attack. We won't understand what maintains such an irrational cycle if we keep repeating the conventional explanation, that terrorism results from a combination of poverty with ignorance. Social psychologists and sociologists have found that most kamikaze pilots and suicide bombers were well-educated members of the middle class. Only further investigation can disclose the grievances, frustrations, and religious superstitions that led them to seek martyrdom. Atran 2003. The ability to tamper with mechanisms is particularly important in technology. For instance, immunologists and epidemiologists know that vaccination protects against infectious diseases because it induces the synthesis of the appropriate antibodies. And normative epidemiologists can calculate the minimum level of vaccination that will prevent an epidemic because they know that, above a certain threshold, infection will propagate through contact until all but the naturally immune individuals have been struck. Thus, the prevention and management of infectious diseases rests on a body of theoretical epidemiology centered on the infection mechanisms, rather than on dubious inductive inferences from observed samples. See example Anderson and May 1991. In general, statistical correlation explains nothing, it is what cries for explanatory models, whether deterministic, stochastic, or mixed. And efficient control is based on knowledge of dynamics. Most epidemiological generalizations and correlations that are not backed up by solid hypotheses about mechanisms at best stimulate research, and at worst are unjustified alarm calls. For example, a strong positive or negative correlation between two features X and Y only indicates covariation, as in the case of stature and body weight. Only further research might establish that changes in X cause changes in Y, or conversely, or that both depend on the changes of a third variable Z. The moral is obvious: look for mechanisms behind every interesting strong correlation. For example, the U-shaped relation between morbidity and body mass index, BMI, is an indicator of nutrition habits, in particular both malnutrition, for small values of BMI, and excessive food intake, for large values of BMI. A technology can be effective but not efficient, that is, it may work but only at a high cost. The classical example is Roman engineering, characterized by reliability and durability ensured by excessive bulk. Efficient technology rests on well-confirmed mechanismic hypotheses. By contrast, the inefficiency of pseudo-technology is due to the non-existence or ignorance of the relevant mechanisms. For example, it is known that magic, intercessory prayer, water dowsing, feng shui, homeopathy, faith healing, and psychoanalysis fail. See, example Kurtz, ed. 2001. The reason is that they do not rely on any real mechanisms other than the placebo effect, that is, plain suggestion. Incidentally, we still do not know the neurocognitive mechanism whereby suggestion works. However, there are good reasons to suspect that words and placebos are effective to the extent that they trigger physiological processes that start in the cortex and are likely to involve the release or the blocking of neurotransmitters that activate or inhibit the formation of neuron assemblies. The relevance of mechanism to understanding and control is such that it is not uncommon to find in the scientific literature apologies of the form "unfortunately, no mechanism is known to underlie the fact or the equation in question." For example, nobody believed in allergies until it was explained in terms of antigen-antibody reactions. Physicians do not believe in homeopathic nostrums, except as placebos, because there is no mechanism whereby a few molecules of any active principle could affect entire organs. And scientific psychiatrists do not believe in psychoanalytic stories, not only because they lack experimental validation, but also because they are not backed up by any known brain mechanisms. But at least we know about sex what Freud did not, namely, that the most important sex organ is the brain. In all of the above scientific examples, a mechanism was conceived of as a process, or sequence of states, or pathway, in a concrete system, natural or social. Besides, most mechanisms are concealed, so that they have got to be conjectured. This suggests the plan of this chapter: system, mechanism guessing, and explanation. These and other concepts will only be sketched and exemplified here, they are elucidated in detail elsewhere. Bunge 1964, 1967a, 1968b, 1979a, 1996, 1997, 1998, 1999. 2. System and Systemism. The Baron D. Holbach, 1773, one of the major encyclopedists, should be credited with having joined materialism with systemism. Indeed, he seems to 125. Have been the first to state not only that all existents are material, but also that everything, both in nature and in society, hangs together. This ontology, systemic materialism, prospered in the natural sciences, all of which study material systems, whether tangible like nervous systems, or intangible like molecules and social systems. Systemic materialism has been far less popular in the field of social studies, where individualism and idealism have ruled. Still, some social scientists have realized that what they study are social systems. Thus, the greatest economist of the 20th century, I am chiefly concerned with the behavior of the economic system, as a whole, Keynes 1973, XXXII, likewise Vasily Leontiev, whose input-output matrices concern national economies. Kenneth Boulding, 1964, preached the systemist gospel in the desert of mainstream microeconomics. Fernand Braudel's most famous work, 1972, concerns no less than the entire Mediterranean basin. And Henry Ford asserted that mass production, unlike craftsmanship, is ruled by three maxims: system, and more system. However, most social scientists abstain from using the expression social system even while studying social systems or designing policies to alter them. In short, systemic materialism has done very well in the natural sciences, and marginally well in the social and biosocial ones. On the other hand, it has not prospered at all in the humanities. Along with scientism, another candle of the Enlightenment, it was snuffed out by philosophy professors in the 19th century, and has remained in the hands of amateurs. What prevailed in academia were Hegel's idealist holism and the idealist individualism of Dilthey and Rickert, Max Weber's philosophical mentor. The counter-enlightenment has triumphed to such an extent that the ideas of the encyclopedists are hardly taught in our universities. True, a few anthropologists and sociologists, in particular Radcliffe Brown, Parsons, Luhmann, and Habermas, have written extensively about social systems. However, some of them, particularly Parsons, 1951, and his follower Luhmann, 1984, emphasized equilibrium, just like the neoclassical microeconomists. To them, a social system is basically in a steady state, and all change is either a departure from stasis or a return to it, as if change were abnormal rather than the rule. Besides, the static systemists regarded social systems as disembodied bundles of values, norms, actions, or communications. Unlike Holbach, they were systemists but not materialists. A few other scholars, such as Gittins, 1984, have conflated system with structure, as if a structure could exist independently of the entities that it binds. Still others, particularly systems engineers such as Ashby, 1963, have called system any black box with inputs and outputs, or even just a list of variables, with disregard for stuff, structure, and mechanism. In other words, they have adopted a functionalist point of view. 126. Because the word system is used somewhat loosely in the social sciences, it will be convenient to adopt a definition of it. I use the following one: a system is a complex object whose parts or components are held together by bonds of some kind. These bonds are logical in the case of a conceptual system, such as a theory, and they are material in the case of a concrete system, such as an atom, cell, immune system, family, or hospital. The collection of all such relations among a system's constituents is its structure, or organization, or architecture. This concept of a structure is borrowed from mathematics. A large number of alternative notions, none of them clear, were introduced in the 1950s, when the word structure suddenly became fashionable in the humanities and social studies. See, Example Center International de Synthèse 1957. Depending on the system's constituents and the bonds among them, a concrete or material system may belong to any of the following levels: physical, chemical, biological, social, or technological. The semiotic systems, such as languages and diagrams, are hybrid, for they are composed of material signs or signals, some of which convey semantic meanings to their potential users. The simplest sketch or model of a material system is the list of its composition, environment, structure, and mechanism, S, or equals. Here, C, denotes the set of parts of E, the collection of environmental items that act on or are acted upon by S, the structure, or set of bonds or ties that hold the components of together, as well as those that link it to its environment, and M, the mechanisms, or characteristic processes, that make what it is and the peculiar ways it changes. Note that we distinguish a system from its model, S, just as the electrician distinguishes an electric circuit from its diagram, S. Note also that, contrary to Glennon, 2002, we distinguish a system from its mechanism, S. All four components of the model are taken on a given level, such as the person, the household, or the firm in the case of social systems. They are also taken at a given time. In particular, M is a snapshot of the processes that go on in the system in question. In turn, a process is a sequence of states. If preferred, it is a string of events. And, whereas the net effect of some processes is to alter the overall state of the system, that of others is to maintain such state. For instance, a sailboat is moved by wind, whereas the impacts of myriad water molecules on the hull keep it afloat. And what keeps a business firm above the market water is the sale of its products. The most familiar example of a social system is the traditional nuclear. 127. Family. Its components are the parents and the children,
The relevant environment is the immediate physical environment, the neighborhood, and the workplace. The structure is made up of such biological and psychological bonds as love, sharing, and relations with others, and the mechanism consists essentially of domestic chores, marital encounters of various kinds, and child rearing. If the central mechanism breaks down, so does the system as a whole. The neoclassical economists, obsessed like shopkeepers by price competition, failed to grasp the central mechanism of the capitalist economy, innovation. Schumpeter, 1950, 83, unveiled it in a single magisterial page. He saw that what sets and keeps the capitalist engine in motion is nearly incessant creative destruction. This is the introduction of qualitatively new consumer goods, new methods of production and transportation, new types of organization, and so forth, and the concomitant destruction of their precursors. This is what he called an organic process, that is, one that affects the entire economic system. It also has political and cultural repercussions, as when business captures political parties, and when the great literary, musical, and plastic arts classics are displaced by mass-produced pseudo-artistic merchandise. Nor is creative destruction limited to material products, it can also affect dreams and myths. One example is the so-called new economy of the mid-1990s, centered on the illusion that e-commerce would replace snail commerce. A related illusion was the Nasdaq bubble, favored by the artificially low discount rate decreed by the U.S. Federal Reserve Bank, that alleged bulwark of free enterprise. The same government agency also helped form huge and vulnerable industrial conglomerates, some of which declined precipitously, while others existed only on paper. Both bubbles were punctured at the dawn of the new millennium. They might not have been formed if a materialist ontology had prevailed, that is, if it had been realized that paper bulls do not charge. Another topical subject is terrorism. Regrettably, knowledge of organized violence is poor, and as a result its prevention is inefficient. In particular, the most popular view of grassroots political terrorism is that it is incited by some fanatical, perverse, or demented individuals. While some terrorist leaders do meet this description, it does not explain either the devotion and abnegation of numerous terrorist foot soldiers or the persistence of their causes. In any event, a successful war, or rather mobilization, against group-sponsored terrorism must start by understanding it as a low-budget war from below. The first thing to understand about terrorism is that it comes in two main kinds, state-instigated and group-sponsored, and that the former is by far the more immoral and lethal of the two. State terrorism is the easier to explain because it has a single source, namely, the ruling elite, and a single goal. 128. Namely, the suppression of dissent. By contrast, group-sponsored terrorism usually attracts people from different walks of life, and is a mechanism of the weak for redressing at once grievances of various kinds, economic, natural resources or jobs, political, social order, and cultural, in particular religious. Any anti-terrorist campaign that does nothing to meet genuine grievances is bound to work, at best, only in the short term and at the cost of civil liberties. In general, systemic issues call for systemic and long-term solutions, not sectoral and near-sighted measures. In particular, social violence stems from us/them barriers. Hence, it is best tackled by removing the barriers in question. For example, the Arab/Jewish confrontation is likely to be solved only by mixing both populations rather than by strengthening the barriers between them. Joseph Agassi, Personal Communication. This is a practical message of systemism. The twin concepts of system and mechanism are so central in modern science, whether natural, social, or biosocial, that their use has spawned a whole ontology, which I have called systemism. Bunge 1979a, 2003a. According to this view, everything in the universe is, was, or will be a system or a component of one. For instance, the electron that has just been knocked off an atom on the tip of my nose is about to be captured by a molecule in the air. and the prisoner who just escaped from the county jail is about to be either recaptured or absorbed by a family or a gang. There are no permanent strays or isolates. Systemism is the alternative to both individualism and holism, Bunge 1979a and 1979b, Stompke 1979. Presumably, it is the alternative that the historical sociologist Norbert Elias, 2000, was looking for in the late 1930s, when he felt dissatisfied with the conceptions of the person as the self-contained homo clauseus, and of society as a black box above individuals. Arguably, systemism is the approach adopted by anyone who endeavors to explain the formation, maintenance, repair, or dismantling of a concrete complex thing of any kind. Notice that I use the expression systemic approach, not systems theory. There are two reasons for this. One is that there are nearly as many systems theories as systems theorists. The other is that the systems theory that became popular in the 1970s, example Laszlo 1972, was another name for the old holism, and got discredited because it claimed to solve all particular problems without empirical research or serious theorizing. However, just as Monsieur Jourdain spoke prose without knowing it, so most scientists practice systemism without mentioning it. Thus, in his highly original and monumental work on early civilizations, Bruce Trigger, 2003a, studies the physical environment, economy, polity, and culture, in the sociological sense of this word, of each of the 7 early civilizations he examines. 129. Moreover, he stresses the interdependence of those various components or aspects of society, and describes the mechanisms that gave rise to the state and its functions, such as social control, public works, and state-sponsored cultural activities. Trigger also adopts explicitly a materialist ontology, though certainly not the vulgar materialism that denies the importance of ideas and rituals, Trigger 2003b. That is, Trigger has successfully adopted the materialist systemic approach, just like Fernand Braudel and his colleagues in the Annals. However, one will look in vain for the expressions social system, social mechanism, and systemic approach in that work. Likewise, the ancient Egyptians, though deeply religious, had no word for religion. All of which shows once more, against Wittgenstein and his school, that ideas can thrive without the corresponding words. Systemism is just as comprehensive as holism, but, unlike the latter, it invites us to analyze wholes into their constituents, and consequently rejects the intuitionist epistemology inherent in holism. For example, whereas holistic medicine claims to treat patients as wholes, without regard for the specificity of their subsystems, scientific medicine treats patients as supersystems composed of several interdependent systems. Likewise, whereas revolutionaries advocate total and instant changes of society as a whole, systemic social reformers favor gradual reforms of all the ailing subsystems of society. The systemic approach advocated here is not a theory to replace other theories. It is, instead, a viewpoint or strategy for designing research projects whose aim is to discover some of the features of systems of a particular kind. Although this approach is routinely used in science and technology, it is part of philosophy, and the latter is not equipped to tackle empirical problems. Philosophy can facilitate or block scientific research, but it cannot replace it. 3. Mechanism. As stated above, mechanisms are processes in concrete, material, systems, whether physical, social, technical, or of some other kind. Biochemical pathways, electrical and chemical signals along neural networks, sexual competition, division of labor, publicity, polls, and military expeditions are mechanisms. By contrast, the conceptual and the semiotic systems, such as theories and languages respectively, have compositions, environments, and structures, but no mechanisms. The reason is that changeability, or energy, is the defining property of matter, whether physical, chemical, living, social, or technical. To coin an ambiguous slogan, to be material is to become. The ontological concepts of system and mechanism are central to modern science and technology. Even when they study elementary particles, they 130 inquire into the systems and mechanisms in which they become involved. The following examples should suggest that the same holds for the social sciences. Our first example is Kondratiev's long waves of economic activity, which have drawn the attention of economists and historians from Schumpeter, Kuznets, and Brodel onwards. However, the very existence of such decades-long cycles has been questioned for 3/4 of a century, because it is not clear what their underlying mechanism might be. Still, one plausible mechanism hypothesis is this: obsolescence of the dominant techno-economic system, new techno-economic system, and social changes, market saturation, drop in prices. Berry, Kim, and Kim 1993. A topical example from politology is this: the flaws of American democracy, such as the high cost of running for political office, and the concomitant intimate relationship between political parties and corporations, are turning young people away from politics. In turn, this voluntary disempowerment is one of the imperfections of that democracy, and it erodes even further political participation, which is the main democratic mechanism. Concurrent mechanisms are the application of the rule of law, education, voting, honest vote counting, and the free formation and circulation of information conveying reliable knowledge. This is a case of feed-forward, self-amplifying control. And it explains why political apathy leads to bad government. Indeed, when the competent and honest citizens tend to stay away from politics, the incompetent and dishonest take over, which may be called Gresham's law of politics. Finally, an example from culturology. The cultural poverty of contemporary Islam, with its nearly total absence of original science, technology, philosophy, and art, stands in stark contrast to the brilliance of its culture in the Middle Ages. This fact is an aspect of a multifaceted stationary process. While today's Islamic societies, particularly those rich in the devil's juice, have imported some of the trappings of modern industry, such as cars and cell phones, most of them have kept a traditional social structure. Indeed, they have discouraged or even banned the quest for novelty, economic, political, and cultural, which is precisely the quest that built modern capitalism and keeps it going. The highly complex systems, such as living cells and schools, have various concurrent mechanisms. That is, they undergo several more or less intertwined processes at the same time and on different levels. For example, a cell does not cease to metabolize during the process of division. A waking brain engages in a number of parallel processes: biochemical, vascular, cognitive, emotional, and motor controlling, and the people who compose a school metabolize and socialize at the same time that they learn, teach, manage, or gossip. The coexistence of parallel mechanisms is particularly noticeable in biology. 131. Cal and social systems. For example, bioevolution is driven by several intertwined mechanisms, among them genetic change, natural selection, and niche construction. Human social evolution is driven by production and exchange, cooperation and competition, and much more. Think, for instance, of the mechanisms operating in a scientific community: research, the truth-finding mechanism, criticism and peer review, social quality control mechanisms, and a combination of cooperation in the search for truth with competition in the allocation of credits and resources. Because a number of mechanisms may operate in parallel in one and the same system, and because some of them may interfere with one another, it is convenient to distinguish essential from non-essential mechanisms. See Sconwan 2002. The former are those peculiar to the systems of a certain kind, whereas the latter may also occur in systems of a different kind. For example, contraction is essential to a muscle but inessential to a cell, and loaning money is essential to a bank but optional to a manufacturer. We are now ready to propose and refine this definition: an essential mechanism of a system is its peculiar functioning or activity. In other words, an essential mechanism is the specific function of a system, that is, the process that only it and its kind can undergo. More precisely, we propose the following stipulations, based on the concept of a specific function defined elsewhere, Bunge 1979a. Definition 1. If denotes a system of kind, then, 1. The totality of processes, or functions, in over the period t is equals the ordered sequence of states of over t. 2. The essential mechanism, or specific function, of over the period t, that is, m equals s. S is the totality of processes that occur exclusively in and its conspecifics during t. Definition 2. A social mechanism is a mechanism of a social system or part of it. Note that the concepts of goal and utility are absent from the above definitions. The reason is of course that some mechanisms are ambivalent, and others have unintended negative consequences. For example, free trade may make or undo a nation, depending on its competitiveness, aggressiveness, and political, in particular military, power. However, the concepts of goal and utility do occur in the characterization of the mechanisms in highly evolved brains like ours. One may also speak of the goals of artifacts, in particular formal organizations, only elliptically, though, because intentionality is a peculiarity of individual brains. In the case of social systems, an essential mechanism is a process that brings about the desired changes, or else prevents the undesirable ones. Only this very particular case is 132. Covered by Merton's well-known definition of social mechanisms as the social processes having designated consequences for designated parts of the social structure, 1968, 43. 4. Causal and stochastic mechanisms. A causal mechanism is of course one ruled by causal laws, such as those of classical electrodynamics or classical ecology. An example of such a mechanism is the electromagnetic induction that drives electric motors in accordance with Maxwell's equations. Another is the oscillation of the populations of organisms of competing species according to the Lotka-Volterra equations. A third is the cooperation between two persons, or two social systems, according to definite, though not necessarily explicit, norms, such as that of reciprocal altruism. A fourth example is a negative feedback mechanism such as Watt's regulator of steam pressure. However, all causal processes are affected by some random noise, as illustrated by the fluctuations in electronic circuits and by accidental errors of observation. There is a natural tendency to think of all processes, hence all mechanisms, as causal, or deterministic in the narrow sense. Thus, a chemical reaction is usually conceived of as a causal process, or mechanism, for the emergence of a product from one or more reagents. However, quantum chemistry shows that this is only an aggregate effect. An individual or microchemical reaction is a process with an important random component. For example, a reaction of the type A plus BC is to be analyzed as the random scattering of S by Bs, with a certain probability that Cs will emerge. Roughly, the expected number of molecules of kind C resulting from N collisions of S with Bs, each with probability P, is Np. Caution, this is not a process of the bottom-up type, because the value of the probability depends critically upon such macrophysical variables as temperature and pressure, which in turn are emergent macro properties of the environment in question. There are plenty more stochastic, or random, processes, such as those of random walk, random self-assembly, lottery, random extraction of balls from opaque urns, atomic collision, and genic mutation. However, arguably all of these random processes have a causal component. For example, the balls in a lottery urn are pulled by gravity, the particles in an atomic collider are accelerated by electric and magnetic fields, and genes are activated and deactivated by enzymes. It is doubtful that there are purely causal or purely random processes, and hence mechanisms, recall Chapter 4. At first sight, there is a third category of mechanism besides causal and random, namely, chaotic. However, most known cases of chaos are particular cases of causation, namely, those whose outcome, like that of a roulette game, 133. Depends critically upon the initial conditions. After all, most chaos-theoretic equations do not involve probabilities. 5. Mechanism and function. Sometimes mechanisms are called functions. This conflation is not advisable when one and the same task can be performed by different mechanisms, the case of functional equivalence. For example, some quadrupeds can advance by walking, crawling, or swimming, documents can be reproduced by printing presses, mimeographs, and photocopiers, markets can be conquered by force, dumping, free trade agreements, or even honest competition, and certain goods can be sold in markets, retail stores, department stores, or through the internet. Because the functions, mechanisms relation is one-to-many, we should keep the two concepts distinct while relating them. Another reason is that a purely functional account, such as cars are means of transportation, though accurate, is superficial because it does not tell us anything about the peculiar mechanism whereby the function in question is carried out. See Mario and Bunge 2001. Some of what holds for our knowledge of cars also holds for that of systems of other kinds, such as towns. For example, it is not enough to know that African Americans tend to self-segregate in cities because they like to live among themselves. One must add that they are actively discriminated against, and even received with hostility, if they attempt to move to predominantly white neighborhoods. Schelling, 1978, 139, notwithstanding, racial segregation is not voluntary but the result of active racial discrimination. The latter is the invisible mechanism that manifests itself as segregation. Another reason for keeping the mechanism-function distinction is that, unlike mechanisms, the functions they accomplish are ambivalent. Indeed, as Merton, 1968, 115, noted, social functions can be either manifest or latent, unintended. Besides, social mechanisms generally have dysfunctions as well as functions. Thus, the manifest function of the peer review mechanism is quality control, but one of its latent functions, or rather dysfunctions, is to entrench cliques and perpetuate their beliefs. Thus, intellectual quality control may be perverted into the control of thought and power. There are no universal mechanisms, hence no cure-all procedures. All mechanisms are stuff-dependent and system-specific. For instance, only carbon has the versatility required to enter in the vast majority of the chemical reactions that keep an organism alive. Only live brains, provided they have been properly trained and primed, can engage in original research, and only brains in certain abnormal states can hallucinate. However, mechanisms, like anything else, can be grouped into natural. 134 kinds, such as those of fusion and fission, aggregation and dispersion, cooperation and competition, stimulation and inhibition, blocking and facilitating, and so on. The formal analogies among mechanisms involving substrates or stuffs of different kinds facilitates the task of mathematical modeling, since one and the same equation, or system of equations, may be used to describe mechanisms involving matter of different kinds. For example, one and the same system of equations may describe cooperation and competition among organisms, in particular people, or among chemicals, see, example Bunge 1976. Likewise, mechanisms of the so-called yin-yang kind, made up of couples of entities with opposing functions, such as stimulation and inhibition, or oxidation and reduction, are instantiated by molecules, neurons, social systems, and more. However, the functional and structural models and simulates are unavoidably shallow because, in ignoring stuff, they overlook mechanisms. And such oversight prevents the recognition of specific differences and qualitative novelties. For instance, dust specks, germs, seeds, ideas, habits, and artifacts diffuse, but their diffusion mechanisms are very different, some are physical, others biological, and still others social. Hence, we must disclose such mechanisms if we wish to either facilitate or hamper the spread of the stuff in question. Thus, the functionalist approach, which discards stuff and therefore overlooks mechanism, is bound to fail in practice as well as to set limits on research. Functionalism has been particularly pernicious in molecular biology and psychology. Indeed, in both fields it has discouraged the search for mechanisms, and it has promoted the idea that flowcharts provide explanations, when in fact they only supply global descriptions. For example, to state that messenger RNA acts as a blueprint for, or that it specifies, proteins is only a metaphorical description of protein synthesis. To understand this process in depth we need to know in detail the chemical reactions that produce the proteins in question. In other words, the processes of transcription, DNA-RNA, and translation, RNA-protein, can only be understood in terms of intermolecular forces. Likewise, psychology won't explain much as long as it does not advance from the information processing metaphor to the neural mechanism. 6. Mechanism and law. How are the concepts of mechanism and law statement related? John Elster, 1998, 48, has claimed that the antonym of a mechanism is a scientific law. Accordingly, explanations by reference to mechanisms would replace expla. 135. Nation by reference to law statements. This opinion is mistaken. Elster seems to have been misled by his examination of only a few cases of two kinds, a. known mechanisms with unknown laws, and b. known laws with unknown underlying mechanisms. But the fact that the pertinent mechanismic laws are unknown in certain cases, indeed in most, does not prove that they do not exist. Mechanisms without conceivable laws are called miracles. For instance, Thomas Aquinas held that the Holy Ghost grafts the soul onto the human embryo, and John Ecclesiastes once speculated, in the revered journal Nature, that the mind moves neurons through psychokinesis, or telekinesis. Surely, these hypotheses are mechanismic, but they are also unscientific, because they are inconsistent with the relevant laws, none of which refers to immaterial entities. I submit that scientific research presupposes, a. materialism, or the hypothesis that the real world is material, so that it contains no autonomous, subject-free, ideas, and, b. the principle of lawfulness, according to which all events satisfy some law, s. Trust in the first principle allows scientists to dispense with the ghostly. And trust in the second principle sustains their search for laws and the rejection of miracles. Elster's opinion, that mechanism is the opposite of scientific law, is falsified by the following counterexamples. Statistical mechanics explains thermodynamics in assuming that the elementary constituents of a thermodynamic system abide by the laws of classical mechanics. Wave optics explains ray optics in proving that light rays emerge from the interference of light waves. Molecular biology explains Mendelian genetics in proving that the heredity material consists of DNA molecules, some of which code for proteins, and thus ultimately control such biomechanisms as metabolism, cell growth, and cell division. Incidentally, the last two mechanisms are governed by the logistic curve, which is also that of learning driven by external reward. What is true is that, in social studies, law and mechanism are necessary but insufficient to explain, because almost everything social is made rather than found. Indeed, social facts are not only law-abiding but also norm-abiding, and social norms, though consistent with the laws of nature, are not reducible to these, if only because norms are invented in the light of valuations, besides which every norm is tempered by a counter-norm, as Merton, 1976, pointed out. In any event, mechanism and law can be uncoupled only in thought. An explanation by reference to mechanism deepens subsumption instead of replacing it. The differences between the two kinds of explanation, subsumptive and mechanismic, as well as their commonalities, emerge clearly upon analyzing them logically. Let us do this in two simple cases. Consider the well-known empirical generalization taking ecstasy causes. 136. Euphoria, which makes no reference to any mechanisms. This statement can be analyzed as the conjunction of the following two well-corroborated mechanismic hypotheses,
Taking ecstasy causes serotonin excess and serotonin excess causes euphoria. These two together explain the initial statement. Why serotonin causes euphoria is of course a separate question that cries for a different mechanism. Incidentally, the preceding example disproves Ravunchio's 2001 assertion that explanation via mechanism is not available outside physics, in particular in cognitive neuroscience. An example from sociology and management science could be this: the inertia resistance to change of a social system is proportional to its size. This explains why even friendly takeovers, which require quick adaptations, are hazardous to corporations. In turn, the relevance of size to inertia is explained by the need for face-to-face, or at least screen-to-screen, contacts to maintain the cohesion of the system, and thus ensure its behaving as a unit. To put it schematically, we have split the initial statement bulkiness, inertia into bulkiness, contacts and contacts, inertia. The previous argument is clarified when expressed with the help of the standard symbolism of elementary logic. We started with a law statement of the form x(x, bx, and analyzed it as the conjunction of hypotheses of the forms x(x, mx, and xmx, bx, where m refers to a key feature of some mechanism. All real mechanisms are lawful, but the law's, mechanisms relation is one-to-many rather than one-to-one. For example, the oscillations in the price of any stock look like a random walk, superficially similar to the motion of a molecule in a gas, and the exponential function describes both the growth of a population with unlimited resources and that of scientific papers. There are two main reasons for the laxity of the law's mechanisms coupling. One is that any given input-output relation, or black box, can in principle be mediated by different mechanisms, or translucid boxes. See Figure 5.2a. The second reason is that the macro-level laws relate global features, such as growth or decline, concentration or dispersion, that are compatible with alternative microprocesses. See Figure 5.2b. Because the patterns, mechanisms relation is one-to-many, the search for either can be uncoupled from the search for the other. However, barring miracles, there are no lawless mechanisms any more than there are mechanism-less patterns. Hence, any mechanism-free account must be taken to be superficial and therefore presents a challenge to uncover unknown mechanism, s. By the same token, any mechanism unsupported by some law, s, must be regarded as ad hoc, and therefore equally transient. In sum, satisfactory, and psychologically satisfying, explanations of both. 137. Kinds, if scientific, resort to law statements. So, mechanismic hypotheses are not an alternative to scientific laws, but are components of deep scientific laws. In other words, mechanism, or translucent box, opposes phenomenological, or black box, not lawfulness, see Bunge 1964, 1967a. 7. Guessing mechanisms. How do we go about conjecturing mechanisms? The same way as framing any other hypotheses, with imagination both stimulated and constrained by data and well-weathered hypotheses. Let us consider a few examples. Altruism and cooperation among humans are about as frequent as selfishness and competition. Why is this so? That is, what mechanism drives either behavior? Most sociobiologists claim that, because altruism and cooperation are expensive, they are confined to relatives. Accordingly, spouses, adopted children, and close friends should not expect help in emergencies. That is, the animal would have an unconscious desire to protect and spread its own genes. This is the kin selection hypothesis, the psychological counterpart of Richard Dawkins's selfish gene conjecture, according to which organisms are only gene carriers. Though popular, the kin selection hypothesis runs counter to the empirical evidence that there is cooperation among non-relatives, as well as rivalry, sometimes even violence, among kin, see, example West et al. 2002. Moreover, transgenic relationships can be more loving than same-species ones. Thus, the American President George W. Bush declared once that his dog is the son he never had. An alternative hypothesis is that cooperation occurs regardless of kinship if its benefits exceed its costs. Conflict would be parallel. See, example Odlingsme et al. 2003, 298 ff. Besides, we do good deeds because it feels good to do good even if we do not expect to be repaid. In fact, recent brain imaging studies, Rilling et al. 2002, on people playing prisoner's dilemma games have shown that we feel good when behaving cooperatively towards strangers. Input mechanism macroproperty A macroproperty B. Output microproperty M. Figure 5.2 M, A, an input-output relation mediated by a mechanism. B, two macroproperties related via a microproperty. A, B. 138. Certain neuronal systems in charge of reward, pleasure, light up in the process. An alternative is that humans and other animals tend to cooperate among themselves because they need help and expect reciprocity. These two hypotheses are of course mutually compatible. Thus, presumably cooperation involves at least two intertwining mechanisms on many different levels, cellular and social. There is no method, let alone logic, for conjecturing mechanisms. In general, hypotheses, as Peter Medawar put it, appear, along uncharted byways of thought. True, Peirce wrote about the method of abduction, but abduction is synonymous with conjecturing. And, as he himself stated, this is an art, not a technique. One reason is that, typically, mechanisms are unobservable, and therefore their description is bound to contain concepts that do not occur in empirical data. This is why mathematical modeling is often used to identify mechanisms. It is not that the core of reality is mathematical, but that only mathematical thinking can cope with complexity. Even the mechanism that makes the pendulum clock tick involves unobservables such as the gravitational field and inertia. Likewise, the elastic energy stored in a tensed bow is unobservable. Social systems are epistemologically similar. For example, factories are invisible, what one can perceive is some of their components, employees, buildings, machines, reservoirs, and so on, but not the way they work synergically, which is what keeps them together and going. Even the operations of a corner store are only partly overt. For instance, the grocer does not know, and does not ordinarily care to find out, why a customer buys breakfast cereal of one kind rather than another. However, if he cares he can make guesses, for instance, that children are likely to be sold on packaging. That is, the grocer may make up what is called a theory of mind, a hypothesis concerning the mental processes that end up at the cash register. If the grocer were a neo-behaviorist, he might reason thus: sight of package, appetite, purchase. Observable inputs and outputs, such as publicity and consumer behavior, explain nothing. They only pose the problem of conjecturing the mechanism, likely to transduce inputs into outputs. Notice that this is a typically inverse problem, of the behavior intention type. Once a solution has been found, it allows one to attack the direct problem, input and mechanism output. See figure 5.3. When powerful and reasonably true mechanismic theories are available, as in physics, parts of chemistry, and parts of biology, most problems are direct or can be transformed into such. But this is not the usual case in social studies. Here one has to start nearly from scratch when tackling a new problem. No. 139. General equations of social motion are known that can help predict what an individual or a social system will do when acted upon by certain stimuli, or figure out what were the stimuli and the internal processes that caused the observed reaction. In particular, the time variable does not occur in the vast majority of the formulas in standard mathematical economics, obsessed as it is by equilibrium. 8. Explanation, subsumptive and mechanismic. The standard account of explanation in the philosophy of science,
from Mill to Popper, Hempel, Braithwaite, and Nagel, is the so-called covering law model. According to it, to explain a particular fact is to subsume it under a generalization, according to the schema, law and circumstance fact to be explained. For instance, one may say that Aristotle died because he was human, and all humans are mortal, or that the price of soap went up because all merchandises became more expensive, and soap is a merchandise. All this is logically valid and sound, true. But it does not elicit understanding, and consequently does not qualify as explanation proper. I submit that the covering law model fails to capture the concept of explanation used in the sciences, because it does not involve the notion of a mechanism, Bunge 1967a. For instance, one explains the drying of wet clothes exposed to sunlight by the absorption of light, which increases the kinetic energy of the water molecules in the wet cloth, to the point that they overcome the adhesive forces, and fly off. Senescence and death are explained by wear and tear, inflammation, oxidation, telomere shortening, and other mechanisms that operate concurrently. Cognitive neuroscience explains learning by the formation of new neuronal systems that emerge when they fire jointly in response to certain, external or internal, stimuli, Hebb's law. Genuine explanations in the social sciences are similar. For example, unemployment of a certain kind is accounted for by the spread of labor-saving devices, which is in turn driven by the search for decreasing waste and Figure 5.3 direct or forward problem, A, and inverse or backward problems, B, and C. In principle, given a theory, solving, A, and B, are matters of computation. By contrast, C, calls for a theory that may not yet be available, and is therefore the hardest to solve. A, input mechanism. Output, B. Input mechanism output, C, input. Mechanism output. 140. Increasing profits. Alejandro Ports explained the growth of the informal or underground economy as a perverse effect of the labor legislation designed to protect workers. Mark Granovetter explained getting jobs by the strength of weak ties, that is, information about openings supplied by friends of friends. Wars are explained either by the desire of governments to retain or expand territories, natural resources, or markets, or to win the next election by making the innocent rally around their great leaders at a time of a national emergency, namely, the very same emergency engineered by the very same patriots. In all such cases, to explain is to exhibit or assume a lawful mechanism. This is the process, whether causal, random, or mixed, that makes the system work the way it does. Of course, a mechanism need not be mechanical. There are thermonuclear, thermomechanical, electromagnetic, chemical, biological, in particular biochemical and neurophysiological, ecological, social, and many other mechanisms as well. I call this kind of explanation mechanismic. Use of this neologism is advisable given that most mechanisms are non-mechanical. Let us consider briefly two comparatively simple cases of non-mechanical mechanisms, those of demographic change and social cohesion. To a first approximation, the changes in the numerosity n, t, of a human group are represented by the rate equation dn/dt equals kn. The solution to this equation is the exponential function n, t, equals n0 exp, kt, where n0 is the initial value of n, and k the rate of growth. If k0, the population grows exponentially, if k equals 0, it remains stagnant, and if k0, it declines exponentially. So far, we have only a description, as with all rate equations. The previous description is easily transformed into an explanation if the rate of change k is analyzed thus: k equals birth rate, death rate plus immigration rate, emigration rate. This may be regarded as the overall demographic mechanism of a social system S. That is, we may set m equals k. Incidentally, the sociobiologists are so obsessed with reproduction that they underrate the three remaining demographic mechanisms.
And yet evolution involves not only reproductive success, a large birth rate, but also physiological fitness, adaptation to the environment, and active alteration of the latter, that is, niche construction. All of these processes show up jointly as a low death rate, in addition to migration. Our second example is one of the oldest problems in social studies, namely, what holds society together in spite of the different, and sometimes conflicting, interests of its individual components? There have been many answers to this question, and some of them, though different, are mutually compatible. 141. For instance, according to some, the cement of society is reciprocal altruism, quid pro quo. Other scholars claim that exchange is the glue of society, still others hold that homophily breeds cooperation, that people with similar interests, traditions, values, and customs are likely to get together and stick together. Game theorists design prisoner's dilemma models where people learn to cooperate, or, on the contrary, to defect. Finally, Hobbesians only believe in conflict and coercion. Every one of these views has a grain of truth, but none of them is fully satisfying. We might learn something more by asking, what are the roots of social inequality, disunity, and marginality? Some of the most obvious answers are violence and exploitation, gender, race, class, and ideological discriminations, and residential mobility, see Tilley 1998. How do these causes or motives work, that is, what are the mechanisms that transform them into the observed segregations? It would seem that the mechanism common to all of them is exclusion or non-participation, whether or not deliberate. For instance, women are excluded from most top management positions, medical faculties, and golf clubs, blacks, Catholics, and Jews from WASP clubs, the poor from leafy streets and good schools, and agnostics and labor organizers from high political office. If we now turn to the original question, we realize that the key mechanism of social cohesion is participation, of people of all kinds in social networks of various types, of citizens in campaigns and polls, of women in jobs, of workers in the way their workplace is run, of teenagers in gangs, of seniors in charities, and so on. The notion of participation can be quantitated as follows. The degree or intensity of the participation of, as in BS, example of women in academia, of youngsters in politics, or of employees in management, may be set equal to the numerosity of the intersection of the sets A and B, divided by the numerosity of the guest's social circle A. Thus, a numerical index of social cohesion, and its dual, social marginality, can be set up, Bunge and Garcia Sucre 1976. Since cohesion is sufficient for stability, we may set M equals. Note that, far from being empirical, like most other social indicators, is based upon systems theoretical assumptions about social structure and social cohesion. The same systemic view suggests different indicators of further social features. For instance, we get a handy indicator of community attachment by asking the question, what factors, other than segregation, contribute decisively to social disorganization, that is, to the weakening or even dismantling of mechanisms of social cohesiveness? The answer is that one such factor is residential mobility. Nomads do not fit easily in local social networks, hence they make no significant contribution to their strengthening. In other words, length of residence indicates level of participation in local social activities. 142. Which in turn contributes to social cohesion, Casarda and Janowitz 1974, Sampson 1988. In general, individual features explain collective ones, which in turn contribute to explaining individual behavior. The systems theoretic researcher moves from micro to macro and conversely. In other words, he employs two mutually complementary research strategies, top-down and bottom-up. 9. Realism versus descriptivism. Scientists have always known that to explain the behavior of a system is to exhibit or conjecture the way it works, that is, its mechanism, s. Thus, William Harvey accounted for the circulation of the blood by conceiving of the heart as a pump,
Descartes explained the rainbow in terms of the refraction of sunlight by the water droplets suspended in the air after a rain. Newton explained orbits in terms of forces and inertia. Berzelius, to Hegel's horror, explained chemical reactions in terms of electrostatic forces. Tocqueville explained the fall of the Ancien regime as a delayed result of the aristocrats' neglect of their properties and counties, which in turn followed upon their concentration at Paris and Versailles. 1 century earlier, under pressure from Louis XIV, Darwin explained evolution by descent with modification come natural selection. Marx and Engels explained history by both economic change and class struggle. Einstein explained the bending of light rays in the vicinity of massive bodies by the space curvature induced by the latter. Bohr accounted for light emission by the decay of atoms from excited to lower energy levels. Hebb explained learning as the formation of new neuron assemblies, and so on. We do not understand adequately the things whose mechanisms are still unknown. For instance, nothing but illusory understanding is gained by stating that the mind, or the brain, has computed this movement or that emotion. The computer metaphor is seriously mistaken, for, a. the most interesting mental processes, such as questioning, inventing, and problem-finding are spontaneous rather than rule-directed, and, b. algorithms are artificial rules for performing computations on symbols, not natural and lawful processes. Bunge and Ardila 1987, Searle 1980, Carey and Monner 2002. This is why computers imitate some, not all, of the global features of some, not all, cognitive processes, and not the other way round. A consequence of the computationist fad is that some psychologists prefer doing computer simulations to engaging in brain research intent on finding neural mechanisms. A consequence of such neglect of the minding organ is that depression, schizophrenia, and other disabling mental disorders are not yet being well treated because their mechanisms have not yet been fully unveiled. 143. It is not enough to know that mental diseases are correlated with the imbalance of certain neurotransmitters. To know how such molecular facts translate into mental experiences, such as joy and sorrow, we must find out the effect of the excess or lack of dopamine, serotonin, and so forth, on neurons and neuronal systems. We must climb up the whole staircase, from molecule to brain and environment, and back. No knowledge of mechanism, neither understanding, nor control. The phenomenalist and empiricist rules don't explain, just describe and describe only phenomena, appearances, led the behaviorists and computationists, as well as the positivist philosophers, such as Kant, Mill, Mach, Duhem, Kirchhoff, Ostwald, and the members of the Vienna Circle, to reject the search for mechanismic hypotheses. Yet, ironically, the builders of modern atomic physics, a non-phenomenalist theory, paid lip service to those same positivist dogmas. Thus, in his epoch-making paper of 1925, Heisenberg stated that theoretical physicists should use only observable variables. But at the same time he introduced position and momentum operators without classical and therefore measurable counterparts. Incidentally, the search for suitable position and velocity operators is still on, see Bunge 2003c. In time, however, Heisenberg realized this inconsistency, and complained about his young colleagues who only wished to describe and predict facts. In 1969 he told me, "I am of a Newtonian cast of mind. I wish to understand facts. Therefore, I appreciate the theories that explain the working of things, more than any phenomenological descriptive theories." Bunge 1971. Finally, we note that the quantum theory explains much but not everything. For example, it explains light emission as the decay of an atom or molecule from one energy level to a lower one. But it suggests no mechanism for this decay when not excited by a collision. Although most physicists are satisfied that this is a spontaneous, uncaused, process, a few wonder whether a mechanism for it might eventually be uncovered, which is an instance of the thesis that calculation is not the same as explanation and that there is no final explanation. 10. Philosophical realism postulates that the aim of science is to explain reality. This thesis may easily be conceded, but differences are bound to emerge when it comes to explaining explanation. Mill, Popper, Hempel, and Braithwaite adopted the so-called covering law model, according to which to explain a fact is to subsume it under a regularity. Others claimed that to explain is to propose. 144. A metaphor. Some were led to this view by a superficial understanding of Bohr's model of the atom and Darwin's tree of life, none of which make sense separately from the theories they are part of. Still others adopted the metaphor view of explanation because it is part of the hermeneutic or linguistic turn, the postmodern view that the world turns around words. Rationalists reject metaphorism, because even good analogies can play only heuristic or pedagogical roles. Worse, they can be grossly misleading if taken literally. For example, the linguistic analogy in molecular biology, and the computer analogy in psychology, are misleading because they induce the illusion that the processes in question can be understood even though the corresponding mechanisms are largely unknown. Even the famous particle wave duality in quantum mechanics is misleading, in suggesting that electrons and their kin can be described in classical terms. Actually, the referents of quantum physics are neither particles nor waves, they are sui generis entities. Hence they deserve a name of their own. I have proposed to call them quantons. Bunge 1967c. The confusion over quantons is harmless compared with the hermeneutic view that is gaining currency in the cultural, social, sciences. According to it, these studies are metaphors on metaphors since culture, society, would pivot around language, and the latter is, at least in part, a metaphorical construction of the world, example Tilly 1999. Please, keep talking, for we want the world to keep going. Rationalist philosophers dismiss metaphorism as an irrationalist extravaganza and an excuse for not soiling one's hands in handling real things. And a few of them have realized the importance of mechanism, and thus the superiority of mechanismic explanation over subsumption, example Bunge 1967a, 1968b, 1983, 2004a, 2004b, Kitcher and Salmon, eds 1989, Mackamer, Darden, and Craver 2000. And so, there is progress in philosophy. It may be slow because of conservation mechanisms, such as respect for tradition, willful ignorance, obscurity worship, ideological censorship, and a peer review process dominated by philosophical conservatives. Nevertheless, philosophical advances do occur once in a while due to the operation of countervailing mechanisms, such as grappling with new problems posed by society, science, or technology, institutionalized skepticism, and, above all, curiosity about what goes on behind screens. 145. 6. It is well known that engaging in research of any kind is to tackle cognitive problems. This is why a well-written paper starts by stating the problem it tackles, and ends up by listing some open problems. The general concept of a problem should therefore be central to the study of knowledge. Yet the philosophical literature about problems in general, their logic, semantics, epistemology, and methodology, is scandalously poor. In particular, nearly all philosophers, social scientists, and policy makers have ignored the very existence of inverse, or backward, problems. The exception has been the so-called problem of induction, data hypothesis, though it has seldom been realized that it is an inverse problem. This failure is likely to have nurtured the illusion that there must be an inductive logic just as formal, algorithmic, and rigorous as deductive logic. Yet, inverse, or backward, problems are pervasive, as well as the toughest and most interesting of all. Think of Newton's problem, of inferring, in fact guessing, the laws of motion of planets from data concerning some of their successive positions, of jumping from sample to population, of diagnosing a sickness on the strength of its symptoms, of guessing a past event from its vestiges, of designing a device to perform certain functions, or of figuring out a plan of action to achieve certain goals. Likewise, to guess the intentions of a person from her behavior, to discover the authors of a crime knowing the crime scene,
to image an internal body part from the attenuation in intensity of an X-ray beam, computed tomography, to identify a target from the acoustic or electromagnetic waves bouncing off it, sonar and radar, or to guess the premises of an argument from some of its conclusions, axiomatization. All of these are inverse problems too. And all of them are far harder than the corresponding direct problems. In general, going downstream is easier than going upstream. 146. Direct or forward problems call for analysis, or progressive reasoning, either from premises to conclusions, or from causes to effects. By contrast, inverse or backward problems require synthesis, or regressive reasoning from conclusion to premises or from effects to causes. In other words, work on direct problems is basically one of discovery, whereas the investigation of inverse problems calls for radical invention. No wonder then that the inventors of X-ray crystallography, William and Lawrence Bragg, 1915, the double helix model of the DNA molecule, Francis Crick and James Watson, 1953, and computed tomography, G. N. Hounsfield and Alan M. Cormack, 1979, were awarded the Nobel Prize. Besides, a hallmark of most inverse problems is that, if non-trivial and soluble at all, they have multiple solutions. Just think of planning an activity designed to attain a given goal, as opposed to describing any such activity, of reading someone's mind off his behavior, of detecting landmines in a field, as opposed to planting them, or of the multiple interpretations of a postmodern text, by contrast to scribbling it. We all face inverse problems some of the time. For instance, not only humans but also apes do so when they form theories of mind to account for the observable behavior of conspecifics. However, not even Polya, 1957, who devoted an admirable book to the analysis of problems, realized that inverse problems constitute a distinct category of problems. The widely used collection of problems in analysis, by Polya and Zago, 1925, contains only direct problems. What Polya and others have done is to analyze, with a primarily didactic aim, indirect methods for solving direct problems, such as reductio ad absurdum. Widespread interest in inverse mathematical problems emerged only in the last few years. The vast majority of philosophers have been remarkably laconic on inverse problems, with the sole exception of the induction, or data hypotheses, problem. Since this is an inverse problem, it is likely to have either multiple solutions or none. The reason for this is as follows. By definition, a hypothesis goes beyond the data relevant to it. It does this in at least one of two ways, either because the hypothesis involves a leap from some existence to all possibles, or because it includes concepts that, like those of causation, mass, intention, and national sovereignty, do not occur in the data because they are not experiential. In sum, since data do not exude hypotheses, these have to be invented. And, of course, once invented they have to confront both old and new data. We will return to this problem in Chapter 7. To emphasize the sharp contrast between the two kinds of problem, direct and inverse, and to better understand the nature of inverse problems, let us look at a sample of problems occurring in various branches of learning. The 147. Goal of this exercise is not to attain truth by induction, but to become familiarized with the beast. After all, philosophers of science should expect more from analyzing real cases of scientific research than from rereading and reinterpreting classical philosophical texts. One preliminary sample. To find a shadow projected by a solid body on a given surface is a direct, or forward, problem with a single solution. Projective geometry and its application, descriptive geometry, provide precise rules for solving this problem familiar to machine designers and cartographers. The corresponding inverse problem is to reconstruct the shape of a body from one or more of its infinitely many projections or plane maps. Like nearly all soluble backward problems, this one has multiple solutions. For example, when staring at a Necker cube, an ambiguous plane representation of a cube,
One sees now a cube facing to the right, and about 30 seconds later a cube facing to the left, or conversely. The early spectroscopists faced an even harder task, that of inferring, actually guessing, the composition and structure of a light source, such as the Sun, from the line or band spectrum it emits. This inverse problem was a major motivation for constructing the quantum theory. With the help of this theory one can solve, at last in principle, the corresponding direct problem, given, assuming, the composition and atomic or molecular structure of a source, find the frequencies and intensities of the light it can emit. Again, finding the traces left in the world by a well-defined deity, such as one indulging in planting bogus fossils, is a trivial direct problem, since every feature of the world will be attributed to its creator. By contrast, inferring the profile of the deity from a study of creation was the goal of the natural theologians of the first half of the 19th century, as well as of the contemporary professors funded by the Templeton Foundation. Somehow, no definitive identikit of the creator has resulted so far. The preceding set of problems constitutes only a minute sample of the vast family of inverse, or backward, problems that pop up in all fields of research, policy, and action. A larger sample is shown in Table 6.1. To the direct, inverse relation, generalities. The general concept of an inverse problem is familiar to mathematicians, physicists, and engineers, to the latter under the names of synthesis and reverse engineering. By contrast, the concept is unfamiliar to most social scientists, policy makers, and philosophers. A major reason for this gap is of 148. Table 6.1 Sample of forward versus backward problems. The arrow symbolizes the research process, from givens to solution, S. Direct or forward, inverse or backward. Algebraic equation, roots algebraic equation, antenna, waveform antenna, S, artifact, function, task, artifact, S, author, text, author, axiom, system, theorems, axiom, system, S, basic science, applied science, basic science, brain in society, mind, brain in society, cause, effect, S, effect, cause, S, computer program, computation program, creator, creation, creator, crystal structure, diffraction pattern, diffraction crystal structure, dynamics, kinematics, dynamics, disease, symptoms, disease, earthquake, center, seismogram, quake center, equation of motion, trajectories, equation, field equations, field intensities, field equations, force, S, movements, force, S, gene mutation, mutant phenotype, mutation, generalization, particular case, S, generalization, grammar, sentences, grammar, ideas, speech, ideas, initial date. Radioactivity, initial date, input, output, desired output, requisite input, intention, behavior, intention, legislation, social behavior, legislation, mathematical function, derivative function, mathematical function, integral function, means, goal, means, organ, role, organ, past, present, past, plain text, cipher, text, plain text, plan, activity, plan, population, sample, population, potential, field, intensity, field. Intensity, potentials, probability, statistics, probability, question, answer, question, S, reagents, chemical compound, reagents, scatterer, source, example, atom, spectrum, source, example, atom, stimulus, response, stimuli, technical design, description, specification, technical design, theory and data, predictions, data theory, transaction, budget, transaction. 149. Course that the latter fields of studies are mathematically underdeveloped. A second reason is the popular belief that a sufficiently powerful computer can handle any problem. A third reason is that inverse problems are far tougher than the corresponding direct problems. By the same token, inverse problems are also more intriguing, more demanding in ingenuity, experience, and labor, and often also more rewarding than the corresponding direct problems. Think, for instance, of guessing equations of motion from trajectories, of conjecturing the forces that scatter a beam of particles,
of imagining the genotype environment combination that produces a given phenotype, visible appearance, of hypothesizing the situation intention combination behind a given action, of ferreting out the grammar underlying a text, of guessing the way of life of the people who left behind certain archaeological remains, of imagining the artifacts that might perform a desired task, or of designing the industrial and commercial process that might yield a given return. A highly developed research field contains plenty of special methods, techniques and algorithms, for tackling direct problems of various kinds. By contrast, there are no special rules, in particular algorithms, for solving the vast majority of inverse problems. The usual way to go about them is to proceed by trial and error, to figure out and try out different hypotheses until the correct one is found. In turn, the latter is found by scanning and varying the existing set of similar solutions to the corresponding direct problems. By proceeding in this way, an inverse problem is rendered equivalent to a family of direct problems. In particular, an inductive problem is thus transformed into a set of deductive problems. However, before setting out to solve a problem we had better find out whether it is direct or inverse. And how do we distinguish an inverse problem from a direct one? To my knowledge, so far no generally accepted general and precise definition or criterion has been proposed. The following rules of thumb are tacitly used in different fields. 1. Mathematics: all the problems soluble with the help of well-defined techniques, in particular algorithms, are direct, whereas the converse process, that of recovering such problems from their solutions, is inverse. Examples: a. Roots of an algebraic equation, b. Dots curve, c. Theorem postulate, s. And definition, s. 2. Natural and social science: the inverse problems are of the forms, effect cause, sample probability distribution, property thing, behavior mechanism, or macro level micro level. Examples: a. Figure out the bond, S, that holds the constituents of a given system together, b. Discover the neuromuscular circuit that performs a given behavioral task. 150. c. Guess the decisions that triggered the individual actions that gave rise to a given social event. 3. Technology: the inverse problems are of the forms function mechanism and dysfunction defect in mechanism. Examples: a. Design a process for the mass production of a given drug, b. Design or redesign a formal organization to carry out a given task, c. Find out the causes of the malfunction of an artificial system, such as a computer or a bank. These and similar examples suggest the following pair of conventions. Definition 6.1 A direct or forward problem is one whose research goes down either the logical sequence or the stream of events, that is, from premise, S, to conclusion, S, or from cause, S, to effect, S. Definition 6.2 An inverse or backward problem is one whose research goes up either the logical sequence or the stream of events, that is, from conclusion to premise, S, or from effect to cause, S. Two caveats are in order. The first is that simplicity is irrelevant here. Although most inverse problems are harder than the corresponding direct problems, there are exceptions. For example, given a finite set of numbers, together with the fundamental theorem of algebra, we can easily find the algebraic equation that those numbers solve. By contrast, there may be no algorithms to solve the given equation. The second caveat is that sometimes more than one inverse problem corresponds to a direct one. For instance, consider the equation AF equals G, where F and G are functions, and A is the operator that transforms F into G. The direct problem is, given A and F, find G. The same equation raises two inverse problems. The simplest of them is, given A and G, find F. If A has an inverse, the solution is F equals A, 1G. The second inverse problem is much tougher, and it has an uncounted number of solutions. Given G, find A and F. For example, given the spatial distribution G of some stuff, find the law that relates G to the field F generated by G.
The problem encountered by the founders of the field theories of electromagnetism and gravitation was precisely of this kind. Let us now proceed to examining the peculiarities of inverse problems in some research fields. In the present chapter we will look at mathematics and physics. Some of the other sciences and technology will be tackled in the next chapter. 3. Logic and mathematics. Wittgenstein, 1978, that great trivializer, regarded mathematics as a game. Indeed, he believed that doing mathematics is a matter of following rules. This is, presumably, how he taught at elementary school the mathematics he 151 knew. Paul Bernays, 1976, Hilbert's closest co-worker, aptly called it household mathematics. When the rules are known, mathematical work is not high-grade research but rather routine work, if often demanding and time-consuming. Such work can often be entrusted to a student or even a computer. When algorithms are available, the student is spared the effort of imagining any tricks. He tends to memorize rules and to go about problem solving in a rather mindless way. For instance, he may calculate integrals even after having forgotten the definition of an integral. This is why the study of Euclidean geometry, which is bereft of algorithms, can be more formative than that of analytic geometry, which resorts to algorithm-rich algebra and the calculus. Original mathematical research, like research in any other field, starts by spotting, inventing, or tackling research problems, that is, interesting open problems. And inverse mathematical problems happen to be research problems par excellence, because there are few if any rules, in particular algorithms, for solving them. In particular, the endeavor to invent a rule or method to solve mathematical problems of some kind is itself an inverse problem of the goal-means type. This endeavor is so daunting in the case of inverse problems that the bulk of what is presumably the longest and most recent treatise in the field, Methods for Solving Inverse Problems in Mathematical Physics, by Prilepko, Orlovsky, and Vazin, 2000, is constituted by theorems on the solubility of inverse problems, in particular on the conditions for the existence and uniqueness of solutions to them. To a physicist or engineer this is like leaving a restaurant without having eaten anything, but having paid the cover charge for the privilege of reading the menu. To get a feel for mathematical inverse problems, let us examine a couple of elementary examples. The first is to decompose a given natural number into integers, which is harder than adding given integers. Thus, 1 plus 2 equals 3, whereas 3 equals 1 plus 1 plus 1, and 3 equals 1 plus